Broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, welcome to PYRO Asia 2020. We are in day 3. I thank you again for all the sponsors supporting this event, and let's get started. Okay, just give you a quick in review about today's schedule. Okay, we try to be there are lots of oral presentations today. We make sure we try to be on time. And as you see, we session 7, session 8, session 9, we have, and also we at the end of the session 9, we'll have announcing Young Research Award, and also what will be the next, where will be the next event will be held, and so this is schedule. As I said, I try my best to make on schedule all the things. Okay. Professor Ji Feng, can you please unmute your speaker, please? Currently, you are muted. Can you please unmute your speaker, please, Professor Ji Feng? Okay, can you hear me, sir?
Hello?
Yes. Okay, you are there.
Yes.
Yeah.
Yes.
Good, yeah.
Yeah.
Okay.
Yeah. Okay.
Ji Feng is here. Okay, now we get
Hi.
started. Yeah, just a second, sir. Okay, how to ask the questions? This, I think most of you know about this, and I just wanted to reinforce this point. If you have any questions of any presentation, please post your questions in the question box. I will, and make sure you attention to the speaker name so that we knows who is you want to ask to whom. Okay, so please follow this. Okay, thank you. This is me, Param Prasad Rao. I just give you a quick, you did not see me for the last 2 days. Just give you the picture of mine. Okay, and I own the company called Technobase. It is International Resource Center for the Polymer Industries and Process Technologies. I have 23 years experience in polymers, energy, and environment. I'm a chemical engineer. Okay, so just quickly, if you have any questions, you can contact me. I guess you know my numbers, email address. Okay. Okay, let's get to the first session today, and the focusing on applied pyrolysis, biochar, and advanced materials. Let me open this. Okay. And the session chair is Professor Ji Feng Zheng. Professor Ji Feng Zheng, welcome. And I think yes, most of you heard him yesterday. Okay. Okay, and so I welcome Professor Ji Feng to introduce the session, and yeah, please, sir.
Yeah. Okay. Can you hear me?
Yes, we can hear you, sir. Please go ahead.
Hello?
Yes, we can hear you.
Hello?
We can hear you. Please go ahead.
Okay. Okay. Just wait a minute. I'm sorry. Today, it's my pleasure to share this section. Today we have one plenary invitation speaker, Dr. Just 1 minute. Open. Dr. Yusik, okay. She will give us a presentation, smart biochar technology, shifting paradigms towards advanced materials and healthcare research. He is from Korea University. So let's welcome Yosik, okay. Give us a friendly lecture. Professor Yosik, okay. Can you hear me?
Yes.
Okay, please.
Yeah, so could you please turn off your speaker and microphone?
Turn off my speakers. Okay.
Okay, let me quickly introduce, Professor Young Sik. Okay, I think, most of you met him, at yesterday's briefly in the session. He's from the Korea University. I'm introducing for the sake of for benefit of everyone. His academic background, he's a director of Korea Biochar Research Center. His academic background covers waste management, bioavailability of emerging contaminants, and bioenergy and value-added products. He also experienced in the fundamental soil science and remediation of various contaminants in soils and sediments. Together with his graduate students and colleagues, Professor Oke has published over 600 research papers, 85 which have been ranked as the Web of Science ESI top papers, 78 named as highly cited papers, and 7 nominated as hot papers since 2009. He maintains a worldwide professional network with his service as an editor of the Critical Reviews in Environmental Science and Technology and editor of the Environment Pollution, and as a member of editorial boards of Renewable and Sustainable Energy News, Chemical Engineering Journal, Chemosphere, and the Journal of Analytical and Applied Pyrolysis, along with several other top journals. Guys, as you see, he is one of the legends, I guess, in this field. I'm sure you find his presentation is very useful. Let me share Professor Yok's screen.
So thank you so much for your kind and detailed introduction. I'm very honored to get your intro today. And hello, everyone. Very nice to meet you today. And personally, sorry. Can you see my screen now?
Yes, we see your screen. Go ahead, sir.
Yeah. Thank you. So as a co-chair of this PYRO Asia conference, together with colleagues from Singapore, China, Japan, Malaysia, and so on, I'd like to thanks to Kartik for his big lead. And today, in my plenary presentation, I'd like to talk about the sustainable waste management. Under the umbrella, I'm going to talk about smart biochar technology. Actually, the term smart biochar tech is initiated by myself, that based on my review article since year 2014. I'm currently, as introduced, work as Korea University, and just last week, QS ranking in the world, Korea University become ranked #1 in whole Korean university, and then we become one of the top 10. It's exactly top 11 in whole Asia, and is the best private university in Asia for 4 consecutive years. And our university is ranked one of the top 60s in the world. And also, I have an honorary professorship at the University of Queensland in Australia. So just for brief information for sustainable waste management program that I'd like to introduce to you. I understand I have roughly for 30 minutes, so it's currently 2:10, so I will finish before 2:40. So APRO was established in US in 1997 by the president of UCLA, president of UC Berkeley, and president of Caltech, as well as University of Southern California. So it has now a membership of president of 51 leading research university from all around the Pacific Rim. So APRU Sustainable Waste Management is my own program, which belongs to the APRU. And APRU, we have currently 2 million students. We have more than 200,000 academic staff, including faculties and the supporting staffs. So this is brief information. Our APRU, we have president of UCLA, Professor Jin Block as a chairman, together with president of Chulalongkorn University in Thailand, president of Fudan University, president of Korea University, and president of Hong Kong UST, and so on. So all of the extremely well-known 55 university presidents are all involved in this program. And here I'm at the APRU. I'm officially serving as a program director for APRU Sustainable Waste Management Program. If you need any additional information, you could click the link below. Or if you need my full PowerPoint slide, I'm happy to provide upon your request, or I can upload it in a chatting site so that you can feel free to download it. For the sustainable waste management, deposition of waste result from severe land, water, and air pollution cause tremendous negative impact, not only for human. Sorry, my slide it just disappeared. Hello, organizers.
Yes, I can see you. We can see your slide.
But I cannot because someone just appeared and then my slide gone. So I'm just trying to see how I can do it. Okay, so maybe it works now, right?
Yes, it is. Yes.
Okay, thank you. So sustainable waste management, it not only for the human being, but also for flora and fauna diversity in ecosystem. So our program focus on recycling and recovery of all type of waste material while paving the way toward circular economy, land reclamation, and water and wastewater treatment. And currently, my program, I'm serving as a director of program, and we have a program co-director, Professor David Wader at Nanyang Technological University. He worked as editorial board of Science Journal for 8 years. And Professor William Mitch at the Stanford University, he did his bachelor at Harvard University Archaeology, did master PhD at the Berkeley, and he was very well-known professor at Yale University. Since year 2013, he moved to Stanford University, serving as a full professor there. So Bill Mitch and myself and David Wader, we are serving as a director of the program, and I'm leading as a main director. So just about 5 months ago, in end of June, we had a meeting. It's called the annual president meeting. If you see this photo, I'm located on top of the right corner. But other than myself, I'm currently a program director, but most of the participants here are university president. You see here, he's the president of Nanyang Technological University, president of UCLA, and president of Berkeley, and so on. They all attended this important meeting. And during the meeting, my program was shortly introduced. And as you see here, COVID-19's unsustainable waste management was introduced during the same month. So this is our recent letter in Science titled COVID-19's Unsustainable Waste Management with the name of Korea University together with the April Sustainable Waste Management Program. Here we've been emphasizing all the plastic and waste comes from near hospital and healthcare center. And we've been wondering how we can protect the waste management chain. How does it help achieve UN Sustainable Development Goal? That was a big initiation, and our program is currently working on the turning all the waste into biochar and using biochar to solve problem of plastic pollution. So this photo shows one of my field test site, which is located in southern part of Korea. We have constructed a plastic film house and then applied a lot of plastic that we know their composition. And then we are currently tracking the fate of plastic in the environment, and then try to use the biomass-derived biochar to control this plastic issue. And I trust this is the only field-scale application looking at the interaction between plastic and biochar up to now. And we have moved on to the second stage based on this project. And I hope to share some interesting results with you soon. And also in very recent science letter with Michael Banks from Institute of Marine Research in Norway, Massachusetts in US, we reporting microplastics role in antibiotic resistance. Then just this month, 1st December, we have hosted the first virtual Nature Forum on plastic and sustainability. So as you know, plastic pollution is a pressing environmental and public health problem related to large quantity of single-use plastics, its persistence in the environment, and low rate of plastic recycling and regeneration. So during this event, plastic waste management, the fate, transport, effect of micro and nanoplastic in the environment, public policy are discussed. A panel discussion with the speaker, we identified the key research need in plastic research and to provide a potential solution to plastic pollution in the context of relevant UN SDG. If you visit the website, though this event is finished, you can still register and watch the whole video. It's 100% free. And that event was together with me, the Fabio, who is the editor-in-chief, Nature Sustainability, Laura, the associate editor, Nature Review, Earth and Environment, served as a scientific organizing committee together with the project leader from Nature Research in Korea, Japan, and USA. And this particular event, we got really world-renowned speakers, including Professor Lilik from Germany, and Professor Caroline from Hong Kong, Professor Denise Mitrano from ETH in Switzerland, and Professor Michael Bank from Norway and USA. And we got 1,300 participants registered for the event. And for the real-time presentation, we got almost 900 participants fully attended this event. So hope you can still visit website below. It's gonature.com, plastics forum. You can watch the video. And you can see the some of my ongoing project, shortly introduced at the end of the presentation. Okay, and then just next week after PYRO Asia, we've been hosting another important event. It's Engineering Sustainable Development Conference that we're gonna talk about the plastic pollution and sustainable biochar to address UN SDG. So hope you can join this event. If you want to join but difficult to register, just please inform to me. And this review article is this year. It's published in a Nature Review after I got an invitation a year ago. In this particular review, I have fully focused on looking at the soil pollution linked with UN SDG, such as UN SDG 1 is no poverty, SDG 2, zero hunger, SDG 3, good health and well-being, SDG 6, clean water and sanitation, and so on. And this article published in Nature Sustainability is one of the examples that how does soil pollution linked with UN SDG, and what will be the possible management strategy for the soil pollution. Okay, and this slide shows some of my ongoing research that use biochar to address soil pollution issue. And then particularly today, I just want to talk about for the how I use the biochar or smart biochar technology to address the UN SDG. So I very briefly go through for my center have worked on during the last 10 years. Actually, my biochar center opened officially in year 2010. And next year, gonna be our 10th anniversary. So we are preparing 10th anniversary conference together with nature. That's for waste management conference gonna be held at the Korea University end of next year, together with editor-in-chief of Nature Electronics, editor-in-chief of Nature Nanotechnology, editor-in-chief of Nature Sustainability, together with April Sustainable Waste Management Program, which include Professor William Mitch from Stanford University, Fabio and Ovine and Yaquin and Monica, they are editor-in-chief at Nature Sustainability. Yaoqing is the senior editor at the Nature Sustainability, but he worked previously at Nature Communication. So now turn to the topic. I will talk about a bit more biochar. I understand during the last 2 days, there were a lot of presentation. All participants talk about the definition of the biochar, but look like that definition is somewhat not consistent. But overall definition, we consider this biochar is produced by so-called thermal decomposition of organic material on the limited supply of oxygen at a relatively low temperature. So we all know that this biochar is very stable in the environment. So compared to uncharred organic matter, biochar is stable enough. So its half-life is going for a few thousand years, at least. So one of my colleagues, Professor Jakob Kujakov at U of Göttingen in Germany, conducted over 10-year incubation experiment, confirmed that the composition of biochar takes 4,000 years, which means this carbon in the biochar is so stable, so they're not going to be easily decomposed. So we can sequester the carbon through the biochar application. That's a big motivation. Exactly 5 years back, if you see here, 5th International Symposium on Soil Organic Matter. That conference is one of the largest conferences deal with organic matter. At that moment, Professor Johannes Lehmann at the Cornell University, we invited him as a speaker, and Jakob Kujakov at Göttingen in German served as chairman, and I was chairing biochar session 5 years back. And then we, through this symposium, we published a special issue for biochar and plant soil interface, together with Professor Johannes Lehmann at Cornell University, Professor Jakob Kujakov at University of Göttingen in Germany. So at the beginning, biochar and the plant soil interface editorial provide our perspective for the biochar research in the field of soil and environmental studies. So if you have any interest, you can check this editorial published at Plant and Soil. Plant and Soil is one of the best journal in the field of soil science. Okay, so I just want to share this one with you. I remember yesterday one of the presenters showed a similar figure, but number of publication in biochar is sharply increasing. It reached this year almost over 3,000 paper during only for the 1 year registered in a Scopus, which means the paper which is not registered at the Scopus, including every document, should be over 5,000. I didn't show this slide to probably. For this one is for the shows information what countries are reading this biochar research. As you see here, China, US, Australia, India, South Korea, UK, Germany, Canada, Pakistan, Italy. Those are top 10 countries that read biochar research up to now in terms of number of publication. And this figure is my own, and I don't think none of you can access this data, but if you need, I can share. In this particular article with a company, analytical company with Pluto, we have analyzed change in journal, which cite biochar. We found that publication that cite biochar are high quality as well. I mean, the paper that cite biochar research is also very high quality. More than half of those which cite biochar are from top Q2 journal of JCR category rank. Citation are increasingly coming from JCR Q1 journals. If you see here, blue shows the JCR Q1. So compared to year 2011, 2019, have huge amount of Q1 journal article, which means at least in the field of biochar, number of publications sharply increased. More importantly, quality increased a lot. It's going to Q1 journal. I want to show this slide with you that may bring more attraction. We have analyzed analysis on the top 1,000 most cited paper in year 2020 and have analyzed 57% of the whole article published in one of the 10 journals. Bioresource Technology, Journal of Hazardous Material that I served as first co-editor-in-chief, Science of the Total Environment, Journal of Environmental Management, Chemosphere, Soil Biology and Biochemistry, Chemical Engineering Journal, Environmental Pollution, Environmental Science and Technology, Journal of Cleaner Production are the 10 journals that publish the most of the article. So at least for 10 journal, I also served as associate editor or editorial board or editor-in-chief or guest editor for all the 10 journals. And if you somehow working on biochar, if you're not sure where to submit, one of the 10 journal might be a good destination for your research. Okay. And now let's looking at the trends in biochar. I also worked with Pluto and made this map. It shows top 20 countries by number of publication and also by citation from 2011 to 2020. If you look at the number of publication, then US, China, Australia, India, South Korea, Japan, and all European countries publish a lot. If you look at the number of citation, then also the US and China are pretty good in terms of the quality, but Australia is also pretty good, as well as India. Okay. And this slide now shows production technology, but in terms of production, there are a lot of experts, especially for this PYRO Asia conference. I see a lot of the chemical engineer or the chemist who is working on pyrolysis or gasification or process simulation with Aspen Plus yesterday. So I'm not going to talk much about the production technology, but I will just skip for the slide that I prepared. This is the production method that I have summarized. And this is one of our plant, or one of our major company. So I've been visiting this company together with my colleagues from Japan, from UK, and from other Asian countries. So this shows commercially available the biochar feedstock and application. As you see here, most of the product for biochar is commercially used as soil amendment or soil remediation. So from now on, also I want to talk about my application of the biochar in the field of soil remediation. And this shows biochar characterization that's available in our center. Just for your information, the Korea Biochar Research Center officially announced 10 years back. So it started in year 2010. And we have organized the very first Biochar International Conference exactly 10 years back. And currently, we have around several hundred biochar samples that produced by our own or produced by other countries or other centers collaborator. And we have fully characterized data available, such as synchrotron or XRD or TGA, FTIR or XPS and so on. So if you need any collaboration in the field of biochar, especially if you need any characterization or if you need any sample for your application, you can reach us, then we can provide more detailed information. In terms of research trend, many research during the last 10 years focus on soil remediation. I wrote this review just 6 years back, but two of my review up to now cited more than 3,500 times, which means using biochar for soil remediation or water treatment is one of the hottest topic up to now. And now many people working on designing or engineering biochar. Yesterday, I remember there were a few presentation was the catalyst. So we can, of course, use biochar as a catalyst, but it depends on how we design it. So for that purpose, I performed this analysis with the Pluto company that, as you see here, graphite biochar or iron biochar is to the most hottest area in the field of biochar nowadays. If any one of you are working on graphite biochar or iron biochar, you have a very high possibility that you will get high citation in the future. And it is one of my main application of the biochar that, as you know, the animal, the carcass disposal site in Korea, because of the outbreak of foot and mouth disease in the year 2011, due to this event, the animal burial pit contaminated our farmland and crop, and we saw that veterinary antibiotic, pharmaceutical, and personal care product, as well as some heavy metals or trace element, contaminant, occur from the leachate. So we developed the biochar and engineered the biochar into the soil column, try to look at how does biochar application control the transport of antibiotic. As you see here, properly designed biochar was very effective to control transport of specific antibiotic in the soil. Also, we have developed this schematic presentation, how we can use biochar to control pharmaceutical and personal care product. And all the figure that I provided is my own figure, so that's available in my own articles. This is another work for using biochar for soil remediation, specifically for heavy metals. We have worked on germination test and did bibliometric. One of my recent review article fully analyzed, comparing the biochar with known amendment. We confirmed that biochar is one of the most effective amendment that can immobilize heavy metals in the soil. We also got an invitation, were able to publish our work in one of the material science journals. You can refer to this review article. After that, our group, especially Professor George Linkleber in German, got one more invitation, and currently we are writing another review for the same journal. Okay. And this is our newest work that we work with Professor Shannon Wang at National University of Singapore for the application of artificial intelligence, machine learning, and deep learning for biochar research. And up to now, a few of our recent papers are available using machine learning for biochar study. And currently, this is our newest work that we've been working on. How we can predict heavy metal immobilization efficiency with biochar with machine learning. That's what we are currently working on, and that result might be available within next 1 or 2 months. I hope to share the result with you in any future conference, but I just shared some of the slide. Lastly, also, we've been working a lot for the synchrotron, try to look at the mechanisms. So shifting paradigm means exactly 13 years back, a handful of carbon. So biochar can sequester carbon was mentioned in Nature. And 10 years back, Saransoy reported in Science, biochar has certain benefit over carbon storage. And then year 2014, biochar by design is published in Nature Geoscience, and making biochar to be smart can solve a lot of problems. Last year, read by Chinese government, the new journal at the Nature Springer named Biochar has been published. So this journal currently, mock impact factor is around 4 or 5.0. So this journal could be one of the leading journal in the field of biochar in next few years. And then now I'd like to very briefly introduce for our newest work is emerging application of biochar. This is using biochar as a supercompensator or as a self-healing material. And this is, my group is currently working on using biochar to capture the CO2. And some of our theoretical review or experimental data have been published in a top journal in Green and Sustainable Science and Technology. And she's my PhD student, Pavani. Actually, she has a presentation today. She's gonna talk about some of the related topics today. So I'll just skip for this presentation. Also, Dr. Yuan, research professor in my group, is working on how we can do further activation and produce porous carbon that can capture CO2 more effectively compared to pristine material. Also, my group is working on using biochar under the Hydrogen Society. That is our newest figure, which is not published yet, but I'm just sharing in the slide. And finally, together with Professor Chia Wang at National University of Singapore, we've been working on using biochar in healthcare research. And here on the right side is Professor Beck, is a medical doctor in National University of Singapore at the hospital. So we've been working on toxicity of biochar as a kind of the new topic. So overall, this biochar is proven technology, is known to provide a solution for many of the UN SDG. And I really hope for you to all join Nature Conference end of next year. This is the very first conference organized with Nature for waste management and valorization for a sustainable future. Of course, biochar is one of the main topics of this conference. So I hope to see you all in next October, and thank you very much for your attention. The time is 2:40, so thank you.
Thank you very much. You are on time, sir. Okay, guys, let me take over the screen. Okay. Okay, do you like to ask any questions to Professor Okay? Yes, I have some questions. I still not received yet. Okay. Can we put a question and answer session during the after oral presentation, sir? Is it already with you?
Sure,
so that they have the time also to think to what kind of questions to ask to you. Yeah. Okay. Yeah. Okay,
yes. Thank you so much. Yeah. I'll do that. Thank you.
Dr. Jifeng, do you like to ask any questions or any comments on the Professor Okay's presentation? Professor Jifeng, can you unmute your speaker, please? Okay, I will continue the next presentation. Okay, if we have any questions to Professor Yoke, you please post a question in the question box, and relevant questions will be addressed at the end of the session, please. Yeah, thank you. Okay, the next Okay, the next lecture, the keynote lecture, is by Professor Thallada Bhaskar. Is from the Indian Institute of Petroleum, and he's going to give a talk on the pyrolytic approaches for the valorization of waste polymeric materials. I think yesterday I have briefly mentioned, he was in the panel discussion, so I have introduced you all, and let me straight away to ask him to share his screen. Just a second, yes. You are self-muted, sir. Can you unmute your speaker, please? And also I send you a webcam. Yeah. Okay. Okay, can you put on your presentation mode? Yes. Okay, good. Yes, all set. Yeah.
Is it visible?
Yes, it is. Yeah.
Yeah. Good morning to you all. and organizing committee members for giving me an opportunity to share some of our works and the concepts which are being practiced and experimented here. In continuation of the panel discussion and the kind of questions raised by the participants, we thought to share the different approaches and the underlying considerations, points to inform the audience. With this background, would like to go ahead. For the audience who are from the different countries, I am located at Dehradun, which is in the Uttarakhand state of India, which is close to New Delhi, which is around 300 kilometers, and close to Himalayas. It is one of the laboratories under Council of Scientific and Industrial Research under the Government of India's Ministry of Science and Technology and Earth Sciences, which is one of the laboratories located in the CSIR. CSIR has around 38 laboratories, which is a nice place, beautiful and picturesque, close to the river Ganga and Himalayas. And as we are talking on the conference on the PYRO Asia, as Professor Oak mentioned the advantages of the converting the biomass materials, as well as the contribution of one of the products in the pyrolysis as a biochar for diverse applications, from the healthcare to the soil, and soil only gives us the food for the health. So it is everywhere, and the biogenic material transformations, how best we can use. With this, to extrapolate these concepts, we can think of how best these approaches and these biological materials and the biomass materials will address the human well-being. That is to address environment, economy, and equity. We have been looking these biomass materials or the bio-based materials are the oldest form of the biomass, that is the fossil-based hydrocarbons, which are again from the biomass, but they are interconnected, which is to see the ecological life support systems, which are air, water, soils, climate, nutrient cycles, and the biotic communities. And if we wanted to talk about economic support, that is markets, income, wealth, employment. So like this, if we talk of one activity, one point, it also depends on the other parameters. So we need to look in a balanced way and sustainable way of utilization and exploitation of these materials to address. Otherwise, we are going to have a big problem. As we know very well that the issues in the increase in the CO2, global warming effect, and also the linear way of the economic growth, which generates huge quantity of the waste, and also at the same time the energy used for the different applications, and also the present virtual trend, the electricity which is required for all our activities, including the Wi-Fi, broadband, TV, whatever it is. So we have interconnected and to produce these kind of the commodity and the activities. So in a nutshell, we can say that the linear economy has been providing the economic development, but at the same time the environmental degradation is taking place. But when it comes to the circular economy, we can avoid the environmental degradation while looking at the economic development. So the challenge is now to decouple the economic development from the environmental degradation. So that is what the sustainability comes at the place. And also the challenge top order to have the economic incentives and the optimal utilization of the energy in it. So with this, the resource efficiency is the mantra, because there are sources, renewable and non-renewable resources, and the resources which are limited. So the resource efficiency is most important to use either less resources for a given or required output, or the alternate way to improve the resource efficiency is for a given resource usage, get the more output. If you are addressing or if you are able to adopt one among them, then we can achieve slowly on the pathways for the resource efficiency. With this background, if we look at the soil and the essential elements which gives our basis for the life as well as for the sustainable, to couple with the all kinds of farmers of the life. So at IIP Dehradun, the ideology, the concept to say that our division, that is material resource efficiency division, to shift from the linear economy to the circular economy and use the essential elements on the soil, on the earth, carbon, nitrogen, phosphorus, oxygen and hydrogen, which are basic elements for the life on the earth, which may be converted into the different forms to optimally utilize to produce the required products, consume, then reuse and repair, while having the different scientific technological interventions in the different modes. So we have to address all these elements in this. Just now Professor Oak has mentioned that the biochar, which is the carbon, and basically which has served several applications, including to the environmental issues as well as the healthcare issues. So for a life, we need the nitrogen, phosphorus also to grow to have the biotechnological or microbes, enzymes. We need these kind of all these elements and nutrients in one form, the other form. So with this concept, we are trying to see how the Indian scenario to use to address the economics as well as the environmental benefits. Now we are all looking and hearing the news that the global warming and the volatility of the fossil prices as well as the economy's disruption. Now if we look at the Indian scenario, now India is importing around 300 metric million tons of the carbons when you compare with the carbon contents in the crude oil, coal, natural gas, which are the major imported commodities to the India. So if we have around 350 metric million tons of the carbon here, we can avoid or we can stop the import of these kind of resources to utilize or to address the requirements in the Indian population. If we see the broad or the major items or the commodities, agri residues, forest residues, biogas or the MSW or UCO, now if we calculate the amount of the carbons in these items, more than 500 metric million tons of waste carbon is there, excluding the CO2 emissions. That means that the demand which is for the carbons are available in Indian scenario. So we have to convert, we have to use these kind of resources to address and for the requirement of the economic growth as well as to avoid the environmental consequences due to the emission of the CO and CO2. In order to show that one, the government of India has been striving to understand, the locate and the quantify qualitatively the amount of the biomass. Now you can see here the major residues available in India. You can see that around 660 metric million tons of the residues and surplus around 250 metric million tons of the biomass is available. Now you can see that the basic major portion is around rice straw, that is 82%, remaining the 5% rice husk, cotton straw, wheat straw, bagasse around 2%. Now we can see that the bio-based residues which are available pan across India, then we have to understand these properties. Now, as I mentioned that if we have those kind of carbon resources, we can convert those kind of carbons for the required fuels or the chemicals, but it is not a simple approach to use or the one technology to address these kind of 82% of this rice straw. It is a typical simple example. If you can see in continuation of my point in the panel discussion yesterday, that the lignin content variation of a rice straw in 3 different parts of the country from 5% to the 30% of the lignin. It shows even though it is a rice straw, the variation of the lignin is too much. Hemicellulose and the cellulose also in similar quantities. It shows that the development of a technology or the available process either in India or other parts of the world, it is not directly suitable, applicable on the Indian situations or the Indian waste resources or the waste carbon resources or the biogenic resources. So the process has to be decentralized or the process has to be optimized to the available biomass with respect to the composition available. So that is a huge challenge. With this, as we have seen a typical example of the how variation of the composition and the science or the technical process technology has to be adopted for the different. So in this, considering these complexities, we have been working on the different processes in the thermocatalytic process, from understanding the composition to the kinetics, carbonization to produce the different biochars, as well as the different forms of the pyrolysis, dry process, as well as the liquefaction, where if the biomass is having more than 50, 60, 80% of the moisture from the aquatic biomass, we need to implement or use the liquefaction process to produce the derived chemicals or the functional chemicals or some crudes which are used to upgrade the fuels and there. So this is the conceptual point that unlike the fossil-based refinery, we need to have a decentralized small-scale units to compact and increase the density of the biomass to convert the liquids or the chars to apply at the soils, as well as the local applications to the diverse applications, and the industries which can utilize or which requires these kind of the carbon resources, whether it is the electronic industry or whether it is the agriculture industry, whether it is any other steel industry which has the resources to use either in the form of a biochar or in the form of a liquid or in the form of a solid resources or the heating cooling applications. So in this way we need to have decentralized, then we have to adopt the single or a hybrid thermochemical process for the centralized applications. Then these densified materials, either solid or the liquids, can be shifted to the centralized refineries, so the product can be used or produced at the local applications. That is the mantra, so that the sustainable utilization and the avoiding the supply chain logistics and the scale up merits which has the fossil based refinery will not have here in the case of the bio based, due to the presence of small quantity of the biomass available, small and large areas in India. So this has to be, thermochemical process has to be utilized for the different applications in this way. Use the energy for the irrigation purpose, as it is 60-70% of the rural India agriculture requires the water irrigation pipes and the energy, and then to grow, then the residues has to be converted. So this is one of the applications. Similar way you can produce the biochar, and which is again used for the growth of the agricultural produce, because the food for 1.3 billion population is the most essential critical component compared to the energy or the other requirements. So food is most essential part of this one. So as we have been hearing about the different approaches, I will not go into the details. The thermochemical or the biochemical platforms, these are the two basic things. So in this, I would like to mention that the feedstock characterization is most essential part of any process. Before we begin, we need to understand as per the biomass available at that local quantitative, then design the process, what process has to be done. Then for the reactor development, you need to understand the kinetic parameters, then do the pyrolysis GCMAS to understand what kinds of compounds are produced or possible potential. Then for the value addition or get the most economic benefits, try to separate, try to get those chemicals, then do the lab scale studies, then you understand, then go to the product characterization, then upgrade those products. Then the remaining carbon or in the form of a solid in the biochar or the gases, you need to apply or you give the second life to these kind of a process products. So for the feed, you need the different kinds of analysis or the experimental treatment methods in the laboratory to understand, to strategically design the process, as well as for the products, you need these kind of the essential things. There are several other characterizations which are essential, but with these things, you will get an idea what actually that is required. This is basically I'm trying to address and provide information to the students so that they will not do any fundamental mistakes in carrying out their research or thought process for this. So with this, once you do the simple thermogravimetric analysis, you get huge quantity of the information from the simple technique, that is to apply, that is by applying the mathematical tools and understanding the data. You can get the kinetic parameters, you can get the fixed carbon or the volatiles, moisture, then use this data for the process scale-up too. So you can do this kinetic analysis by using this one, and we have published several number of publications using the different methods and modifying these mathematical treatment to get the required data. So this is one of the typical recent publication data. You can see that a simple sample, you can see that how a conversion from the 10% to the 90%, how the parameters, how the alpha value will change, how the activation energies will change, that you can see from the master plot. You can see that the 10%, 0.1 to 0.4 conversion, how this mechanism is changing, how the mathematical treatment is different at the lower conversions and also at the higher conversions. With this, you can understand design so that you will not have any problems in the heat integration, so that the efficient optimum conditions, optimum load on the required power and the design or the downstream process can be developed. That is what yesterday some of the question is that we are producing. Some people asked that they are getting the maximum wax. So that is the heat integration and the downstream process is not appropriate, so that you will end up in getting such kind of a products. So this is so essential part when we transfer these heat to the non-conductance materials like biomass. So in this journey, we have studied a typical biomass by using the PyGC mass to understand the potential, not to mix the several biomasses at one place or one reactor, so that we can get the maximum functional benefits from this biomass. So we have done using the pyrolysis as well as the HTL, that is hydrothermal liquefaction. Basically, this is the dry process. We have extended for these kind of biomasses, forest residues, oil cake, agricultural residues with high moisture containing, again the hydrothermal liquefaction extended. I will share some of the results and the applications, how complex it is to have the economical incentives and to sustainably implement these models. Theory is okay, pyrolysis is not the new, but how best we understand these pyrolysis methods for the real scale applications and the utilization of these methods. So one of the approaches is to have the mobile units, pyrolysis units, to produce the biochar and use this biochar in the soil itself. It will goes to the field rather than biomass coming to your plant, so that the supply chain management is addressed and the utilization of the product like biochar in the soil itself is benefited, and the heat and power can be generated using the resources at the site itself.
Dr. Bhaskar,
So with this,
excuse me, Dr. Bhaskar, can you please conclude it? We're almost time up for your presentation. Thank you.
Yeah. So now there are several applications for the bio oils which we can apply as the functional chemicals. That oils can be used for the food, fragrance and the paint industries. We have extended these materials for the Ayurvedic applications and the herbal formulations to use for the veterinary products and the oils. These bio oils are part of the Ayurvedic medicines, which is the traditional Indian medicine systems from the plant-based chemicals. So with this, we are trying to use the high moisture biomass materials to produce the chemicals. The lignin, which is coming from the 2G industry, pulp paper industry, basically with the high lignin. These materials, we have produced the different type of the chars, that is pyrochar and hydrochar. and they understood what kind of parameters will influence the properties of the produced biochar, so that the targeted applications can vary from the soil enrichment to the electrochemical applications. So with this, we have extended this char catalyst support for the catalytic applications to produce the high value chemicals by replacing the conventional noble metal catalyst. At the same time, we used these carbon based material catalysts to convert these very high value chemicals. Also used this biochar for the adsorbent for the natural gas, which is very high, 140 centimeter cube per centimeter cube at room temperature with 3.5 megapascal, so that is better. Not only that, we have extended these carbon based materials for the electrolyte for the high density capacitors. Not only that, we have also used for the capacitor electrochemical applications, and we found that very high value specific capacitance for the targeted biomass for the targeted applications for the defense applications. With this pyrolysis concept extended to the plastics, municipal waste plastics and electronic waste plastics, to understand the composition in the different countries, different localities is different. So the technology elsewhere developed may not be suitable for the local applications or the local plastic compositions, as the applications or uses are different. So with these high-end analytical equipment at our laboratory, we are extending these materials and trying to understand, implement these fundamentals. If we don't do our scientific work, someone else would do. But if we neglect our social responsibilities as scientists, there would soon no science. So the PYRO Asia may address to use the waste materials, diverse waste materials, to address the sustainable development goals. Thank you once again.
Thank you, Dr. Bhaskar. Guys, and if you'd like to ask some questions to Dr. Bhaskar, please post questions in the question box, and we will address it at the end of the session. Guys, today there are lots of presentations in line. I will be very strict on the time today. Please understand that. So let's everybody please follow the time so we can manage these, the time schedule today properly. Okay, now the next innovative talk is on the advanced thermal process for the valorization of agricultural residue at distributed scale. This will be given by Professor Abhishek Sharma from Manipal University, Jaipur. Let me quickly introduce Dr. Abhishek Sharma. He is currently as a professor in the Department of Chemical Engineering in Manipal University, Jaipur. He is holding Dr. Ramdas Pai Research Chair position in organization. He has 13 years experience in process engineering, basically on the waste evaluation, alternate energy, and multi-scale processes. He has worked in the process design and development department in Engineers India Limited after completing his bachelor degree, and he has achieved his PhD from Curtin University, Australia. Let's welcome Professor Abhishek Sharma to make a presentation. Let me share the screen. There we go.
Hello, everyone. Are you able to hear me?
Yes. Yes, we're good. Yeah, go ahead.
Okay. Yeah. Can you see my screen?
All good. All good. Go ahead.
All good. Thank you. So, first of all, thank you for inviting me for this session. And I just want to congratulate Mr. Payram as well as Karthikeyan for organizing this event seamlessly in the online mode. And also want to thank the previous two speakers, Professor Bhaskar and Professor Oak, for laying the foundation of my talk and emphasizing on the relevance of converting this waste into useful products. So I'll directly focus on the technology on which I'm working on currently. Just a minute. Okay, so am I visible as well? And my slides are visible too, Param?
Yes, all good, all good.
Okay, thank you. So I'll just tell you of the global scenario first. I mean, there's around 146 billion metric tons of biomass being produced annually. Out of that, around 35% energy contribution of this biomass is there in the developing nations. And the total energy contribution in the world is around 14%, which is significant. But the problem lies in its utilization. So as per the World Bioenergy Association, the challenge is most of the biomass is being used traditionally. So just as a source of heat energy. And modern biomass application, which we are talking right now, is very limited by 2016-17. but it's growing with time. People are coming up with new technologies, as being suggested by Professor Bhaskar too, and Professor Oak for converting. Yes. Hello. Hello. There's some disturbance, Bayram. Should I continue?
Yes, please proceed.
There's some disturbance coming. Okay. So for the technologies, I mean, there are multiple technologies available. We have published some work on that, like, thermochemical conversion and biochemical conversions, like gasification, combustion, pyrolysis, hydrothermal liquefaction, then hydrolysis, fermentation, anaerobic digestion with multiple products like heat energy or maybe syngas, bio-oil, char and fuel gas, then bioethanol as well as biogas. That work has been published in 2015, highly cited work in Renewable and Sustainable Energy Reviews. Then there's some comparative studies have also been carried out by our group. Another review has been published in 2019 in Greenhouse Gases Science and Technology. And it has been seen that the fuel cost in dollars per GGE goes down. You're going to see the trend with respect to selection of technology. And here we have to understand that most of the technologies over here are like gasification at high temperatures and biochemical operations, but they are in this centralized mode. As soon as you integrate gasification with distributed biomass pyrolysis, the overall cost goes down. As you can see this trend. So the reason behind that is, I'll just briefly mention to you that the lower transportation cost. The transportation cost of biomass goes down when you are working at the distributed scale, maybe at 5 to 10 tons per day or 50 tons per day scale, depending on the availability of biomass. Now, the biomass has very low bulk density, like around 150 to 200 kg per meter cube. That's why the transportation cost is very huge when you are transporting for distances more than 50 kilometer radius. So when you have distributed systems, that the cost goes down. Then also the capital and operating cost is lower in case of distributed systems because the downstream processing would be relatively easier. Like, for example, the metal content mainly stay with your biochar, doesn't go with the flue gases as you're going to see in the centralized gasification systems. And the bigger advantage is lesser dependency on the environmental constraint. With time, there is change in the feed quality as well as quantity. So you can't look for a centralized system over here. You have to go with the distributed system. And over there, biomass pyrolysis is very successful as a sustainable solution because the products which you are generating, biogas, can be used back in the system to provide us heat energy. Then the oil can go to biorefinery and for biochemical generation, as being mentioned by previous speaker too, after separation and purification. And biochar found a number of applications, including soil remediation, as a fertilizer value, as well as an adsorbent and catalyst. Now, when you talk about the technologies, there are different technologies available for conversion of biomass to these intermediate products, which will further be upgraded as a useful end product. Those technologies, you're going to see the most favorable one with respect to market attractiveness and technology strength is fluidized bed, circulating fluidized bed, and the auger type of reactor. And depending on your scale of operation, you choose one particular technology. Now, I'll briefly tell you about the necessity of utilizing agricultural residue in the nation. So if you're going to look on the left-hand side, the crude oil in India, which we are generating, is around 41 to 45 million tons. However, our consumption, if you're going to look, is close to 220 to 40 million tons. So we are importing around 196 million tons of this crude oil from outside the nation, which is a significant cost for the nation. Now, if you're going to look on the right-hand side, you're going to see that we produce around 686 million tons of gross crop biomass residue. This is the annual production, out of which around 234 million tons, 35% of the total, is available as surplus for bioenergy generation. The rest is being used for different other applications like cattle fodder and some other heat applications. As you can see, the distribution is like it has good amount of sugarcane residue, followed by rice and the wheat. And then we have cereals, cottons, oilseed pulses there as well. Now, if you're going to talk about this 234 million tons, and if we produce around 30% of oil from this, which is around 60 million tons, it will go back over here. It will reduce the cost which we are paying for importing the crude oil from outside the nation. However, the challenge lies in that agriculture residue production itself. As you're going to see that with time, there is like different crops being harvested. So mustard is primarily harvested in the February and March period, cotton in November and December, rice in March and April. So the problem is, again, as we mentioned earlier, that there are environmental constraints. And for that, the sustainable solution over here is this thermochemical technology, which we are currently working on. So we have developed a process in our lab for treating 50 kg per day of biomass, different type of biomass using that facility, and getting different products like syngases, fuels and chemicals, and char. We are primarily focused on 3 particular residue for this study, like for this particular presentation study, that cotton stalks, mustard husk, and the rice husk. All 3 are pretty easily available in the nearby areas, which you can use. So our intention is like, the farmer should be benefited. Whatever products we generate, some part of it will go back to the soil, and it will help the farmers in improving their productivity, because it has been seen that this char improves the productivity by around 40%. But that depends on the soil in which you are putting back the char which you are producing. So now the feed analysis has been carried out. Rice husk contains very high amount of ash content as compared to mustard husk and cotton stalks. The reason for that is high amount of silica in that. Calorific value is quite good. Carbon content is also quite favorable for converting this biomass into bioenergy. Then we have carried out the thermal analysis, the TJ studies for all the 3 type of feed, and seeing the behavior with respect to temperature and time. So basically at different heating rates and with respect to time, weight loss has been studied and it has been plotted. So as you're going to see, majority of the mass loss is occurring between 250 to 550 degrees Celsius. And that is primarily because of decomposition of cellulose, hemicellulose, and lignin in that range. The same behavior for cotton stalk has been observed. Then the work, as the previous speaker also mentioned, that for scale up, we have to also talk about the kinetics. So kinetic studies has been carried out. Basically, there are 3 zones, as you can see: the drying zone, the active zone, in which the most of the decomposition happens, around 60 to 70% of decomposition happens in this range, and then the passive zone, in which minimal decomposition occurs primarily because of the lignin content available in the biomass. Now the kinetic modeling work has been published. One of the paper is under publication, and another one on plastic has been published recently in the Chemistry Select. The experimental studies have been carried out in that setup, that semi-continuous facility, which is operating at 50 kg per day. This is the overall setup which has been shown. These are the operating conditions which have been maintained inside the reactor. So we have operated between 350 to 550 degrees Celsius. The pressure is atmospheric condition has been maintained, so it will be easier to operate with the decentralized scale. You don't have to provide any compression energy to the system. And the batch feed is around 1 to 5 kg per batch we have processed, particle size around 5 to 20 mm, and heating rate to 20 degrees Celsius per minute. Reaction time we have varied from 60 to 120 minutes and seen its effect on the product quality as well as yield. And the environment we have maintained inert by putting nitrogen in the system. Now the yield, if you're going to notice with respect to temperature, there is decrease in the char yield with increase in temperature from 350 to 550 degrees Celsius. And there's increase in the yield of oil and gas with increase in temperature. So the maximum yield of oil, which is coming around 30%, gas is coming around 40 to 45%, and remaining is char. The same behavior has been observed in cotton stalk and rice husk. Now for the char analysis, we have carried out char studies, and we have seen the calorific value of all the 3 type of char which we are receiving from mustard husk, cotton stalks, and rice husk is very high. It's comparable to coal, so it can also use as a form of energy. However, the focus over here is to use it as a potential fertilizer. So like what has been observed, that with increase in temperature, there is increase in the carbon content and decrease in the oxygen content. The same behavior being seen in other biomasses. And the volatile matter though decreases, because with increase in temperature, more volatile compounds from that char matrix. Now with XRF studies, it has been seen that it contains micronutrients like magnesium is there, potassium is there, calcium is there. And the presence of iron is also there in some biomass, which can be very useful for certain applications, soil applications. Then the FTR studies have been carried out, which confirm the presence of certain functional groups. So these functional groups are primarily because of the silicates, the monosilicates, which are present in rice husk. Then we have some OH groups, which are maybe because of phenolics present in that char matrix. So at higher temperatures, these phenolics will also come out. Then we have also some aromatic compound present in that biochar, and some inorganic components, which is in form of ash, or you can say that particular metallic content, which is available in your biochar. So this study confirms that there are some unconverted material also present in your biochar, which then can further be treated like some at higher temperatures, and those compounds can be retrieved in oil as well as in the gas compounds. Further char analysis has been carried out by SEM and EDEX, and it has been seen that mustard husk has more like a honeycomb structure, for which there are certain applications we are exploring. The rice husk in the cotton stalks, we have seen that there is deformity in the structure of biochar with increase in temperature, because volatiles, when they evolve out, the structure changes. Though it improves the porosity as well as the surface area, but it affects the other morphological properties of the biochar. The same EDEX studies confirm that there is good presence of potassium and calcium in CS and MH, as well as there is very high presence of silica in rice husk. At the same time, the zinc content is also significant, which has been confirmed over here. And there are a lot of zinc deficient soils in India, for which these kind of biomass or biochar are very helpful. Then the oil has been studied using flash point, pour point, acidity, and gross calorific value. Based on that, it has been seen that this oil is not useful as a source of diesel directly, because it has a very high flash point and a very high pour point too. The acidity is also very high. If you're going to compare it with the diesel grade fuel, the gross calorific value is low. This is primarily because of the water content available in the system, which has been confirmed using FTR studies, as well as there are a lot of acids which are coming with the oil, and the high oxygen content also decreases the calorific value of the oil. So direct usage of this oil for or as a fuel is difficult. Now the other application is you have to improve the quality of this oil by using different hydrogen-based processes as well as catalytic cracking, or you just stabilize this oil and use it as a FCC feedstock. The another alternative on which the current focus is extracting chemicals from this particular type of feed. So it has been noticed that all the three biomass contains a good amount of fuels as well as phenols. Good amount of phenols, phenolic compounds have been observed, which is great, more than 10%, and there is significant amount of propionic acid as well. There are other compounds as well, like pyrolytic lignin is there, and some levoglukazan too. So this confirms that there is a significant presence of the value-added chemicals which can be extracted using the advanced separation techniques on which our group is currently focusing on. The char application we have already tried in certain soil, and we have got some very good results, which we are currently converting in form of a patent.
Dr. Abhishek, can you please conclude?
Yeah, I'm just concluding. Thank you, Pyro. So for the scale up, the focus is we are already at TRL 3 and 4. We are going towards TRL 7 and 8. So our next step is to go towards a continuous facility, a continuous reactor, which you already have in our labs now for 5 to 10 kg per hour. We are converting biomass into biochar and bio oil using this continuous facility. And then the next step is to go for process modeling. We have carried out one such study of 100 tons per day using pine wood while I was here in Australia. The similar studies now we are carrying out with our own biomass feed and using our experimental data for 10 to 20 tons per day scale. This is not my work totally. So a lot of support is there from my research team. I have a number of research scholars and research students who I want to thank on this platform. And also my industry collaborators and Government of India, like the DST, Department of Science and Technology, is providing the funding support for carrying out this research. Thank you very much. And if you have any questions, I'm available.
Okay,
Thank
thank you,
you.
Dr. Abhishek Sharma. Excellent presentation. If you have any questions to Dr. Abhishek, please post in the question box, please. Thank you. Okay, let me take over my screen. Okay, now we are into the oral presentation. Okay, guys, all oral presentations, please understand that you have 8 minutes only per each presentation. So please wrap it up as quickly as possible. And okay, the first presentation is on the pristine modified biochar for remediation of potentially toxic elements in soil and soil and water environments by Dr. Ali L. Nagar. Okay, he is a postdoctoral research fellow at the Laboratory of Soil Ecosystem and Global Change, School of Environment and Resources Sciences, based in the Zhejiang A&F University, Zhejiang Province, China. Let me share his screen. Let's Dr. Ali. There you go. Okay, please share the screen.
Yeah, okay. So can you see my screen now?
No. Okay, now yes. Okay, proceed. You got 8 minutes, please.
Okay. Okay. So hello everyone. Thank you for the well-organized event. I will talk about biochar for remediation of potentially toxic elements in soil and water environment. The term potentially toxic elements have been widely used. It's a more comprehensive and at the same time more specific term than other terms such as heavy metal or toxic elements. The source of potentially toxic elements in soil include natural inputs or industrial activity or even agricultural activity. Soil flooding, such as in floodplains or in boggy soils, can also affect the mobilization of potentially toxic elements due to the fluctuation in redox conditions, which may simulate the toxic elements transfer to groundwater, accumulation in plant, and their transfer to human food chain. This may pose a potential environmental risk in wetland ecosystems. Soil potentially toxic elements present in different forms. However, only those stabilized into the soil solution are capable of being absorbed by plants. Actually, it's a simple matter to conceptually classify the potentially toxic elements fractions in soil in terms of the relative availability, including non-potentially mobile fraction or potential mobile fractions or mobile fractions. Immobilization methods have been widely recommended as an eco-friendly and less destructive technique for the remediation of contaminated soils. Those methods involve the application of immobilizing agents into the soil matrix, aiming to transform the soluble toxic elements into the immobile forms, making them unavailable for plant uptake. This figure shows the publications related to organic soil amendments and potentially toxic elements from Scopus, a database. This study was by Professor Yong-Sik Ok and Bhavani among different immobilizing agents such as biosolids, compost, activated carbon, biochar, and in some cases referred to as charcoal, is considered a promising novel material for the remediation of potentially toxic elements contaminated environments. The high porosity, large inner surface area, and the diverse surface functional groups of biochar afford the biochar the potential to improve the remediation of contaminated soils. However, we believe that this scenario will not always work like this. In particular, using inappropriate biochar may even pose more risks by enhancing mobility of potentially toxic elements. In this experiment that I conducted with guidance of Professor Yong-Sik Ok and Professor York Rinkaliba in Wuppertal University, adding different types and rates of biochar to vanadium spiked soil exhibited contrasting effects. we recorded the superiority of wood biochar produced at 250 Celsius degree and applied at 2.5%, followed by that applied at 5% over the other biochar types that even further increased the availability of vanadium in soil. Biochar characterization results demonstrated that the high functionality of LWBs and that of HWB, especially in terms of oxygen-containing functional groups, played an important role in the immobilization of vanadium. So we shouldn't consider the biochar as a simple uniform material that always will function the same behavior in soil. In my study with Professor Yongsik Ok, we studied the effect of different biochar types on the immobilization of potentially toxic elements, such as arsenic, cadmium, lead, and zinc in multi-contaminated soils. We found that the mobilization of potentially toxic elements was mainly governed by the release of dissolved aliphatic and aromatic carbon chloride, sulfur chemistry, etc. In conclusion, biochar showed a limited impact on the remediation in case of multi-contaminated soils, which should be enhanced by the optimization of biochar service properties. So care must be taken when we apply biochar to multi-contaminated soils. This heat map showed us the association between the phytoavailability and potential mobility of the elements and the relevant controlling factors. We can see clearly here how factors such as dissolved aromatic carbon or aliphatic carbon, pH, phosphorus, sulfur, etc. can affect the behavior of potentially toxic elements in biochar treated soil. So therefore, it's still unclear for decision maker and environmental agencies which biochar can be employed in the remediation programs of contaminated soils. So we need to analyze the data of previously well-designed experiments in order to have a better vision. We collected data from 41 bear observations to evaluate the effects of different biochar properties in chromium immobilization. Feedstock type, including wood, agricultural residuals, manure, and sludge, didn't play a crucial role in affecting chromium immobilization, as you can see. Meanwhile, increasing pyrolysis temperature and the application rate enhanced chromium immobilization. In addition, the immobilization efficiency was higher with greater biochar pH. For nickel, we extracted data from 59 bear observations among different studies. Biochar produced from wood and agricultural wastes performed better in reducing nickel availability in the soil, while manure and sewage sludge derived biochar had a minimal effect. As we can see, biochars reduced at pyrolysis temperature ranging from 500 to 700 Celsius degree were more effective for nickel immobilizations. And biochar with high pH were more efficient in immobilizing nickel, while biochar application rate had no effect in the immobilization of nickel in soil. We approached it to meta-analysis to analyzing data collected from multiple and independent studies in order to determine overall trends. So meta-analysis usually provides us with a more accurate estimate of the effect size and increases the generalization of individual study results. As you can see, the application of biochar often decreased the cadmium mobilization, which was good news. Important variables of biochar production conditions that modulated the biochar effects on cadmium immobilization can be clearly observed here in the figure. For instance, we can see that sewage sludge, manure, rice straw biochars induced higher cadmium immobilization. In addition, medium pyrolysis temperature and relatively higher heating rate and lower residence time were preferred production conditions in case of cadmium immobilization in soil by biochar. So the immobilization of cadmium was more significant, as we see in case of urban soils, in particular with coarse or medium soil texture. And as expected, the biochar was more efficient in remediating acidic soils than those alkaline or neutral soils. The mechanisms of immobilization of cadmium following biochar application included several mechanisms such as ion exchange, electrostatic attraction, surface compensation, co-precipitation, etc. However, the main factor that governs the biochar effects in cadmium bioavailability is the induced changes in soil pH following the application of biochar to soil. As we can see here in this linear relationship, when the soil pH increase in biochar treated soil, the cadmium bioavailability decrease. Regarding zinc, the application of biochar also often decreased the cadmium mobilization in soils. Manure biochar exhibited the lowest efficiency for immobilization of zinc. Lower heating rate and residence time for biochar showed better results, and the biochar was more efficient to immobilize zinc in urban and paddy soils. Actually, such studies can provide important insights on factors that affect biochar's efficiency for immobilization of potentially toxic elements in contaminated soils. In this study that I published with Professor Yongsik Ok, the potential of biochar to immobilize potentially toxic elements depends on biochar's chemical and physical properties, which differ based on pyrolysis process and the feedstock used, as we all know, and pre or post modification methods. In this figure, we illustrate different modification processes to achieve different biochar surface and characteristics. So to design biochar with the desirable properties, a suitable feedstock should be selected at first to considering the elemental compositions and properties of the surface of this biochar, and then the pyrolytic conditions should be optimized to obtain a specific biochar with a proper physicochemical and structural modification. I'm going to conclusions. Understanding the immobilization mechanisms of potentially toxic elements by biochar will provide us with insights on which biochar should be applied for each specific case. And this will also help us to fabricate biochar with favorable properties. However, further studies are needed to validate the efficiency and superiority of engineered or designer biochar in terms of remediation of potential toxic elements contaminated environments. Here I am showing a few points as overall conclusions. And thank you very much for your listening, and please don't hesitate to share with me if you have any question or idea via my email or via the chat here. Thank you very much.
Okay, thank you, Dr. Ali. If you have any question, Dr. Ali, please post in the question box. Let me take over my screen. Thank you. Okay, the next presentation is by Ms. Pamani. She's going to talk about the sustainable gasification biochar as a high efficiency absorbent for CO2 capture, a facial method to designer biochar fabrication. And let me brief about her. Currently, she works at the Korea Biochar Research Center at the Korea University, and she's a PhD scholar at the university. Her research mainly focused on the sustainable waste management, CO2 absorption on biochar, and use of biochar for heavy metal immobilization. She has published over 10 articles in LCI index journals. Okay, let's welcome Pawani to make a presentation. Okay, Pawani. Okay, please share the screen, please. Okay. You're on.
Okay, thank you very much. I think you can see my screen now, right?
Yes, go ahead. All good.
Okay. I would like to present on sustainable gasification biochar as a high efficiency absorbent for CO2 capture, a facile method to design a biochar fabrication. Let me move to the introduction. You know that carbon dioxide is the main anthropogenic. Can you see my screen?
Yes, we see your screen. Yes, go ahead.
Okay. You know that carbon dioxide is the main anthropogenic greenhouse gas contributing to global warming, causing negative impacts on global ecosystem. And out of the various anthropogenic sources of carbon dioxide, fossil fuel is the main anthropogenic source. So at present, there is an extensive research interest in development of technologies for capturing and storage of carbon dioxide to address the challenges of global climate change. Even though different adsorbents have been evaluated for CO2 adsorption during recent years, high cost for large-scale production and also ineffectiveness in regeneration have become major challenges in current CO2 adsorbents. So biochar, it seems that it is a bit slow. Biochar is a porous carbonaceous material produced through thermochemical conversion of organic materials in oxygen-depleted conditions, and it is emerging as a cost-effective green adsorbent to maintain environmental quality. At present, modification of biochar using different physicochemical methods has drawn significant interest from scientific community. This could be also used for capturing CO2. So in this study, we focus to assess the effectiveness of KOH activation and the combination of KOH and CO2 activation for enhancing CO2 adsorption capacity of gasification biochar. Let me move to the methodology. Here we produce two types of biochar. One is with 100% wood chips and the other one with a mixture of wood chips and chicken manure. And one portion of this biochar was activated with 1 mKOH at 850 degrees of Celsius for 2 hours. And this KOH, a portion of this KOH activated biochar was further activated with CO2 at the flow rate of 500 milliliter per minute for 1 hour at 850 degrees of Celsius. So here, I will use W for wood chips and WCM for mixture of wood chips and chicken manure, and K for KOH activation and KC for KOH and CO2 activation in my presentation. And this biochar was further characterized for physicochemical properties and CO2 adsorption capacity. Let me move to the results and discussion. If we look at the properties of biochar, you can see that surface area and total pore volume and also microporosity has been significantly increased in both KOH activated and KOH plus CO2 activated biochar. Actually, if we consider wood biochar, it is almost 10 times in KOH activated wood biochar compared to pristine biochar. Even the microporosity has been increased. And here, the formation of different potassium species during KOH activation result in intercalation of potassium into carbon structure of this biochar, and it can widen spaces between carbon layers, enhancing pore volume, and thereby surface area is increased. And also in carbon dioxide activation, carbon dioxide will react with carbon, forming carbon monoxide and widen the increase the porosity. So if we look at the carbon dioxide adsorption isotherms of biochar, you can see almost all activated biochar showed significantly high CO2 adsorption capacity compared to pristine biochar, corresponding to high surface area and porosity. And also this WCMK, which is the biochar produced with wood and chicken manure and activated with KOH, showed the highest CO2 adsorption capacity, that is 2.9 moles per kilogram, corresponding to highest surface area and porosity. If we look at the two pristine biochar, that is wood biochar and wood and chicken manure biochar, we can see that wood and chicken manure biochar had high surface area and porosity compared to wood biochar. Irrespective of this high surface area and porosity, this wood and chicken manure biochar showed low CO2 absorption capacity compared to wood biochar. If we look at HC and OC ratios, we can identify that wood and chicken manure biochar had high HC and OC ratios, indicating that it has more hydrophilic characteristics. So this may be the reason for low CO2 absorption capacity in wood and chicken manure biochar, because this previous studies have found that CO2 absorption can decrease under humid condition due to high affinity for water, and therefore this hydrophobic and non-polar characteristics of biochar may exhibit better absorption capacity. If we look at gravimetric CO2 absorption of biochar, you can see that all biochar achieved more than 70% of their maximum absorption capacity within 10 minutes, demonstrating that all this biochar performed rapid absorption. And the biochar which showed highest CO2 absorption capacity was assessed for recyclability. We found that both of these biochar maintain more than 99% of their maximum absorption capacity up to 10 consecutive adsorption-desorption cycles, indicating that both of these biochar can be easily regenerated. So I would like to conclude my presentation with the conclusions that engineered biochar exhibit high CO2 absorption compared to pristine biochar, and modification of biochar with KOH is a more effective method for enhancing CO2 absorption, and higher surface area and microporosity greatly influence the CO2 absorption capacity of biochar. In addition, hydrophobicity and aromaticity of biochar also have significant influence on CO2 absorption. In engineered biochar exhibit rapid absorption and excellent regeneration ability. So this concludes my presentation. So this study was recently published in Renewable and Sustainable Energy Reviews, and this study was conducted with the collaboration of Korea University, National University of Singapore, and Hong Kong Polytechnic University. Finally, I would like to invite all of you for Nature Conference, which will be held on from 26 to 28 of October next year at Korea University. This is on waste management of valorization for a sustainable future, and this will be held with the EIC of Nature Sustainability, Nature Nanotechnology, and Nature Electronics, and together with a senior editor of Nature Sustainability, together with Professor Yang Sik Wo, will be served as a scientific organizing committee. So you can have more details using this website. And thank you very much for your attention.
Thank you, Pavani. I appreciate the presentation. Guys, if you'd like to have any questions to Pavani, please post in the question box. Let me take over the screen. Okay. Okay, the next presentation is on the kinetic modeling of raw and torrefied coal and duckweed blended feedstocks for co-pyrolysis by Pyrolysis method. It will be presented by Munmi Bhattacharya. Okay, let me welcome Munmi to share the screen.
Is it audible? Is it visible, sir?
Yes, the presentation is okay. Yes.
Okay, sir.
You want to share a webcam as well?
Yeah. I can't see my slides. I can't see my slides.
Yeah, we see your slides. Okay, can you put a display settings?
Okay. Am I audible?
Yes, please go ahead.
Hello.
Please go ahead. Yes.
Okay, sir. Good afternoon to everyone present here. My topic of presentation is kinetic modeling of raw and torrefied coal and ductile blended feedstocks for co-pyrolysis by Broido method.
We lost your voice. We can't hear you, Munmi. We lost your voice. Okay, we back to your presentation again. Okay, after finishing other presentation, if you don't mind, so that we can continue other presentations first. Yeah, is it all right? Okay, guys, I need to save the time, so I'd like to take over the screen and move to the next presentation. In the meantime, Munmi, you please check your the speakers. Okay. I hope that Dr. Anrita is online. Okay, the next presentation is on the effect of banana peel biochar on the growth performance of water spinach. Okay, let's welcome Dr. Anirita to make a presentation. And currently, she received her bachelor degree in civil engineering from University Technology Malaysia in 2016, and PhD in fuels and sustainability from Nottingham University, Malaysia in 2013. Currently, she's working as assistant professor in the Department of Chemical and Environmental Engineering, Faculty of Science at Nottingham University, Malaysia. Let's welcome Dr. Anita to make a presentation. Let me take a screen for you. Okay.
Good afternoon, Dr. Param. Can you see my screen and can you hear me?
Yes. Would you like to share your webcam, or you don't want to?
I can, but I just worry the internet connection. It might be, lag down.
Okay, fine. Just go with presentation. Go ahead.
Okay, all right. So very good afternoon to everyone present here. Today I'll be presenting on the effect of banana peels biochar on the growth performance of water spinach. So I am Anurita Selvaraju from Department of Chemical and Environmental Engineering from the Faculty of Science and Engineering, Nottingham University, Malaysia campus. So I have divided my presentation into introduction, methodology, results and discussion, and are finally followed by conclusions. So all of us know that biochar has a lot of benefits, and one of the main benefits when it is being applied to the soil is eventually it can decrease the nutrient runoff, it can increase the soil carbon, it can also improve the soil fertility. So with that, it can be eventually applied as a fertilizer in the soil, and it has shown to have positive effects on the crop growth. So looking at the research that we have been conducting, we realized that in Malaysia itself, we have a lot of bananas that are being produced in Malaysia. So for example, in year 2017, almost 35,000 hectares have been planted with bananas, and we have a production of around 350,000 metric tons. So this actually accounted for around 24% of Malaysia's total food production in year 2017. So when we have a lot of production of bananas, we can also say that we have a lot of waste that is being produced from the bananas as well. So we know that from the banana we have waste that are involved, which are pseudostems, and also the rejected fruits and the peels. So since large quantity of banana peels are available, it represents not only significant disposal problem, but it is also a tremendous waste of resources. So what we intend to do is eventually to upgrade this particular banana peels to convert into biochar, so that it can be eventually used as a valuable product and see how it can affect the growth of the water spinach. At the same time, we want to actually reduce the environmental pollution, because most of the time the banana peels are ending up in the landfill, and it also causes greenhouse emission effect as well, especially the methane production when it is being decayed. So the aims and the objective of our research was eventually to evaluate the biochar from the pyrolysis process and to explore the soil conditioning potential abilities to increase the crop growth. So the targeted crop for this particular research was eventually water spinach. The objective of the research was eventually to convert the banana peels to biochar through slow pyrolysis process. Secondly, to analyze the biomass and their respective biochar on their physico-chemical characteristic. And finally, the objective was to determine the best biochar concentration for optimum water spinach growth. So for this experiment, we eventually collected the banana peels from a banana stall that sells banana fritters. Okay, so the air-dried peels are eventually ground into 1 to 2 mm. So they were actually sieved and they were sent to a pyrolysis reactor in a tubular furnace. So the pyrolysis experiments was eventually conducted in the tubular furnace to produce biochar. So the biochar that is being produced after the pyrolysis were eventually applied in the pot together with the soil to eventually see what is the growth of the water spinach. So from the pyrolysis experiment, we eventually vary the temperature, the residence time or the dwelling time, and also the heating rate. So to eventually see what is the optimum yield that can be actually obtained from these particular parameters. So the temperature selected was around 200 to 700 degrees Celsius, and the residence time was around 30 minutes to 120 minutes. And finally, the heating rate was around 5 degrees per minute to 20 degrees per minute. So this range was eventually fed into a design of experiment, response surface methodology, to eventually get the best operating parameters. So from the experiment, we eventually got biochar at a temperature of 400 degrees and a residence time of 120 minutes and a heating rate of 18.4 degree Celsius per minute that will be eventually used to see the growth of the water spinach. So from this response surface methodology, we eventually get the 3D plot of the biochar yield together with the to see the effect of the temperature and also the residence time. So what we can eventually see is the biochar yield can be increased with lower temperature. So when it's higher temperature, definitely the biochar yield will be eventually decreasing. And a longer residence time produce higher char yield during the pyrolysis process. So at this particular temperature, we eventually got a char yield of 48.4% with an oxygen to carbon ratio of around 0.276. So the optimum biochar that was chosen for the crop growth applications are from biochar of 400 degrees Celsius, residence time of 120 minutes, and also a heating rate of 18.4 degrees Celsius per minute. Let me just move into the results from the application of biochar onto the soil. So what we can eventually see over here is we actually monitor the plant growth or the plant length over around 40 days. So we eventually can see the sample with 1% weight of biochar, it improved the growth of the length of the plant by around 42 centimeter compared to the control, which managed to reach only a mean length of 31.46 centimeter. So we also can notice that a concentration of more than 1, which is around 3% and 5%, actually have a negative growth. It doesn't really reach the optimum growth that the biochar of 1% weight resulted. So that was on the plant length. Secondly, we were eventually looking into the number of leaf that is being monitored with the biochar concentration. Again, similarly, what we realized was we eventually managed to get 1% weight biochar, actually managed to get the match the control numbers of leaf with a mean of 12.6 leaves, and the concentration of biochar, which is more than 3%, is eventually having a negative growth. So for both the results that we got, we can eventually say that small concentration of biochar is eventually enough to increase the crop growth rate, and the yield are considered more compared to 3% or 5% of weight. So we only need a small application or small concentration that we need to eventually put in the soil to get a better yield. So from the research, we can eventually conclude that the operating conditions that are needed for the banana peels are eventually 400 degrees Celsius and the holding time of 120 minutes and a heating rate of 18.4 degrees Celsius per minute. So this was eventually chosen to produce the biochar to be used for the water spinach growth. So at this operating condition, we have a very good yield of biochar, which amounted around 48.4%, and it also gives a oxygen to carbon ratio of 0.276, which we can say it improves the stability of the biochar when it is being applied to the soil. So in the water spinach experimentals growth, it shows that the banana peels biochar of 1% is eventually enough to improve the plant growth significantly. So with that, I conclude my presentation. Thank you very much.
Thank you, Dr. Aniruddha. Okay, if you have any question to Aniruddha, you please post in the question box. We'll take care of it in the question session. Let me take over the screen. Okay, I didn't see this gentleman, Francis Prashant, is not on in the list in the logged in, so I'm going to skip this presentation. If he comes, if we have time, we take out later. Next presentation is on the biomass modeling of the biomass fast pyrolysis using the single particle scale by Vikram Reddy. Vikram Reddy, he is the third-year undergrad student in the Department of Chemical Engineering, National Institute of Technology, Calicut in India. Let me share his screen to him. Okay, there we go. Okay, please share the screen. Yes. Okay, you're on.
Yes, sir. Good morning, sir. Is my screen visible?
Yes, I can hear. We can hear you. Please go ahead.
Yeah, thank you, sir.
Presentation mode, please. Yeah. Okay.
Yeah. Good morning, everyone. I'm a moderator, panelist, and all the participants. I, Deputy GC Vikram Reddy, third-year undergraduate student with Dr. Pannisaram Raghunathan from National Institute of Technology, Calicut, Kozhikode, Kerala, India. We present you the works on modeling of biomass fast pyrolysis using single particle scale. As we know, biomass fast pyrolysis is one of the renewable energy processes to obtain liquid fuels from the biomass feedstock, and processes involves thermodegradation in the absence of air or oxygen. So, since the pyrolysis is the first step in the thermochemical process to obtain the liquid fuels, it is necessary to understand the underlying physics involved in the fast pyrolysis. For this reason, different mathematical models have been developed for modeling of biomass pyrolysis. As you can see here, we have biomass particle kinetic model. After that, we will be developing hydrodynamics modeling, and we will combining particle model as well as hydrodynamics modeling to integrate in the reactor model. So, in this study, a comprehensive mathematical model is developed for fast pyrolysis of single biomass particle based on the resolution of mass and energy conservative equations coupled with chemical kinetics. Numerical results are compared with the published experimental data of Park et al. So here are some assumptions we took. One-dimensional time-dependent domain for biomass particle. Inside the particle, local thermal equilibrium, that is no temperature gradient is present between the vapor and solid phases. The particle geometry can be considered as spherical, cylindrical, or slab. The volatile or gas phase is assumed to follow ideal gas condition. Particle shape did not change during the degradation process. That cracking or fragmentation is not considered. The momentum transport in the particle phase is governed by Darcy's law. So the biomass drying. Biomass drying is an important phenomenon and governs both mass and heat transfer rates inside the particle during pyrolysis. In literature, there are several types of models studied, including the heat flux model, the equilibrium model, and the chemical reaction model for the calculating biomass drying rate. In this study, chemical reaction rate based model was used and can be written as the equation provided below. Here, the A and script EBA, which is a pre-exponential factor, was taken as 5.13 in 10 power 10 second inverse, and E, that is activation energy, is taken as 88 kilojoule per mole. This is taken from the literature. Biomass shrinkage. Particle shrinkage is physical phenomenon during biomass degradation mechanism and can be modeled as shrinking per mole. It is assumed to be equal to the fraction of solid which got devolatilized, that is total particle volume is to be the function of biomass, moisture, and charge. Therefore, the change in volume of particle during decomposition can be written as the equation provided, where V0 and Vf stand for the initial and final state of biomass volume. MB, MM, and MC are the mass of biomass, moisture, and biochar respectively at the same time. Here, kinetic model. The reaction scheme and the kinetic parameters are given below for different reaction steps involved. Biomass reactant decomposed into gas, primary tar, and char with kinetic constants K1, K2, and K3 based on the literature studies. These reactions are found to be the first order in nature. The primary tar in general will be a mixture of oxygenated hydrocarbon compounds which further undergo chemical reaction at higher temperature, lead to the formation of gases. Components and secondary tar with the reaction constant of K4 and K5 respectively. The secondary tar undergoes heterogeneous reaction to produce the char at the higher temperature with kinetic constant K6. So here some governing equations which were used during the study. There's different governing equations for solid phase as well as vapor phase, and here some of the overall gas phase continuity equation, overall energy balance, and Darcy's law, which were considered during this work. And here some of the initial conditions which were considered, as well as boundary conditions which were considered during the work. And here are the physical and chemical properties of the fluid we took. And the heat and mass transfer coefficients which were developed from the literature papers. And solution methods. The momentum, mass, and heat balance equations were solved with the partial differential equation solver in the MATLAB PDE. The solver converts PDEs to ODEs and uses a second order accurate spatial discretization. The time integration of ODE is completely using differential algebraic solver of MATLAB for given time step. So let me go on to the results. So here the biomass mass fraction. This figure shows a comparison plot of biomass mass fraction obtained between the present model and the experiment data of Park et al. This simulation is performed for dry spherical biomass particle with size of 25.4 mm at a temperature of 400 degrees centigrade. The heat and mass transfer parameters considered based on literature are 20 watt per meter Kelvin and 1 into 10 power minus 4 meter per second respectively. It is found that results are quite satisfactory with experimental data, but there are some deviations in mass loss profile. This may be due to the fact that the present model did not account the particle shrinkage effect properly. Also, it is found that decrease in mass fraction of the biomass is negligible during the initial period of conversion, but after around 200 seconds, the rate of mass loss tends to reach to a constant value of around 20%. Temperature profiles in this figure, the temperature profile of the spherical particle in air with temperature of 400 degrees. It is found that temperature at the outer surface of biomass particle increases with the time, tending to reach a constant value at around 670 degrees centigrade, whereas the temperature at the center of the particle shows the 3 stages. For the first 50 seconds, the drying is dominant and the temperature remains constant at 300 degrees. When the drying is finished, the dry particle is heated up to 500 degrees and pyrolysis starts slowly. After another 300 seconds, the temperature tends to a constant value of 600 degrees due to the charge combustion. This behavior matches with the previous finding in the report. This figure shows the spatial distribution of temperature along the particle half thickness for different times. It can be seen from the figure that the temperature increases along the particle position. Also, it is found that the spatial distribution of temperature increases with increasing time as expected. Here, the effect of reactor temperature. The influence of reactor temperature in the range of 400 to 600 degrees centigrade on biomass mass conversion for a spherical particle size of 25.4 mm is investigated. The results are shown here. The adequate agreement is observed between experimental and present model in the range, but there deviation in mass loss profile with decreasing temperature. The deviation at lower temperature may be due to the incapability of the model to predict the devolatilization kinetics, which was mainly due to uncertainties in the value of activation energies and heat of reaction. A similar trend was also reported in the literature. Effect of particle shrinking. This figure shows the effect of particle shrinking on the biomass conversion rate, the operating temperature, and diameter of the spherical particle are fixed at 600 degrees and 25.4 mm respectively. The heat and mass transfer parameters were considered as 220 watt per meter Kelvin and 1 into 10 power minus 4 meter per second respectively. It is found from the figure that the influence of mass conversion is negligible. This may be due to the fact that the inability of the present particle shrinkage model on the prediction of biomass conversion rate. However, there is a slight variation on the rate of decomposition at longer time. This may be due to the fact that volumetric particle shrinkage favors the higher rate of heat transfer, which leads to the faster decomposition of the particle. So here are some conclusions. The pyrolysis kinetics were implemented based on lump kinetic model proposed by the literature. The result on biomass loss fraction profile from the present model was compared with the report experiment data, and adequate agreement was found between the present model and experimental data. The validated model was further extended to study the effect of temperature and particle shrinkage on a fraction of mass loss profile. However, the present model needs to be extended to investigate the effect of various drying and particle shrinkage models under different operating conditions for better prediction of biomass loss fraction. So at last, I'd like to acknowledge the faculty, PhD scholars, and lab staff of Department of Chemical Engineering, National Institute of Technology, Calicut, Kozhikode, Kerala, India, and all other who directly or indirectly provided me constant support for my completing my work. And these are some references I took. And at last, thank you very much.
Okay, thank you, Venkat Reddy. If you have any questions to Venkat Reddy, please post in the question box. Munmi, are you ready? I'm just going to ask you to share the screen quickly. Okay, go on. We cannot hear you. I'm sorry, we can't hear you. Hello. Munmi, I have no choice, but I would like to move your session to the your presentation to the last part of into third session today. As part of the oral presentation. Okay, yeah, session 9. I will move your presentation to session 9. Okay, sorry. Thank you for understanding. Okay, let me take over the screen. We'll have a quick Q&A session. I have questions for the professor. Okay, just a second. Let me put. I'm not going to read for you, sir. Quickly, answer one by one, if you don't mind.
Can you hear me?
Yes, please. Yes.
Yeah. Thank you for the question. For the first question for the biochar cost, I can say currently it depends on the country, but for my country, currently biochar is quite commercialized, mainly by two big company. And currently it's commercially available is 10 kg, 20 USD, but the price is currently cut to half. It's roughly 10 US dollar per 50 liter bag. It's volume based. So, however, this price is for using biochar as soil amendment. But if you're going to use the biochar for water treatment, probably upon your strategy, density of the particle might be important. So price can be slightly decreased or even increased if you need any engineering approach. And I can send you my recent paper that will deal with price of the biochar. Okay. And biochar industry, as I mentioned, in Korea, we have, for example, one major company, that's the #1 energy company in Korea, produce 1 million bag of biochar, but one bag is 50 liter bag. It's a big bag. It produce 1 million. We have another company also produce 800,000. It's 0.8 million bag per year. So roughly, including other companies, should be at least 2 million or 3 million bag. And as I mentioned, the one bag is 50 liter, 50 liter. And current price is roughly $8 US to $24 US upon the company. And we recently, to prepare for the IPCC, the IBI, International Biochar Initiative, and key members recently wrote a comprehensive review that just submitted to Environmental Science and Technology. Otherwise, if you wonder for biochar industry or biochar and circular economy in Singapore, you can see the newest article published at the Science of the Total Environment. You could search with my name, but that work is initiated by Professor Chi-Hwa Wang at National University of Singapore. He succeeded to commercialize the biochar and try to make it to be commercialized. And a lot of information are included there. Yeah. As far as I know, the farmer like to use biochar as fertilizer, particularly as an organic fertilizer. But limitation could be possible contaminant in there. For instance, some commercial product contain relatively high amount of PAH, is polycyclic aromatic hydrocarbon, which is carcinogenic. Though we don't have regulation upon certain country, that needed to be very carefully monitored. So I think PAH concentration can be one of the limitations for using the biochar. But farmers also will consider what feedstock you've been using to produce biochar, and more importantly, the density. If it's too fine powder, it occurs a lot of dust. So density and particle formula is two very important aspects while we are commercializing this material for soil application as fertilizer. Yeah, I think the carbon adsorbent developed from biochar, just Pavani, who is doing PhD with me, just presented her topic for using biochar adsorbent, especially for gas option separation for CO2 sorption. We can use it but for gas option separation, biochar still needed to be further activated, so it could be converted into porous carbon. As you know, the porous carbon having higher specific surface area might be better to capture the CO2. Okay, and last question comes from my colleague. So,
Dr. Bhaskar.
Yeah, I know. So, I mean, he's expert on the topic. So, your question might be the most difficult question among ours. I'm just thinking.
Okay,
so,
yeah.
I think that could be extended to the e-waste, I guess. But it depends on day before yesterday, there was one Japanese, the postdoc fellow made a very good presentation. But it depends on whether the e-waste containing any polymer or plastics. Definitely co-pyrolysis can be adopted. But if we talk about the e-waste wholly containing certain metals, I don't think it's possible for us to do pyrolysis. So it depends on what e-waste we are dealing with. It's case specific in my opinion, but that really a good aspect. We need a lot of research on the topic. As far as I know, there's not that much research going on the issue. Thank you very much.
Thank you. Dr. Bhaskar, would you like to add anything?
Yeah, I agree with Professor Oak, and the economic feasibility and the comment on the revenue. So it is difficult to generalize. Yes, I agree that there is a possibility to get the economic incentives. Absolutely, there is no doubt, because Professor Oak also mentioned that the cost for the biochar is also from $8 to the $24. In case of in India also, we have around 20 rupees, around 25 rupees per kilogram for the best biochar is being marketed in Karnataka and Maharashtra already, and the high value applications are being exploited. When it comes to the energy point of environmental point of view, nobody has properly calculated those numbers. Otherwise, there are several advantages and environmental benefits which needs to be considered when calculating the economics.
Okay, let's okay. Professor Dr. Abhishek Sharma.
Yeah, can you hear me?
Yes.
Yeah, so I think there is a caution is about the correlation between temperature and heating rate, and yes, it does exist. The heating rate in which we are operating at is around 20 degrees Celsius per minute, but when we change it, it will affect the temperature of the system for a given reaction time, because it's a semi-continuous facility. But in case of the continuous facility on which we are now scaling up, as I mentioned in my talk, that 5 to 10 kg per hour of scale, then we are going with isothermal conditions, and there won't be much effect of heating rate on the conversion at that time, because the particle will reach the reactor at the time when reactor is already being at that desired temperature condition. So the correlation is there, and the same studies have been carried out, in fact, using TGA. A lot of such studies have been published. I think the person can look in the literature by our group as well as by Professor Bhaskar's groups too, and Professor Oak, I'm sure, must have published in that area. So how to use that temperature and heating rate correlation to extract the kinetics also. That is a very interesting study which you can look for.
Okay, thank you, Dr. Abhishek Sharma. Nrita, would like next question, please? Anirita, are you going to answer it?
Oh, sorry.
Yeah.
There's a question regarding the moisture content of banana peels. So if we eventually did approximate analysis for the banana peels, it's just I never report just now. So from the result that we got, the moisture content of the banana peels was around 80%. I mean the fresh biomass banana peels. But after it was turned into char, the moisture content eventually, once it is air dried before we put into the pyrolysis experiment, the moisture content was around 8%. So through the air drying, eventually the moisture content was reduced from around 80% to eventually 8%. So 8% was the moisture content of air dried banana peels before the pyrolysis experiment. There's another question for me as well. Can I just continue with that?
Yes, go ahead.
Okay, so there's a question on what happened to the plant length after 40 days with concentration of biochar. So eventually we never monitor after 40 days because the water spinach is fully grown and it can be harvested. So eventually we harvested the plant after 40 days. So we never really looked into the plant growth beyond 40 days. So I think that answers the questions. Thank you.
Okay, Pavani, give us now. Pavani, are you there?
Yes.
Okay, go on.
Yeah. Can you hear me?
Yes, go ahead.
Yeah. Actually, my question is the BET surface area in tune 1,400 will affect actual. You know that if there is micropores, it is better for absorption of CO2, especially when the pore size is less than 0.8 nanometer. But actually, in together with there is high surface area, it facilitates absorption because there is more area for absorption.
Okay.
So it will. If there is, it is better if there is more surface area as well as more micropores.
Okay, thank you, Pavani. Guys, there are two more presentations which are supposed to have, happen this session. There are some difficulties. What we do is that we are going to put these two missing presentations to the last session. Okay, please, both Prashant and Munni will do your presentations in the last session. Okay, and I'd like to invite. There are lots of questions are there, and I will pass these questions to the speakers, so they will answer to you directly, because there is a time factor today. Please understand that. Now let me ask Professor Ji Feng to give final remarks on this session. Professor Ji Feng, you need to. Okay, yes, go ahead, sir.
Yeah. Okay. Can you hear me?
Yes, please.
Okay. Thank you, all speakers. Especially thank you for Professor Yung. So you did a lot of work on this section. I think this section is about biochar and advanced materials. So a lot of work focused on biochar, but we need to think about in the future from biomass to biochar and to advanced materials. Maybe we need to do more efforts to promote our future. So I think some guys they did like this biochar as a catalysis supporters or capacitors. So that's a good effort to promote our research level. So we hope, especially in Asian area, we need to put together to think about the future of the biochar from pyrolysis of biomass. Of course, another question is about how to commercialize the biochar or the total biomass from biomass to biochar and advanced materials. Of course, advanced materials, that is especially carbon materials. These carbon materials maybe can produce from biochar like some polymers, some rubbers. So the method, the way is the same. Maybe we can have some method from another area to promote our biomass pyrolysis this area. So we hope we need to make a connection further. So I think today's this section by Shah, there's some younger scientists here. Maybe like Professor Yung, maybe you can give some suggestions for these scientists.
Yep. Thank you very much for the kind suggestion. So could you kindly explain specifically for what you're asking? I didn't exactly catch for what you're meaning. You mean you asked for me to give advice for young scientists, but in terms of this biochar research, or what was your exact question? Hello?
Professor Jifeng, can you? Yes. Yeah.
Okay. Sorry. Maybe some problem with my phone. So, Professor Yung, because you are a high valuable professor in Bashar this area, so because in this section we have some younger scientists. They did research on biochar from biomass. Maybe you can give them some suggestions to how to do their research in the future and how to get their.
Yeah, so thank you very much. As I briefly mentioned, this biochar is, I would say, biochar is not a material. So I don't ask you for you to consider biochar as material. So it is a non-material, but it's a system deal with global carbon cycle. So we can consider biochar as part of soil. As you know, the soil composed with colloid, oxide minerals, air and water, and organic matter. So biochar is going back to, geoscience or soil science. This is the material, comes from the soil, so comes from the nature. So if you're familiar with the term biomimetics, we produce biochar to mimic the soil organic matter. Soil has a function. It can do air filtration, purification, capture the carbon. Soil is our base of our life. In the same way, this biochar has multifunctional material. So it can capture CO2, it can capture contaminant, it can be used for water filtration, even it can be used for supercapacitor, catalyst, and so on. There are a lot of future application in the field of biochar, and this research during the past decade is a bit mature in the field of using biochar for soil application. But there will be a lot more application using biochar building and construction material, gas option separation, as a catalyst. There will be many other applications will be possible, such as 3D printing as filler material. So I really hope for you to get an interest for the biochar, looking for its multifunctionality. When you think about multifunctionality, think about biochar as part of nature, is part of the soil. Thank you.
Okay, thank you all. Thank you, Professor Jifeng, and also thank all the speakers and also the oral presenters. Thank you for making this presentation is good. Let's conclude this session here, and we will be starting this session in next session in 5 minutes time. I need to manage my time, so we just take 5 minutes break and we start immediately. Okay, yeah, thank you.
Thank you. Thank you.
Munmi, can you hear me?
Hello, sir.
Okay.
Is it audible right now?
It's audible, yes. Okay. Okay, let's quickly check. I'll view your presentation in the last session. Yeah, is it all right? Yeah.
Yes, sir. Fine, sir. Yes,
Let
sir.
me quickly test it. Okay, your okay. One more time. Yeah.
Is it visible?
Yeah, it's visible. Okay, can you put presentation mode, please, quickly? Okay. Okay, can you move the slides forward?
Yeah.
Can you
Is
see
it
your
visible?
slides now? Yeah, it is visible. Can you move the slides? Okay, you see your slides? Yeah.
Yes, sir. I see the slides.
Okay.
There was a problem with the speakers of the laptop, so
Okay, fine. Okay, we do it in a last session. Okay. Yeah, now we're good. Yeah. Okay. Yeah. Thank you.
okay, sir. Okay, sir. Thank you, sir.
Prashant, I didn't see you, Prashant, in the list. Can you log in as a panelist? You have a panelist link, right, Prashant? Francis Prashant. Francis Prashant, if you hear me, please log in as panelist. You have a link as a panelist. Please use that link as a panelist so that you can hear me, you can share the screen. Okay, Professor Kim is here. Okay.
Nice to meet you, Dr. Bing Wu. Can you hear my voice?
Hello, hi, nice to meet you too.
Okay. Okay.
Hello.
Hi, Bing.
Oh,
Hi.
Long time no see.
How are you? Yeah,
I'm
long
good.
time no
I'm good.
see.
And you?
I'm good. Really hope we can meet in person.
Yes, yes.
Yeah, I hope next time for the third Pyro Asia conference we can actually meet somewhere in Asia.
Yes, yes, yes.
Is it an annual conference or a biannual conference?
Not annual. I'm not sure. It's not decided yet.
Yeah, I understand it, considering the current pandemic.
Yes, yes. But the international pilot conference will be postponed, right?
Yeah, I know that is. Yeah.
So anyway, I'm looking forward to your lecture. Thank you very much for accepting the
Yeah, it's my
invitation.
pleasure.
Thank you.
excuse me, this presentation is coordinated by Kumagai sensei?
No, Professor Kim, you are coordinator.
Who invite? So I heard you make this kind of special section from elsewhere. So
Yes,
I want to introduce.
Yes, I invited Bing from Elsevier, but the Q&A session should be a normal Q&A session. So Peram collect questions from the audiences, and Bing or other editors can answer to the questions from the audience.
Okay.
Okay. If audience don't have the questions, then you know, the other panelists could also ask questions together. Yeah, is all right?
Yep.
Also, when
Okay.
Professor Kim also shoot the question to Dr. Bing. Yeah.
I'll try. Okay. Can you give me a brief time information for section 8?
Okay, I'm going to start it. Just show you. Okay, here you go.
Okay.
Yeah. See, the Bing's presentation is 20 minutes altogether. Okay, and we go for a 15 minutes Q&A. Yeah, and then we go for the oral presentation. Yeah.
Okay. Okay. Thank you so much.
Okay. I think we get started. Okay, guys. I hope you have some coffee. At least have a chance to go to toilet. Yeah. Welcome back, all of you. Now we are in the session 8. Okay, and this is focusing for the people who like to publish in articles in the international journals. It's a session with the journal editors and the panel discussion. And this session is chaired by the Dr. Young Min Kim. I think yesterday I introduced you the first day. Okay, and he's a professor at Daegu University. So Professor Young Min Kim, it's all yours now. Okay, and this is a schedule. Yeah.
Okay, thank you everyone. I am Young Min Kim from Daegu University. As you know, many scientists make the new idea and make the result by cooperating with colleagues and want to publish in many papers. So these papers provide the required knowledge in the related fields. So this knowledge not only broadens the boundary of knowledge, but also play an important role in determining the direction of government and humanity. So in this aspect, the publication of paper can be thought as one of our important responsibility. So this section is specially designed to give the proper solution on how to coordinate, write, and submit your manuscript for more successful publication of your manuscript. So this section was suggested by Professor Kumagai, and I highly appreciate to him instead of all of the participants of this conference first. This section will be started with the guest lecturer, Dr. Bing Wu. The Dr. Bing Wu from LSB Beijing. So after his guest lecture, Q&A time is allowed to us. So during the Q&A time, many editors of the journal related with analytical and applied pyrolysis. So their name is Dr. Bing Wu and Professor Hazmi Otani and Tuarada Bastar, Soho Kumagai, and Binu. So if you have any question for journal publication, please feel free to upload your question. So after this time, six kind of short presentation will be presented by many researchers. So also Q&A will be performed after all presentation together. So let's invite Dr. Bing Wu with the Param's short introduction for this great guest editors.
Okay. As you see that she works for Elsevier. It's one of the famous international journal publishers, and she had main responsibilities managing the portfolio of journals in the field of analytical chemistry and sensors. Dr. Bing Hu, she holds a PhD in chemistry from Brandeis University. Before joining Elsevier, she was a scientific review editor at the Journal of Visualized Experiments in Cambridge, Massachusetts, in USA. So let's welcome Dr. Wu to make interesting presentation on how to be publish papers successfully in their journals. Let me share the screen. Okay, there I go. Can you click
Thanks for introduction. I haven't received the invitation yet.
I did.
Okay, now I see.
Okay, it's on. Yes.
Okay, thank you. Thanks everyone. Good afternoon, everyone. First, I would like to thank Professor Shugo Kumagai for inviting me to this Pyro Asia conference. It is my honor to have this opportunity to meet you virtually. Before I jump into our topic today, I would like to briefly talk about the origin of scientific publishing. The origins of journal publishing, as we know, trace their roots over 300 years ago. With the invention of Mughal type of Gutenberg in the mid-ages, the ability to create multiple bulky copies of literature was possible. Religious manuscripts were the first types of document to be copied. Elsewhere was a Dutch family that sold and published books. Our current company, Elsewhere, is not a direct descendant of this family, but our company took their name in honor as we began our business in late 19th century. Journal publishing, as we know, was first occurred in 1665. The Royal Society of UK saw the need to record the findings and the transactions of their scientific discoveries. Henry Oldenburg was appointed secretary to the Royal Society in 1663, and he began the practice of sending manuscripts to experts who can judge their quality before publication. So peer review was created. He then took the initiative to edit the first issue of his philosophical transaction of the Royal Society, which is considered the first scholar journal. The current system of scientific, technical, and medical publishing has evolved over hundreds of years and serves science and medical global community. Industry is highly competitive. Over 2,000 organizations annually publish more than 230,000 peer-reviewed journals and 1.4 million articles from 7.8 million researchers worldwide. ScienceDirect is Elsewhere's information solution library for researchers. It offers full text content powered by smart functionality and machine learning tools that dynamically generate topics, summaries, and recommendations to the user. So now let's move on to our topic today, how to publish in a scientific journal. What step you need to take to successfully publish? This is a really good question, and there's no straightforward answer to it. But if you would like to write a truly terrible journal article, I have some really good tips for you. So you could refuse to read the previous literature and take the lazy route to plagiarize, omit key article components, and disrespect previous publication and overestimate your contribution, excel in ambiguity and inconsistency, and apply incorrect referencing of statements. Prefer subjective over objective statements. Give little care to grammar and language. Ignore editor and reviewers' comments. But if this is not what you want and you really hope to write a good article and publish in your paper in a journal, then you might want to follow the those steps. First step, determine whether you are ready to publish. You should not consider publishing if the work is outdated. You would be duplicating previous published work, or if conclusions are incorrect or not acceptable. These points are good indicators that your report lacks scientific interest or does not advance the field. You should consider publishing your work if you have information that advances understanding a specific research field. If you're ready to publish, then a strong manuscript is what is needed next. What is a strong manuscript? A strong manuscript usually have a very clear, useful, exciting message. It is always presented and constructed in a logical manner, and reviewers and editors can grasp the significance easily. Please keep in mind that editors and reviewers are very busy people, so please make things easy to save their time and yours. But before you even start writing your manuscript, there's one more step to go. Choose the right journal. So it is very important to select appropriate journals so that your work reach the intended audience. If your paper is outside the scope of a journal, it will likely to be rejected immediately by the editor, not even because of the quality of the paper, just because the topic doesn't fit the journal. So a good place to start is this journal finder tool. So with this tool, you can just put in the title of your paper and abstract, a few keywords, and the field of your research. Then it gives you a list of potential journals to look at. And please remember that your supervisor, who is often a co-author, also has responsibility of your work. So ask them for help, and also ask your colleagues when you're deciding where to submit, and they may be more familiar with the different journals that are relevant to your field. And there's another tip. Articles in your reference will usually lead you directly to the right articles. After you have a list of target articles, investigate all candidate journals, and please go to the journal website. Almost all publishers provide journal website. So from their website, you can find out their MSN scope, accepted types of articles, readership, and hot topic. And it is also very important that you do not gamble by submitting your manuscript to more than one journal at a time. International ethics standards prohibit multiple or spontaneous submissions, and the editors do find out. So after you choose a journal, then you need to prepare your manuscript. Editors and reviewers do not want to do not like wasting their time on poorly prepared manuscript. This is why each journal typically has a guide for authors with specific details for the preparation of your manuscript. Apply the guide for authors to your manuscript, even to the first draft. It can help you with the text layout, reference style, nomenclature structure, and other important items. This will save your time, and along with editors and reviewers. And what do you need to pay attention to in the guide for authors? I will tell you it's pretty much everything. It's usually super long, but please do not panic. There are some key items you might want to pay attention to, and I list them here. So first, you need to look at what is in and out of the scope of the journal, what the article types are published in the journal. Is it a subscription or open access journal? You might want to ask your advisor whether the funding agency of your research require you to publish in an open access journal, and whether your research group has sufficient funding to support an open access journal. And also you want to look at the article structure of this journal, and whether it is a single blind peer review process or a double blind peer review process. Also, there's some specific requirements like word count, number of tables, number of figures, and their format, reference format, number of reference, compound characterizations, supporting materials. There could be more. And here I also list the general structure of a research article. Usually research articles include title, abstract, keywords, introduction, methods, result, and discussion, conclusion, acknowledgement, and ZOI statement, reference, and supporting materials. You want to apply guide for also for each component of this of your article. And then with that, you can start writing your paper. So first, collect elements of your paper, prepare an outline to start writing a first draft, determine the central message. Also, it is the selling point of your article and the research question. Prepare draft versions of your plot, figures, tables, and images. Summarize main findings and group them in a logical way. and select relevant reference. You may prepare more reference than you want to select, but only select part of them. And then start writing the first draft with outline, figures, tables as your guides, and write it in your own style quickly and without even editing. Do not care about the language quality. Then read your first draft and notes. Read it as a critical reader and ask yourself, is the main message clear to new readers? The third step is to rewrite and improve, revise the text, improve the order and logic of a scientific component, identify gaps and improve unclear parts, and remove double tags, optimize the readability and correct language errors. And again, ask yourself, is the text consistent and coherent? And the last is very important, to get some feedback from co-workers, colleagues, and your advisors. And I have been asked for this question a lot, especially from non-English, non-native speakers. How can I ensure I'm using proper manuscript language? So usually it is the author's responsibility to make sure that the paper is in its best possible form when submitted. But publishers often provide resources for authors and help them to improve the language. And some publishers may perform technical screening before the manuscript was sent out for peer review. So as well have this web of short services, which you can get very professional language editing service or translation service. So we do not only provide service, we also it also come along with a certificate from as well to ensure that your article is in the language of your article is in a good shape. And before submission, check your manuscript as roughly as possible, and ask your colleagues and supervisors to review your manuscript. Finally, submit your manuscript with a cover art and wait for a response. After you submit the manuscript, it goes into the peer review process. So the peer review process have three key roles: author, editor, and reviewers. So after also submitted, editors will first screen the manuscript and check whether the manuscript met the basic requirement. If not, it gets rejected, and we call the rejection at this stage, that's rejection. And if the answer is yes, editors send their manuscript out to peer reviewers. Peer reviewers review the manuscript and give their recommendations and comments to the editor. And based on the reviewer's comments, editors make the second decision. It could be rejection or acceptance. Acceptance is very rare at the first round of peer review. And the third option is revision, and that happens most of the time. And if the decision is revision, it goes back to the author, and author needs to revise the manuscript when resubmit. So then the manuscript goes into the circles again. So there are mainly two types of revision: major revision and minor revision. What's the difference between them? For major revisions, the manuscript may finally be published in the journal, but significant deficiency must be corrected before acceptance. Usually it involves significant modifications and additional experiment. But for minor revisions, so basically the manuscript is worth being published, but some elements of the manuscript must be clarified, restructured, or shortened, or even expanded. But minor revision does not guarantee acceptance after revision. But often it is accepted if all points are addressed. So what editors and publishers are looking for during the peer review process. So first, plagiarism, whether the text is copy-paste from previous published articles. So this is a authenticate check which editors can have access. So after manuscript is submitted, the editorial system automatically runs these checks. As you can see, all overlapped tags are highlighted in color, and this check also gives the source of the original paper. So all copy-paste tags or overlapped tags can be captured here. So if there's plagiarism, the paper will be rejected, and then the editor will check the scope of the journal. If it's without the scope, then the article is rejected and suggests transfer to other journals in other field. And editor also checks the quality of your article, and if it doesn't meet the standard of the journal, it is rejected and often suggest transfer to journals in the same subject. The last component is, of course, the external peer review. Okay, so how to deal with peer review comments? And here we have some advice. So first, prepare a detailed response letter, copy paste each reviewer comment and type your response below, and state which changes you have made to the manuscript, include page or line numbers if required. Please do not add any general statements like comment accepted, and please provide a scientific response to comments to accept. And or convincing, solid, polite rebuttal when you feel the reviewer's comment is wrong. Write in such a manner that your response can be forwarded to the reviewers without prior editing. So be polite, please. Do not do yourself as a disfavor, but cherish your work. You spend weeks and months in the lab or the library doing this research. So don't run the risk of avoidable rejections by not taking manuscript revision seriously. So back to my first question, how to publish, how to successfully publish in a scientific journal. I have another 10 tips for you. Attention to details, check and double check your work. Consider the reviewer's comments, and English must be as good as possible. Presentation is important, and take your time with revisions. Acknowledge those who have helped you, and new, original, and previous unpublished results must be used. Critically evaluate your own manuscript, and also ethical rules must be followed. So after your manuscript is reviewed, and you will receive a decision letter. If it's accepted, congratulations. It's very rare, but it happens. Bring cake to your apartment, share with your colleagues, and now wait for the page proofs and then for your article online in print. And if it is rejected, please do not despair. It happens to everyone. And try to understand why your paper is rejected. And if you submit to another journal, begin as it were a new submission. Take advantage of the reviewer's comments from the rejection and read the guide for authors of the new journals again and again. So before I end my talk, I want to briefly talk about some ethical issues you might want to avoid. Of course, those three types of ethical issues are really serious, like fabrications of data, falsification, and plagiarism. So this plagiarism includes self-plagiarism. So you want to be very careful when you use some text from your own publication even. And disclose conflict of interest, not only in the conflict of interest letter, but also in a cover letter. If you are not sure whether it is a conflict of interest, please declare it in the cover letter, and editors will take that into consideration. And there's some, please avoid authorship issues, no ghost or gift authors, and please do not submit your manuscript to more than one journal at a time. And of course, peer review manipulation should be avoided. Okay, so at the end, I want to introduce you to this Research Academy source, and it is a free e-learning platform designed to guide and support early and mid-career researchers throughout their research. Throughout their research journals. 45% of the users are PhDs and 30% are masters. There are a lot of different online courses you can take advantage of, and it includes research preparation, writing a journal article, and publication process, and preparing a funding application, and even career planning. So it is a free platform, and you can and it's in different languages. You can visit it whenever you want. Okay, at the end, I want to thank you all for your attention, and really nice meeting all of you.
Okay, thank you, Dr. Wing. Professor Kim?
Hi. Yes.
So I'd like to add some comments to her presentation first.
So we highly appreciate giving a tip for the efficient publication processes. So privately, I also agree many of things of your presentations. So now the importance of ethics is dramatically increased, and the monitoring tools also developed, and also the similarity testing service is developed, and also we can use that kind of good service from elsewhere and another unique tools. So I believe this kind of presentation will be very helpful, especially to the junior researchers. So thank you one more time to Dr. Bing Wee. And there is, can I continue the Q&A section?
Yes.
To Dr. Bing now? Okay, so we receive, I can see two questions. First, what is the minimum % in originally test for a paper to be considered for next step? How much is the maximum match with each source? Okay.
So actually, thank you for the question. I think it's a really good question, and actually there's a lot of discussion between among editors as well. So there's no simple answer to that. So there's no magic number that we can tell the authors, hey, if the result is below this number, the manuscript will be sent out for peer reviewers. So actually we always recommend our editors and authors and reviewers to look at their report itself rather than the score, because what is overlapped is important than how much it is overlapped. For example, method or experiments part are more likely to be the same as previous published materials, because if you're using the same method, it's very likely that you're using similar tags in your article. But for discussion part, if you are copy paste the same paragraph by just modifying some numbers, then it is more severe. So we would never recommend editors just to look at the report itself, but we always recommend our editors to look at the report itself and check what is overlapped. And now preprints are more and more common. So if you submit your article to a preprint platform, then your SNK report will give almost like a 100% similarity score. But that doesn't mean it is a duplicate publication or a plagiarism. That's just because you submit to a preprint platform. And there's another example of thesis. Some university publish their doctorate thesis online, and this also leads to a very high similarity score. This is not considered as plagiarism. So, of course, when you write a paper, you want to avoid plagiarism as much as possible. But there's no simple answer to the question. So, please use your original language as much as possible. And I know that non-native speakers often have problems or some difficulties in using different languages. So editors sometimes take that into considerations as well. So please do not panic. Just try your best. Okay. So the second.
Okay, keep going. Excuse me, Dr. Bing. Second and third question is very short. You can answer by yourself.
Mm-hmm. So the second question is the Bell paragraph considered for original test? No, it is not considered for original test. The authentic report, the authentic check can exclude references and other parts, and editors can actually manually change the settings. So please don't worry about that. Those are not taken into some consideration. And the third question is how to decide any journal based on one's work. I think I briefly talked about how to select journal. So first, the journal finder tool can help you with to find a range of journals with different requirements for quality and novelty. And with a list of target journals, then you need to evaluate the quality and novelty of your research. And of course, your advisor suggestions is very important, as they have more experience in publishing and submitting a paper to those journals. And of course, you also want to check the article type of the journals. If it is a review-only journal, or does it publish research articles, or does it publish only short communications or only freelance articles? So you want to take those into considerations as well. Yep.
Okay, is there any more question?
Sorry, we don't have any other questions. I think that you can also ask other panelists to talk about their experiences. Professor Shogo-san. Yeah.
Okay, we will start the panel discussion related with the Q&A with the journal editors. So please open your web camera. So Professor Bing Wu and Jimei Otani Sensei. Okay.
Professor Oak is also should be invited.
Okay.
Yeah.
오경식 교수님, Professor Oak, can you join?
You mean the Professor Yoshioka? You mean? He's not available today, so.
Okay.
Professor Oak is also the journal editor.
Okay.
Mm.
Yes. Okay.
Okay. Anyway, so I have comments. So first of all, Dr. Wu, thank you very much for sharing your knowledge and lecture for writing a good paper, and also sharing what we are doing every day. So regarding the plagiarism, that's very important. But as she said, we carefully check the plagiarism, not only the percentage of the plagiarism, but also the content of the same part. So for example, experimental part, so we cannot avoid same experimental way in the sentence. So this case, it's not seriously check that point. But in the case of the similarity in the discussion, so for example, we can see the same discussion. Only the difference is the material and the product's name and also the figure. So this case, we carefully check the originality of each paper. So that's why the authors should not use same template of the paper. So even though we do a similar experiment using different materials, but the same template of paper could be checked by plagiarism test. So that's one very simple comment and advice from me. Thank you.
Okay, and I think the Professor Otani can also giving a good tip, especially to the junior researchers.
Mm-hmm. Thank you very much for the excellent lecture by Dr. Wu. So I am not now editor. I am an advisory board. So stand from the point of view as a reviewer, I also agreed with your lecture. So the much important point is how the reviewer can understand the writer's thinking or writer's way of experiment. So the manuscript should be logical, clear, and concise. It is very important, I think.
Okay, I also want to giving a same question to Dr. Binu. Okay.
Hi, thanks, Professor Kim, and thanks, Bing, for the nice articulation of the expectations, from a good manuscript. I'm sure it's going to be really beneficial for all the young researchers. So I'm on the editorial board of Journal of Analytical and Applied Pyrolysis, and also one of the editors of Advanced Powder Technology, not really related to pyrolysis. But I would like to share some of my experiences that, so there are two things. One is, of course, as Professor Otani mentioned, it's very important that the manuscript is really concise and and the novelty being very clearly, explicitly stated towards the end of the introduction section. So many a times we see, manuscripts wherein the authors discuss a lot of prior literature and prior art about a work, and then they quickly jump and say that this work describes about so and so. So it's always better to explicitly state, the motivation and the novelty of this work. That would be very useful for both the editors as well as the reviewers to make quick decisions and also be very clear, get a clarity on the presentation. And one more point I would like to mention here is that oftentimes we come across, the reviewers' comments not being answered in a very descriptive way. So many a times authors simply state that, if there is a question from the reviewer, right, they simply say, yes, answer, or they simply write a single word that it is done. So we typically state that we basically expect that, the authors to explicitly state what is the response to the reviewer's comment, and also highlight what has been changed in the manuscript in the response to reviewer's comments file, so that it's going to be much easier for the editor and also for the reviewer. If the manuscript goes for a second round of review, it's going to be easy for the reviewers to quickly get a feel of the response of the authors to the question, and also see their responses rather than going through the manuscript again and to search where this change was made. So this, I think, is so I frequently encounter that so sometimes the authors simply state that yes, it is implemented, or just a few words response to a reviewer's comment. I think the authors can be more descriptive, so that it's basically easy for both the reviewers and also the editors before making a decision. So thanks. I hope it was useful.
Okay, thank you so much for the great answers for the question. And there is one question to panel members. So please share some overview on the pyrolysis related paper publishing trend, especially in Asia. So which country are publishing more papers? Country competition. So I am keen to know the number of papers coming from South Asia, Southeast Asia, to understand the population of this among the researchers. So I think this question is proper to the Professor Soho Kumagai, because he is now editing the Journal of Analytical and Applied Pyrolysis. Could you please answer?
Okay, so now I don't have specific number, but Bin, do you have any information about the submission or publication trend all over the world? I think you have some data.
Yes, yeah. So I think just talking about Asia, so far China still ranks the first in the number of submissions and publications in the pyrolysis field, but India follows that. So far the growth rate of number of publications from India is over 12% annually, and the quality and the quantity increased crazily over the past 5 years. And followed by India is South Korea, Japan, and Malaysia. So those are 5 major players in their publication, in scientific publication in the pyrolysis field and overall in the chemistry field.
And actually that trend depends on the field of pyrolysis. So for example, biomass field, the China and of course Southeast Asia submission is higher than Japan and Korea. I'm not sure, but it's up to the field. For example, in my case, I am handling paper regarding plastic pyrolysis. So this case, I don't often receive papers from Southeast area, mainly Europe, China, and Japan, Korea. So it's really depend on the pyrolysis field. So how do you think, Professor Bean? Maybe you are advisory board and receive many papers.
Yeah, I agree with you, Shogo-san. The reason is because it's also related to the current trends in different countries. So certainly, I also, even when I review manuscripts, I see a lot of manuscripts on pyrolysis coming, of course, from China, and next probably would be from the Europe, but not much from the other Southeast Asian countries. I think currently there is a good boom in the research funding for plastics and plastic recycling kind of projects in the Europe that is reflecting this trend.
Yeah.
Okay, thank you so much. The time is limited. I think there's additional 3 minutes is allowed. So we have one more question. So some journal mentioned to us. So the scope is not proper to this journal because he thinks he did not cite the same journals. So what could be the reason for this response? So I also requested the kinds of the comment from the editorial board of some papers. So Professor Otani, so could you please give an advice for your opinion?
I don't really understand this question. I'm sorry, but I do not understand the question.
So if anyone can answer this for this question, please.
So can I answer?
Okay. Okay.
Yeah.
Thank you.
So actually we do not. I do not care the number of reference in the same journal. So the paper must fit to the journal scope, and the journal scope is modified day by day, year by year. So that's why at first the I'm sorry, the authors must carefully check and carefully check the journal scope, and also please check the recent publications. That's really important to understand the trend of papers which accepted in the journal.
Yeah, I think I agree with. Sorry.
Excuse me. Yeah, Dr. Bing Wu, please answer. Okay.
Yeah, thank you. So I agree with Professor Kumage that the scope of a journal is actually dynamically changing. Let me take one of my journals example, sensors and actuators, big chemical. So in 5 years ago or 10 years ago, it was a journal which focused mostly on instrument just by sensor itself. But
sorry, Dr. Bing Wu, we cannot hear your voice now.
Hello?
Dr. Vinay, you can proceed.
Okay.
Yeah.
Okay, so we will
Bing,
go to.
Bing, are you done?
Pardon?
Bing has some problems, so please, Dr. Vinay, please go ahead. Yeah, we had to wrap up this session.
Okay.
Fine. I also voice the similar opinion given by Shogo and also Bing. So certainly the journal's scope and also the interest changed with time. In fact, in my early days of publication, I have received a very similar comment even from JAP. Okay, but if you see, maybe a couple of decades back, you could see publications in JAP based on pure TGA-based studies, right? Thermogravimetric mass loss data. But if you currently see the way it is going, right, you will see that every manuscript in JAP would have some kind of a detailed characterization. It may be something like a analytical PYGCMS, or it might be some product characterization using mass spec, or maybe something like a pyrolysis FTIR characterization. So I mean, with advancements in analytical instrumentation also, right? So more and more papers with more detailed characterization of products, right, are expected in journals, and that might be the reason why if you are going to cite very old papers, you will see that very old papers might be just based on TGA data that will be published in a journal. But now, if you are going to publish, or if you are going to submit a manuscript with only TGA data, right, that may not be accepted. So this is one of my points. I think Shogo, I think you can also add if I think.
Yep.
You will
Thank you very much.
Yeah.
That's true. So I'm not sure, but 2 or 3 years ago, the journal changed the type of how to say English, the journal scope. A few years ago, we accepted only TG analysis, TG and TG-based kinetic analysis, but recently the analytical equipment and pyrolysis research level is advanced. So that's why we decided to include the spectrometric analysis, and also the chemical analysis is mandatory in the journal scope. So that's why so please carefully check the journal scope before submission. So it's slightly changed year by year. So that's, yes. Thank you, Binu. That's a good comment. Yeah.
I think the time is almost reached to the allowed time. But as so I only have one question. So in my cases, I'm very difficult to consider the short communication and the full manuscript paper. So when, for example, sometimes I finish the experiment, and which one is proper to me? So I think I also don't know the standard, which one is proper for the publication. So if it is possible, I think Dr. Bingwi can give a proper answer for my question. So which one is more proper for the short communication papers, and which one is for the full manuscript?
Actually, this is a very good question, and there's no simple answer to that. But I think 10 years ago, there's a clear line between short communications and full announced article. But these days short communications becomes longer and longer, and it is very common for people to get confused. And I would say it when you write your paper, it's much easier to start with a full-announced article if you have sufficient data, just because it's well structured. And for short communication, a lot of journals have a specific requirements for the number of pages or number of words or a number of tables and figures. So you need to capture your readers in a limited number of pages. So you need to structure your articles much better than for announced articles. So for early careers scientists or like PhD students or fresh postdoc, I would suggest you start with a 4-ounce article if it is the first time you write your articles yourself. And it's much easier to start with. And if you haven't read a short communication before, you understand it is very hard to get your readers interested in your article. Yeah.
Okay. So time is already over, so we have to close this section. So thank you, and I highly appreciate to all of the panelists for this section. And I believe this section is very helpful to all of the participants of this conference. Thank you so much.
Thank you. Thank
you,
Ben.
Thank you.
Thank you all.
Thank you. It's a very interesting session, guys. Now we get into the time is behind. We are behind the schedule, so let me get to the oral presentation next. The next presentation is on the first presentation of this session on oral. There is a preparation and a characterization of various craft lignin and impact on their pyrolysis behaviors by Ajay Kanti-Mondal. He is a PhD candidate from Fujian Agriculture and Forest University based in China. Let me invite him to make a presentation. Ajay, I hope you're ready. Please share your screen.
Yeah.
Okay. You have 8 minutes. Please get the main points quick. Focus on the main points. Yeah. Save your time. Thank you.
Okay. So good afternoon, everyone. This is Ajay Kanti-Mondal, PhD candidate of Fujian Agriculture and Forest University. So I am presenting here on my current research in my PhD work. So my presentation topic is the preparation and characterization of various craft lignins and impacts on their pyrolysis behavior. So my presentation will be divided in 5 parts. I will briefly discuss here one by one. So at first I have to introduce my research background, why I did this research, what is the logic behind this research. Because as you know that this is the structure of lignin model compounds. You know that lignin is the second most abundant renewable and natural polymer consisting of aromatic moieties cross-linked with each other by ether bonds and carbon-carbon bonds. And black liquor is the byproduct from the kraft process. During kraft pulping process, dirty pulp is washed to remove the lignin, hemicellulose and other wood extractive. Then black liquor is produced. This black liquor contains about 25 to 35% of lignin, and this lignin known as kraft lignin. So every year, the global pulp and paper industry generates more than 50 million tons of lignin as a byproducts, and less than 2% are converted to various products, and rest is used for burning to produce energy. Here you see that the lignin out from the digester in pulping process, and here this lignin, almost all of this lignin are used again for the burning purposes. So as you know that lignin is the most valuable product, but most of these are used for burning purposes without any valorization. So but this huge amount of lignin could be utilized as the production of green energy such as biooil, biochar, and electricity, etc. So in this study, I have tried to utilize this lignin isolation from black liquor at different pH to observe the effect of pH during the isolation of lignin from black liquor, and to analyze the properties of the isolated lignin from black liquor, and to investigate the pyrolysis behavior of isolated lignins. So at first, here I use 2 types of black liquor, loblolipine liner board and loblolipine bliss grade black liquor. Then I evaporated the black liquor, evaporated the water, and I got 2 types of lignin sample. This lignin sample is KL and KB, which is known as the kraft lignin. This thing only I got diurnal evaporation of the water of black liquor. Then I precipitated the lignin sample as pH 10 by sulfuric acid, and then I got 2 types of lignin, and this lignin is in L10 and B10. And similarly, I precipitated the lignin sample at pH 3, and then I got another 2 types of lignin. This lignin is L3 and B3. So here I got total 6 types of lignin: KLKB, L10, B10, and L3B3. So this lignin sample I have tried to use for pyrolysis experiment. Here I use the carbonate furnace. The pyrolysis experiment is done with the continuous flow of nitrogen, and in the right hand side you see that here is the condenser here, and here I got the pyrolysis products of oil, char, and gas. So there is the pyrolysis product here, and pyrolysis total experiment was done at 600 degrees Celsius about 10 minutes. So in between this pyrolysis product, heavy oil is the most important one because it contains a lot of valuable chemicals. So here in this experiment, I have tried to analyze the heavy oil, not consider mainly for light oil, char and gas. So at first I analyzed the lignin sample, the 6 lignin sample. I used here ICP analysis, ash content, GPC analysis for molecular distribution measurement, and for NMR analysis for HSQC-NMR. And similarly, I analyzed the heavy oil for HSQC-NMR and carbon-13 NMR, and also the molecular distribution. And result and discussion part, here I found that the indirectly coupled plasma analysis showed that this is the trace element, inorganic trace element, mainly the sodium sulfur. Sodium and sulfur is huge amount, especially for KL and KB lignin. You see here that is a huge amount of it. This is mainly region due to the adding of different types of sodium salt, such as sodium hydroxide and sodium sulfide, etc. during the pulping process. And after the acid precipitation like L10, B10, L3, B3, this trace element is decreasing significantly because after acid precipitation, the elements sodium and sulfur decrease due to their wash oil. And then I analyzed the ash content. Here you see that the ash content also in KL and KB is higher amount, is about 40%. And the L10 B10 is lower, and L3 B3 is more lower. So here I can conclude that inorganic element converted to ash during pyrolysis of lignin. As a result, KL and KB lignin produce large amount of ash. And we know that the only organic elements transform heavy oil, and these ash or inorganic elements have no contribution to produce heavy oil. These elements can catalytically decompose the heavy oil to char and gas by secondary reaction and by nucleophilic attacking, and as a result decreasing the yield of the heavy oil. So molecular distribution of lignin shows that the KL and KB lignin, the molecular weight is in between the L10 B10 and L3 B3, and after decreasing the pH of isolation lignin for black liquor, this molecular weight is also decreasing. And HSQC NMR of the acetylated lignin sample shows that the KLKB is the aromatic carbon hydrogen, methoxyl groups, and aliphatic carbon hydrogen bond. All are in KL and KB is lower than the L10 B10 and L3 B3, and it is also increasing with acid precipitation lignin. So due to the presence of impurities including carbohydrate, this lignin diluted in KL and KB lignin samples. As a result, the content of this functional group like carbon hydrogen, methoxyl group, and aliphatic carbon hydrogen groups is KL KB is decreasing. Then I got the pyrolysis yield, and pyrolysis yield here is, you see that the heavy oil, this is the most valuable products for pyrolysis, and here I got KL and KB produce less heavy oil, less char, and a higher amount of gas. So this is due to the secondary reaction of heavy oil, which is accelerated by sodium and sulfur that I found in ICP analysis. As a result, this heavy oil decomposed to gas and other char like this. So this heavy oil is decreased in the pyrolysis yield. And quantitative carbon-13 NMR are found that the carbonyl group, especially for carbonyl group and methoxyl group, is lower amount in the KL and KB lignin sample, because it can be concluded that this decarbonylation reaction and demethoxylation is accelerated in KL and KB lignin sample by the sodium and sulfur compound. So it is a significantly decrease in KL and KB. And similarly, it is also a lower amount in L10 B10 than L3 B3. So HSK and NMR also confirm that the KL KB contain more aliphatic carbon hydrogen bond and less aromatic carbon hydrogen bond methoxyl group than other lignin sample. So here we can say that the content of methoxyl group are the much lower in KL and KB. You see the methoxyl group is much lower here in the KL and KB, and it is increasing in the L10 B10 to L3 B3. So this can be happened. This also that's inconsistent with the carbon-13 NMR result, which I highlighted before, and also the KL KB contain higher amount of aliphatic and aromatic carbon hydrogen bond. Due to this severe bond cleavage, the KL and KB lignin pyrolysis oil contain many more aliphatic CH bond, and this is also inconsistent with the carbon-13 nanomer results.
Ajay,
So
can you please
molecular weight
conclude it?
also, so molecular weight shows that the molecular weight is increasing with increasing the going to the lower pH to higher pH. So to be conclusion, for lignin samples, ICP analysis showed that the KL and KB lignin contain large amount of inorganic elements, especially sodium and sulfur, compared to other lignin samples, which form higher percentage of ash. And for heavy oil analysis, most variable product heavy oil decrease KL and KB due to the decomposition of heavy oil by catalytic activity of sodium and secondary reaction of heavy oil to char and gas, which is accelerated by sulfur. And AMR analysis have heavy oil proved that sulfur could effectively lead to demethyl and decarbonylation reaction in KL and KB lignin pyrolysis heavy oil, which is 3 times higher than other oils. So molecular weight for the pyrolysis heavy oil from KL, KB lignin was slower than those from the 4 lignin samples because of the enhanced depolymerization of lignin structure during pyrolysis as a result of presence of inorganic elements. So here I would like to express my sincere gratitude to the organizing body of Pyrolysis Symposium for selecting my abstract as a part of this symposium. I would like to express my warm gratitude to my supervisor, Professor Yang Honi, and my co-supervisor, Professor Phang Wang, for their continuous support to my study, research, for their passion, motivation, enthusiasm, and immense knowledge. My appropriate gratitude goes to all of the listeners, researchers, and all scientists. So thank you for your attention.
Okay, thank you, Ajay. If you'd like to ask some questions to Ajay, please post in the question box. Next, now we'll get to the next presentation. It's on the influence of pomelo derived hydrochar on the combustibility and residual ash of torrefied poultry litter and lignite fuel blends by Dr. Sandal Fakudje. Dr. Sandal, let me share screen. Okay, here I go. Please share your screen. You got 8 minutes, please.
Okay, can you hear me?
Yes.
Yes. So my name is Sandil, and today I'm going to present about our recent study, which is about the influence of pomelo derived hydrochar on the combustibility and the residual ash of torrefied poultry litter and lignite fuel blends. And so my presentation today will cover these contents. And so just a little background on the on our study. As we know that due to the gradual expansion of the poultry litter production in the whole world, there is an abundance of poultry litter, so which can be used as a biomass feedstock for energy generation. So many researchers have investigated the co-combustion of torrefied poultry litter and coal, but what we have seen from their work is that there is an increase in the formation of toxic ash contents due to heavy metals such as copper, arsenic, and lead. So one of the previous studies suggested that the addition of biochar with higher carbon content and superior combustibility can help to reduce the formation and accumulation of the ash contents. So in this study, we produced hydrochar via HTC, the HTC of pomelo peel, and then we combined this hydrochar with the torrefied poultry litter and lignite. And then we studied the combustion properties and also the effect on the ash. So we studied the SEM, and as we can see from these SEM images, we can see that the porous hydrochar, the hydrochar has a uniform structure, unlike the torrefied poultry litter, which has no uniform structure. And we also studied the fuel properties, the physical chemical properties. And what we can see from these results is that the VM contents significantly reduced during the HTC process, and also during the torrefaction process in the production of torrefied poultry litter. And also, as you can see, the carbon contents of the hydrochar were almost similar. They were very high, almost similar to the carbon contents of lignite, which shows that HTC is very effective in producing a high carbon fuel. And also from these results, we can see the Van Crevelen diagram of atomic ratios, which show us that during the HTC process, it is easy to see that during the HTC process, the carbonization of the pomelo peel was very effective. As you can see that as the points move towards downwards and towards the left side, this shows the occurrence of these two chemical reactions, decarbonization and dehydration. Also on the side, we can see from the FTIR spectra, we can see that the use of HTC for production of hydrochar was very effective. As you can see, the CO pending from cellulose is almost completely eliminated with an increase in the temperature at 240 degrees. And also from this figure, we can see the HHV contents. We can see that with an increase in temperature, the HHV content is significantly increased for the hydrochar. And we can see that the HHV of the hydrochar was almost similar to that of coal. And it is higher than that of torrefied poultry litter. But with regards to the energy yield, you can see that the energy yield actually decreases with an increase in temperature, which was mainly due to the mass yield or the char yield. And from these figures is the TG and the DTG diagrams, which shows the weight loss and the weight loss rate of the fuel blends. The first digit of the ratios is PPHC, which is the hydrochar, and PLPC is the torrefied poultry litter, and then lignite. And from this diagram, we can see that the samples that had a higher proportion of hydrochar were highly combustible, and they had a higher reactivity. And this table 2 here is it shows the combustion properties of the fuel blends. And from this diagram, you can see that the addition of a higher proportion of the hydrochar actually reduces the ignition temperature. And also we can see that samples that had a higher proportion of the hydrochar had at least two peaks. And this signifies, the first peak signifies the combustion of the volatile matter, VM, and the second peak is the combustion of the char, or the fixed carbon. And on the table, underneath table 3, we can see the combustion characteristic index. We calculated the combustion characteristic index, which signifies the combustibility of the material, or the ease of the material to burn. So from here we can see that the sample number 3, which is the blending ratio of 116, we can see that it had the highest combustion characteristic index, which shows that the addition of hydrochar to the fuel blends really enhanced the combustion. And we also calculated the activation energy, or the kinetic properties. And as we can see here, if we consider peak number 2, we can see that the activation energy of fuel plants that contained a higher proportion of the hydrochar were lower than the other samples. And but we should also consider that these samples, they also had another peak, the peak of the VM combustion. So this should also be considered. And finally, we explored the ash contents of the samples, and from here we can see that the ash contents were significantly reduced with an increase in the hydrochar content, which shows that the addition of the hydrochar actually reduces the formation of the toxic ash contents. We also analyzed the heavy metals, and you can see that with the sample that contained hydrochar, the heavy metals were significantly reduced, including also the chloride contents. And in conclusion, I would like to say that the environmental threats posed by the leaching of toxic post-combustion ash cannot be neglected. And the addition of porous hydrochar to the fuel plants not only decreased the post-combustion ash contents, but also reduced the ignition temperature while maintaining a high burnout temperature. And this indicates that the addition of the hydrochar actually enhances the combustion characteristics or the combustibility. And this is part of our work. I'm a student of Professor Chen Shang Chen, and our lab is called Advanced Materials for Energy and Environment. And what we do is we conduct research on the utilization of agricultural and forestry waste for the production of bio-based materials for energy and environmental applications. Thank you.
Thank you, Sanil. If you have any question to Sanil, please post questions in the question box. Let me go to the next presentation. Okay, the next presentation is on the application and comparison of the artificial intelligent models on pyrolysis of oil palm biomass by Asmin Mohammad Jaifulijan. She is a PhD student at Monash University, Malaysia campus under the supervision of Dr. Ashar Salema and Dr. Lim Min Kun. Her research focuses on the development of artificial model for oil palm pyrolysis process. Asmin, please share your screen. Let me send a request. Okay.
Okay, sure.
Okay, you have 8 minutes, so please, yeah. If you'd like to open your webcam, please open. Yeah. Yes. Okay.
Okay.
Right. Yes.
Yes. Right. So, oh no, how do I can't see my slides. Sorry. Yeah. Okay, so hello everyone. So my name is Yasmin. I'm one of the PhD students in Monash University, Malaysia. Today I will be talking to you about the application and comparison of artificial intelligence models on pyrolysis behavior of oil palm biomass. So I think I'll just skip this slide and just continue with the background. So as we know, biomass pyrolysis is one of the potential routes to harness energy and useful chemicals from biomass. It's a thermochemical process capable of converting solid waste into usable fuels in the shape of non-condensable gases, biofuels, and biochar. So many researchers are looking into pyrolysis because of this feature and the usefulness of the potential usefulness of the product. So, but however, biomass pyrolysis is a complex process involving multiple stages of reaction mechanisms and kinetics. This, coupled with the multi-scale or multi-component nature of biomass feedstock itself, make it very difficult to model. So for example, lignocellulosic biomass consists of 3 different components, each having their own respective reaction pathways, and these reactions may or may not happen simultaneously, and they may or may not overlap, so adding to the complexity of the process, making it difficult to model. So now, usually when people start to do any pyrolysis process, to understand the fundamental biomass behaviors, researchers typically use a thermogravmetric thermogravimetric analyzer. I think today we heard a lot about TGA. So this is done just by monitoring the weight change that occurs as a sample is heated. So TGA can provide us with a large amount of information, including the material stability, the fraction of volatiles in a certain material, and even the thermokinetics by if we do further analysis on it. So this precise equipment can give us insight into the reaction mechanisms of thermal decomposition involved in the pyrolysis process. So coming back to the biomass pyrolysis modeling, so as opposed to traditional mathematical kinetic modeling, in our study, we wanted to use artificial intelligence and see if it can model the complex pyrolysis behavior using the TGA studies. We want to see if we can make predictions from new unseen data. So the objectives of this study was to first develop 2 different prediction models using artificial intelligence based on 2 different biomass. Then we wanted to compare to use and compare the AI models to see which perform better for our specific application. So the term artificial intelligence is very broad. Is very broad. We are mainly focusing on machine learning to develop these models. So machine learning is basically the ability of machines to learn from data. So the more data it's given, the better they learn. So this figure here shows the standard machine learning pipeline. It shows how the data needs first to be prepared. It is segmented into training and testing data sets. Then it's passed through the learning phase until it can be able to make prediction on its own. So in this study, I developed the artificial intelligence models using MATLAB. So as mentioned before, we wanted to develop 2 different types of artificial intelligence models based on 2 different biomass. So the biomass here used are oil palm shells and empty fruit bunches from oil palm waste. So these biomass have different chemical and also structural characteristics, and they exhibit different pyrolysis behavior, which will be the outputs of the models in the shape of thermogravimetric analysis, thermogravimetric curve, and the derivative curve. So the 2 artificial intelligence models used in this study are going to be artificial neural network and decision trees. So ANN is inspired by the workings of biological neurons of the brain, while decision trees follow a flowchart similar to an upside down tree structure. Okay, so each model work in different ways and needs to be optimized according to their own hyperparameters, but I won't go into details of workings behind them. So both studies will have the same input features, which are the biomass types mentioned before. They also the different heating rates and the corresponding temperatures. So all the data used to develop these predictive models were actual data generated from experimental runs done in a TGA machine. So after all the models were trained and we tested them, or we did a validation test by introducing a new data set that they have not seen before to see how they performed. So here, these figures are a comparison between the results from the AI prediction models and the actual experimental results. We can see that in general, all the prediction models were capable of capturing the pyrolysis behavior of the oil palm biomass. Both ANN and decision trees perform quite well in this scale of study. However, there are slight differences in the performance, which we'll see in the next slide. So here is the statistical analysis, giving a more detailed analysis of the results. So the performance criteria used in this study were coefficient of determination and mean square error. So basically, we want high R²R values and low MSE values, which indicates better predictive capabilities. So in this table, we mainly focus on the testing results to see to compare the predictive abilities. So first, in the TG curve, the decision tree model has higher R² value compared to ANN, but ANN had lower MSE values when compared to the decision tree. So the same trend is seen in the DTG curve. The decision tree had higher R² values, but ANN had lower MSE values. So although the differences here are minimal, as you can see, it will start to show when more data and more features are added to the models. So we can say that based on the results obtained here, decision trees give high R² values, but also high MSE values, which indicates that they actually overfit the data, making it rigid to the introduction of new data sets. But in contrast, ANN has both high R-squared value and low MSE values, which indicate that it is more accepting of new data and give better prediction results as a whole. So this feature is very important in future works as we introduce more data into the models, increasing the complexity. So to conclude, the two artificial intelligent models developed were both capable of predicting the process behaviors of two different biomass. So overall, ANN performed marginally better than the decision trees with high R-squared values and low MSE values. For future works, we plan to use other artificial intelligent models as comparison to see if other machine learning models give better prediction capabilities than our current model. We also want to bring the study to a larger scale with a laboratory priority setup. So the plan is to expand the study by generating more data and by diversifying features to increase the capability of the prediction models. So that concludes my presentation today. I would like to acknowledge the Ministry of Higher Education of Malaysia for funding of the study. I would also like to thank Monash University Malaysia, my supervisors and the research team for all their help. Thank you, and that's it for me.
Thank you, Yasmin. Thank you very much for a good presentation. If you have any question to ask me, please post questions in the question box. So let me take over the screen. Thank you. Okay, the next presentation is on the prediction of co-pyrolysis products of cellulose and polyethylene using the response surface methodology by Shengyu Zi. Okay, he's on. Okay, let me share the screen to him.
Hello.
Okay, can you please share the screen, please? Okay, open the PowerPoint, please.
Okay.
You have 8 minutes, please.
Can you hear me?
Yes, I can hear you. You have 8 minutes. Please continue.
Okay. Hello, everyone. My name is Shengyu Xie, a PhD student from Tohoku University. Today, my topic is about prediction of co-pyrolysis products of cellulose and polyethylene use response surface methodology. The production of wood plastic composite is including during its super properties. However, these methods are difficult to recycle with borrowing the population problem. Literally, the pyrolysis can convert this waste into the valuable chemical feedstock of fuel. In our previous studies, the interaction between the biomass and the plastic can improve the liquid yield and quality during the co-pyrolysis. However, it's necessary to conduct a large amount of experiments for understanding of co-pyrolysis impact, which will cost much time. So, response surface methodology is based on the fact of the polynomial in question to the experimental data, which can include the interactive effect among different variables. The procedure of this methodology includes the section of response, choose the strategy, running the experiment, fitting model, confirming model, and finally, the process optimization. So, therefore, we can obtain the all result within some conditions which can short-term consumption. So, therefore, we applied in this methodology in the co-pyrolysis of cellulose and polyethylene to establish the mathematical model for the prediction of product yields. So this work, the pyrolysis temperature and the PE ratio was the selected response. The next, the center composite design was chose the obtain the pyrolysis condition. In this figure, the R square is the condition and constraint of experiment, and 600 with 15% of PE addition is the center point. So because we set the 5 level for each factor, so there is a equable square in this figure. Pyrolysis experiments were conducted in a factor-fed reactor. The carrier gas was through the tube joint trap engine and collected the gas bag. 0.1 gloom sample was pyrolyzed at % temperature for 15 minutes. The collected gas was identified by GC mass and quantified by GC TCD and FID. The extracted liquid by the tetrahydrofuran solution was analyzed by GC mass and FID. The solid is THF insoluble fraction, which include the cook from the cellulose pyrolysis and wax from PE pyrolysis. Moreover, the char was wetted after combustion. So this is result about gas yield. From this figure, the gas yield was remarkable inclusive with the runs in the temperature and PE ratio. We found that the alkali gas yield were higher than the theoretical value, indicating the interaction between the cellulose and the PE could enhance the gasification. Because they are synergistic in factor between cellulose and the PE, which are don't even see by the temperature. So the gas yield was fitted to the constructed model. This is result about the liquid yield. Liquid yield was decreased with the rise in the PE ratio. We found actually the liquid yield was higher than the theoretical value, indicate the interaction between the cellulose and the PE could enhance the liquefaction. So the liquid yield from the co-pyrolysis could be fitted the contracted model because they are synergistic in factor, which are don't influence by the temperature. For char yield, we can find the char yield should surface under different condition as this figure, and there was no impact of interaction between cellulose and PE on char formation. Therefore, the char yield from the co-pyrolysis could be the fitting to the linear equation because the results are influenced by temperature, where there is no synergistic factor between cellulose and PE. The environmental value was close to the predictor value for char yield. This is result about the main product yields in gas and liquid. The carbon monoxide yield was fitted to the quantic model because they are different the synergistic in factor with the rise in the PE ratio. The carbon dioxide was fitted for the linear model because the results are influenced by the temperature. But there is no synergistic in factor between cellulose and PE. Additionally, the methyl and hydrocarbon yields were fitted the cubic model because they are synergistic in factor, which are influenced by the temperature. The level glucosan yield was suitable for the contracted model because they are synergistic in factor, which are influenced by the temperature. Lastly, the glucoaldehyde yield was fitted for the true FI model because they are no synergistic in factor. The results are influenced by the two factors. So this is the conclusion of my work. The different the polynomial equation can effective describe product yield from the co-pyrolysis of cellulose and polyethylene based the process pyrolysis condition. So we can predict the production yields under pyrolysis condition by these models. We can decrease the experimental time. That's all. Thank you.
Okay, thank you, Mr. Xi. Guys, if you have any question to Xi, then please post your questions in the question box. Let me take over the screen. Okay. The next presentation is on the catalytic upgrading and lignocellulosic biomass pyrolysis vapors. Insight into the physicochemical changes of the ZSM5 by Dr. Jechao Wang. He is the assistant professor at the Xiamen University. He mainly engaged in the basic research on the thermochemical conversion. Has carried out a clean and efficient conversion of biomass and coal, heavy oil, and other heavy organic carbon. He has published 21 articles in journals, 1 Chinese patent. Let's welcome Dr. Wang. Let me share his screen. Yes, can you please share the screen, Dr. Wang?
Okay. Okay.
Okay.
Can you hear me?
Yes. Okay, one,
yes,
two.
Okay.
Go on.
Good afternoon, everyone. My name is Chao Wang from Xiamen University. It's my honor to give these presentations. And today I will talk about the physical chemical changes of JSM5 after it was used for the KT upgrading of biomass. And my topic will contain these 4 parts. Let's look at this introduction. As we all know, fossil fuels will account for the major energy consumptions in the world. These fossil fuels contains coal, petroleum, and natural gas. Traditional biomass accounts for about 7% of the final energy consumption at 2028. As we all know, China is rich in biomass resource, and there are a lot of biomass resource in China. Usually, when we use this biomass, the direct use of biomass as a fuel, such as combustion, is the first use for this biomass, but it will cause some serious problems such as hazard and other environmental problems. The utilization of thermal technology such as pyrolysis and gasification can convert biomass into synthetic gas such as hydrogen and CO1 or bio-oils. This bio-oils can be upgraded by catalytic upgrading into useful fuels or valuable chemicals, or the solid fuels, the solid materials known as biochar. During this catalytic pyrolysis, JSM5 are widely used. As we all know, after catalytic pyrolysis with JSM5, aromatic hydrocarbons such as these chemicals can be obtained. But when use these JSM5 gelatin materials, there's one problem is the formation of coke. As we all know, the formation of coke will gradually lead to the gradual deactivation of JSM5. So it's very important to understand the change of JSM5 after it was used for the catalytic upgrading. And the lignocellulose contains 3 major components such as cellulose, hemicellulose, and lignite. So the second purpose of this work is to understand the effect of different feedstocks after it was JSM5 was used for the catalytic upgrading, and we will use several characterization methods to understand the physicochemical change of JSM5. We use PY coupled with PY isomers to online analysis of pyrolysis product. After the biomass sample was loaded in the first zone, the pyrolysis vapors will pass through the catalytic upgrading zones, and the upgraded product will collected under online analysis by isomers. Okay, now let's look at the disease spectrum of the non-pyrolysis and the catalytic pyrolysis. And we can see that the catalytic upgrading of JSM5 is quite different from the non-catalytic upgrading. We analyze the detailed compounds of the bio-oils, as we can see that JSM5 is contributed for the formation of aromatic hydrocarbons and alkanes. that's quite different from the without that of JSM5. The main purpose of this study is to understand the physical chemical change of JSM5. So we first collected the used JSM5 and compared with these fresh ones. As we can see, the used JSM5 shows different colors with as compared to the fresh ones. We can see that the used JSM5 samples color change to the gray or dark. And the second we use SEM images to understand the microstructure changes, and we can see that the morphology of the fresh and the used JSM5 shows no significant change after it was used for the biomass conversions. So we can conclude that there's no much significant change in the morphology of JSM5 samples. After that, we use this XRD to understand the critical changes. As we can see, all the JSM5 samples shows the MFI structures, and in terms of these used JSM5s, there's no much difference in terms of this peak position and intensity. So there no crystal transformation can be found on these used JSM5 samples. In the case of these FTIRs, we found that on the user samples, there's new peaks around these ranges. So we can confirm that this range is related to the vertical groups. As we all know, the acid size on the JSM5 is the key for the conversion of biomass. So we first measure this total acid amount size of the JSM5s. We can find that the weak and the strong acid size of JSM5 are all decreased after it was used for the KT cracking. In terms of these B size and the L size, they also show some decrease, but we can see that the decrease of this B size amount is much higher than the L acid size amount. So we can conclude that the B size is accounted for the KT upgrading of biomass. After that, we also want to know that how many coke will deposit on the JSM5. So we analyze this elemental coke on the user JSM5. We can see that JSM5 used for the cereals has the largest coke content, and that's hydrogen content. This constant with the physical chemical changes of these samples, because JSM5 samples collected from cereals is dark, which is darker than other two samples. Finally, we analyze these textile properties of JSM5, and we can see that after the reactions, JSM5 samples shows the decrease of total specific surface area. And in the case of these pore diameters, we find that the pore is becoming smaller than the first ones. And we also find that the specific surface area of the micropores is increased. That's an interesting finding, but we still find good reasons to explain that. Finally, we use JSM5 samples for the KT upgrading of three major components in the diagnosis of biomass, and then the physical chemical changes of JSM5 are studied in this study. And we find that the addition of JSM catalyst is contributed to the formation of aromatic hydrocarbons and alkanes. And we also find that there's no crystal and the morphology change of JSM5, and coke deposit on the JSM5 will lead to the decrease of total acid size and BL size, and along with the specific surface area. One interesting finding is in our work is there will lead to the increase of micropores, but the reason behind state of this increase needs to be further investigated. That's my today's presentation. Thank you.
Thank you, Dr. Wang. Guys, if you'd like to ask some question to Dr. Wang, please post questions in the question box. Let me take out the screen.
Okay, thank you.
Okay, the next presentation is on the by Mr. Ranjit Kumar Mishra. Is presenting about the effect of biomass bed thickness and distance between the successive bets on yield of pyrolysis products and properties. Okay, Mr. Ranjit, I'm going to ask you to share the screen.
Hello.
Yes, proceed.
So I'm audible, I guess.
Yes, you're audible. You have 8
And
minutes. You know, focus on the main points. Yeah. Okay.
yes. So myself Ranjit Kumar Mishra, and today I'm going to just present one of my PhD research objective, just to understand the effect of biomass bed thickness and the distance between two successive beds on their pyrolytic yield and their property. So these are my presentation outlines. So first I will go introduction, background, and then material and method, result and discussion, and after that conclusions. So basically we start from the renewable energy era and we shifted to the fossil fuel era in around 18th century, and now we are again shifting to the sustainable energy or renewable energy era, and we are trying our best to finding the best possible source to get the renewable energy. And among all the existing renewable energy sources, biomass is one of the leading and emerging and most sustainable source for the production of renewable fuel or energy. So basically, current why the biomass or why renewable energy is important? That current way of energy use is unsustainable. Demand for renewable energy source is expected to rise in future, biofuel gaining very popularity across the worldwide and promoting industrial fuel and solve the crisis. And why alternative energy fuels? Because of that, is overcome energy deficiency, reduce the global warming, replace the conventional fuel and up to some level, and reduce the dependency of fuel. So as we know that biomass is the organic matter which have the chemical energy, and that can be converted into the different form of energy. So biomass is the potential source of energy and extremely low emission of greenhouse gases compared to the fossil fuel, and reduction of waste and growing variety of crop, increasing the biodiversity. So these are the biomass source, that is forestry, crop and residue, agriculture residue, sea waste, municipal solid waste, animal residue, and industrial effluent. So these are the thermochemical conversion techniques. So I will discuss only the pyrolysis techniques. So pyrolysis provide only char, bio-oil, and fuel, and that can be stored and further can be used for the production of biofuel or chemical, or can be used for the generation of electricity and heat. So this is very well known slides. Everybody know. I hope so. Everybody know about that pyrolysis. So I'm just going to briefly discuss. You take the biomass and place and provide the heat, and in the absence of oxygen, so it will burn and release the gases, that is the condensable gas and non-condensable gas. So the condensable gas will condense by using some condenser, and biochar can be removed after cooling the temperature. So there are some important factors that strongly alter the pyrolysis product and yield and their product distribution as well. So these are the temperature, particle size, heating rate, types of reactor, shipping gas flow rate, influence of mineral matter, and many more. So to find out the best possible use of the bio-oil, bio-oil can be used for the chemical extraction, heat generation, electricity, and transportation fuel. Similarly, for the gas can be also used for the heat and electricity. And char, I already discussed in today presentation, the variety of use of char. So today I am going to just discuss about the effect of biomass bed thickness and successive bed between two beds. So we taken three biomass, that is pine sawdust, sal sawdust, and areca nut husk. And this is our experimental setup. This is the semi-batch reactor. It's the semi-batch fish packed reactor, where we place the biomass. Instead of putting into one bed thickness, I placed into the putting into the 6 bed based on their arrangements. So we have placed in such arrangements like we have placed one biomass thickness one time, then again going for the 2 biomass, then 3 biomass, 3 bed thickness, then 4 bio bed thickness, and up to 6. So this the table shows that the arrangement of bio thickness and distance between the 2 successive beds. So we characterized the physiochemical study of the biomass, and we found that high volatile matter, lower ash contents, and high carbon content, and higher heating value, higher chemical analysis, and extractive content is lower due to because of that these are the wood based. So based on this property, we can say that this biomass has the potential to produce the renewable fuel and value added chemicals. We did the thermal analysis and FTR analysis of all the sample, and we find out the active pyrolytic zone exists somewhere 180 degrees Celsius to 500 degrees Celsius. And FTR analysis confirmed that presence of all the useful functional group that should be useful for the production of renewable fuel. So before going for the actual pyrolysis, we optimized the process parameter like temperature, heating rate, and particle size, while we kept 100 ml per minute nitrogen flow rate throughout the reaction, throughout the pyrolysis experiment. So we find out that 500 degrees Celsius temperature and 80 degrees Celsius per minute heating rate and 0.5 degrees Celsius per minute particle size is the optimized condition where we get the maximum liquid yield. So by keeping these data, we pyrolyze the biomass, and we find out that up to at 4th bed we found the maximum liquid yield. However, up to 1 bed, 2 bed, and 3 bed, the liquid yield is less as compared to 4 beds. Similarly, for the char yield, we find out the lower char at 4th bed, and similarly, similar result we have found for the gas analysis. So we characterize that only the liquid fuel, that means this is only organic phase. We have separated the aqueous phase by the density difference using the separating funnel. And here we again find out that the 4th bed showing the better property as compared to 1st bed and 6th bed. However, the difference is slightly very lower due to the lower length of the reactor. But I'm sure that if it would go with higher reactor length of reactor, it will give the slight difference. Similar results were also found for the salwood and arc converter gels. Then we have also going for the FTR analysis, the pyrolytic oil, and yes, all the pyrolytic oil has almost the similar functional group because of the having the similar chemical composition of the biomass. Then we go for the GCMS study of the fuel, and we find out that all the biomass like pine sawdust, salt sawdust, and arcanut sawdust have the maximum amount of phenol followed by acid and other oxygenated compounds. However, at the 4th bed ratio, we find out the reduction of the phenol as compared to 1st and 6th bed due to the reducing the secondary cracking reactions. So that's why the phenol formation will be lower as compared to 1st and 6th bed. So based on that, we drawn the following conclusion that physiochemical study of biomass showed its bioenergy potential to produce fuel and chemicals. We found the maximum liquid yield 44.458% for pine wood, 34.37% for sawwood, and 33.7% for arcanut at 4th bed. And FTR analysis confirmed the presence of aromatic ether, alkanes, phenol, acid, ketones, ester, and aldehyde. This FTR refer to the pyrolytic oil. Characterization result of pyrolytic oil showed that improved property of pyrolytic oil than the other bed, like heating value and reducing in the viscosity and acidity and other characteristic of the pyrolytic oil. Finally, we did the GCMS analysis, and GCMS analysis confirmed the presence of aromatic phenol, ester, ether, alcohol, acid, and amide group. However, 4th bed arrangement showed that formation of phenol will be lower, and phenol and oxygenated compound will be lower. This is the cited reference. Thank you.
Okay, thank you very much. And now, we're going to actually have a Q&A session, but due to the time issue, what I'm going to do is that whatever the questions you submit to us, I will pass this question to the speakers, and they will reply by email to you. Hope it is all right with you. Otherwise, it will be a challenge to finish the program in time. Okay, I'd like to ask Professor Kim to summarize this session. Professor Kim. We have a time issue. Please summarize. Yeah, thank you.
Okay, thank you so much. And I'm really sorry for the giving a chance for Q&A section. First, I highly appreciate you, Dr. Bing Wee and the journal editors for your great help. And I believe the more efficient publication related with journal and applied pyrolysis can be achieved by all of us. In addition, various kind of short presentator. Thank you so much. Thank you all presenter panelists and especially to Param. Thank you so much. I want to close this section now. Thank you.
Thank you very much, Professor Kim. Guys, we take a quick break, 5 minutes only. We start next session immediately because there are two presentations in the first session were dropped, so I need to bring them to the third session. Okay, so we start in 5 minutes. Okay, you can have a coffee or go for a break. Yeah, 5 minutes. Thank you. Prashant, are you there?
Yes, sir. Yeah.
Okay, can you quickly share your screen? I want to check your screen is okay. I'm going to send a request to you.
Yeah, 1 second. Yeah.
Okay. Okay, you will be the last presentation in the this oral presentation. Okay, yeah.
Yeah, sure, sir. Yeah.
I'll stand by. Yeah. Okay.
Thank
you.
Yeah.
Munmi, I hope your speakers are all right. Yeah. Can you hear me, Munmi? I can't hear you back. I see your speaker is on, but I don't hear you well. And are you sure your speaker is all right? Your presentation will be the before Prashant. Before Prashant. Okay. I hope your system will be ready by the time.
Sorry, Param, can you hear me?
Who is this?
It's Lam here. I mean, Sushil Lam.
Yeah, hi there. Yes, I can hear you. Yes. Okay.
Param, can I just check with you? I'm trying to access to, I'm using my phone, but it asks for the webinar password. What is the webinar password for logging today, for the session today?
That is for the delegate, okay. But when you register as a panelist, you are in the panelist now. I already moved to the panelist.
Right. Okay. So because I'm trying to log out using my desktop laptop and trying to access using phone. Let me just check if I have any problems. I'll get back to you. Thank you, Param.
Okay. Yeah. Thanks.
Param, sorry to disturb again. Hi, Param.
Can you hear me?
Yeah, Param. I mean, it still asks for my webinar password. I mean, even I try to click the link as a panelist.
Really?
So what should I key into my phone? I mean, the
Okay,
webinar password.
Okay, webinar was supposed to be the Pyro 201312.
Can you just send? Send it to my chat. I mean, personally. I mean,
Sure.
thank you.
Sure. Thanks.
Thank you.
Okay, guys, get started for the next session. Okay, this is a panel discussion. We still have some oral presentations, almost like 6 presentations. So we make sure that we'll be finishing on time. And also we have panel discussion, and then we have a wrap-up session with the concluding remarks. Okay, and I invite Dr. Shatugnan Karthikeyan. He is shortly called Karthik, the man behind this event. Main person behind this event. Okay, he is basically consultant, sales and technical support for the Frontier Laboratories. He got a PhD in chemistry, having more than 15 years experience from both academia and industry with leadership skills and R&D, and also the strong knowledge in the environmental and the food safety and implementing various quality management system. Dr. Karthik is all yours now.
Thank you. So I really appreciate your commitment and involvement for the last 3 days. Is really greatly appreciated. And I think we are coming to the last session of the this year symposium, and people must be looking forward to this in different way. One is, after this, at least we can feel that we are done with this symposium, and it's a much needed break for everybody. At the same time, we also have some announcement where some of the applicants may be looking forward to see whether are they really be part of this winner. Okay, so without further ado, so let us get started with the short oral presentation. So we have 4 presentations as part of this session, and 2 were actually dropped in the first session because of some technical glitch. So I think Param will invite one by one first, then we will move on to the Q&A, then panel discussion, and finally the wrap-up session. Okay, Param, back to you.
Okay, thank you, Dr. Karthik. Okay. The next presentation is optimization of preparation green biodiesel from fatty acid methyl ester via one-step hydrotreatment catalytic over PT SAPO11 by response surface methodology. It's by Xing Yong Li Let me share the screen. I think he is using the screen of Mr. Dr. Wang. Yeah, okay. Okay, yes, okay, get it done. You got 8 minutes, yeah? Please focus on the main points only, yeah? You are self-muted. Can you unmute yourself? Unmute your speaker, please. Your speaker is closed. Can you unmute your speaker? Okay, good.
Hello?
Yes, we can hear you. Go on.
Okay, thank you. Hello, everyone. It is my honor to be here for this presentation. Now, I will talk about what I'm interested in biofuel. Okay, let's begin. It is divided into 4 parts of my presentation. In the recent years, because of the depletion of fossil fuels and the growing concern about the emission of harmful gases from their contribution, which have been considered as an environmental friendly and sustainable alternative to fossil fuels, so we are looking to using renewable energy such as biofuel, which replace fossil fuel that can achieve the goal of emission reduction. Biofuel can be divided into first, second generation according to production and technology. Typically, the first generation biodiesel as fatty acid master ester is developed with transesterification from mast vegetable oils and animal fats. But this kind of biodiesel contained a high content of oxygenate compounds suffering from considerable hearing and serious drawbacks such as low heating value, and so which it ran its practical application as transpiration fuels. Fatty acid methyl ester was obtained by transesterification in our research group. The first generation biodiesel compounds were characterized by GC mass. According to the GC mass qualitative and quantitative analysis results, the main fatty acid components of FAME were methyl palmitate, methyl stearate, and methyl oleate. As a repeat, biofuels derived from oxygenation process contain high linear hydrocarbon content and little oxygen, sulfur, and nitrogen. The product with excellent physical and chemical properties, such as high certain number, great cold flow properties, and high heating value and excellent storage stability. However, the chemical utilization of second generation biofuels is underdeveloped because there are still a large number of technical obstacles needed to be overcome. At present, HVO is a high-quality bio-based hydrocarbons. The technology was divided into 3 ways: hydrogenation, active synthesis, and refining. The end product has the same composition as fossil fuels. A typical process is from UOP, Hornwell, and Nest. The hydrodeoxygenation process of second generation biofuel is divided into direct hydrodeoxygenation and hydrodeoxygenation isomerization. Direct hydrodeoxygenation is a process of deep hydrodeoxygenation of fats under high temperature and pressure over cobalt and molybdenum catalyst. Generally, it has a high certain number, but there are still restrictions on the use of it because of the poor cold flow properties. Hydrodeoxygenation isomerization is the improvement of direct hydrogenation process. After hydrogen isomerization, the alkenes not only retain high setting number, but also greatly improve the cold flow properties isomerization. Isomerization is usually carried out over platinum catalysts. Next process and the coupling process are the representative process. Catalysts play key roles in the deoxygenation process. Several kenzyl catalysts have been developed. For example, metal sulfates, supported noble metal, and supported non-noble metal at all. There are several possible reaction paths of deoxygenation reactions. First, hydrodeoxygenation is in order to remove oxygenation to form water. Next, decarbonation to form carbon oxide and water. And third, decombination to decombination groups in the fatty acids are deposed to release carbon dioxide. And other possible reactions like carbon dioxide and hydrogen to form water and more. The traditional hydrodeoxygenation process including two steps. Firstly, unsaturated fatty acid was converted to liner alkenes by hydrodeoxygenation. Next, long-chain alkenes were converted into acyl alkenes by isomerization. Why we need to achieve isomerization of hydrocarbons? Because the crude point and velocity of liner paraffin obtained from the hydrodeoxygenation process are generally higher, resulting in cold flow properties. Now, the second generation biofuel can be directly produced by one-step pretreatment process in our work. We achieve the FAME to convert the high-quality biodiesel by one-step process in fixed bed reactor. Our platinum SEPO11 catalyst. The reaction process operates hydrodeoxygenation and isomerization at the same time. Next, I will share how to prepare the catalyst. Platinum SEPO11 catalyst was synthesized with hydrothermal.
Excuse me, Mr. Lee. You need to fast track your presentation. So we have very less time for you. Okay.
Okay.
Focus on the main points. Yeah. Okay. Yeah. Thank you.
Okay. Thank you. Next is catalyst calculation. First of all, XD calculation. From this picture, we know a typical IO structure at 2 degrees at 8.1 and 22.1. It can be clearly detected, and no pink separation change can be found when platinum supported on SEPO11. Next, the chemical composition analysis was carried by XRF. It was found that SEPO11 molecular C showed a small quantity of denomination phenomenon after supporting platinum. The specific surface area, pore volume, and average pore size were obtained by BET and the T-plot calculation method from the nitrogen adsorption isomerization. The specific surface area decreased from 177 to 140. And from this picture, the shape of catalyst showed ellipsized, and it also contained the Lewis acid and bronzite acid on surface. And from team question, in this picture, platinum, a large proportion of the platinum particle size on PT7 and SEPO11 are mainly in the range of 3 to 11 nanometer. The average particle size is 9 nanometers. PY GAL character region. Desorption pinks weak acid sites and medium strength acid sites from all catalysts appeared at 115 and 350. Next, finally, operating parameters optimization. as one of the most efficient methods. A response first introduced by Boxon and Wheeling is widely adopted to investigate the coupled impact between different parameters. At this moment, we chose a central composite design. According to the design, 30 rounds of experiments were performed. The response results on the different combinations of 4 operating parameters in the biodiesel. And the regression model was calculated by ANOVA. For this table, we know the model of F value of 45.55 implies the model is insignificant. And the residues plotted approximately along straight line indicated that the errors were normally distributed. In addition, almost all the internally students, the residues were in small range near 0 to 0, meaning that the transformation of the response could provide a better analysis. For this picture, the shape of the 2D counterplate could determine a two-factor interaction significant level. We can observe the 2D counterplate shape is sure of oval, and the 3D surface plate shape is the saddle surface, means that there is a maximum value between any 2 variables. And the last, 4 process parameters were optimized by response surface methodology. The optimum conditions were found to be in this table. In order to validate the model as well as further analyze and compare with other operation parameters, verification experiment was carried out several times. The average selectivity of biodiesel alkanes were found to be 98.87% as compared to the predict, and the oxygenation rate ratio is 100%. At this condition, we will also test the mechanical stability of the catalyst. The runtime are more than 120 hours. The yield of liquid products maintained 72%. The average stability of biodiesel alkanes maintained 99%. Okay, there are some liquid products in our research group. Finally, the restructuring products were tested by Perfect Chemical Detection and Analysis Center. The products meet the diesel fuels standard indicators. In fact, some products are better than requirements of these standards. Therefore, it is a potential for production in the future. Okay, that's all. Thank you. This is our tutor, James Group, College on Energy, Xiamen University. Okay, thank you for your listening.
Thank you, Mr. Lee. If you'd like to ask any questions to Mr. Lee, please post question in the question box. Let me take out the screen. Thank you, Mr. Lee. Okay, the next is by Dr. Saurav Poddar. He's going to talk about the the presentation is upgrading of lab scale to pilot plant scale of pyrolysis using Aspen Plus. Dr. Saurav Poddar, I think you were there yesterday, so let me get to you right there. Okay, please share your screen. Are you there, Saurav? Hello. Okay, the next presentation. Let me take all my screen back so that I can get back to the. Okay. The next presentation is on the pyrolysis study of refuse derived fuel using gravimetric analysis by Mr. Mukesh Bhatt. He's a PhD scholar at the Department of Chemical Engineering at Manipal University, Jaipur. Mr. Mukesh, I'm going to ask you to share your screen. Okay.
Yes.
Okay, go ahead.
Is it visible and my voice is audible?
Voice is audible. Okay, the slide's on. Yes, okay, go ahead.
Okay,
Present it.
so
You have
thanks
8
for the
minutes.
opportunity. Yeah, sure. So here we are going for the study of refuse dried fuel. The refuse dried fuel we get from the mechanical biological treatment of municipal solid waste. And so moving on to the next, these are the contents: comparison of MSW with the RDF, TG of RDF, and it's the kinetic model which we have used, and some results, and then conclusion. So as we know that the generation of municipal solid waste is increasing day by day, and so the problem of waste management is a concern. So if you see, for that the MSW is converted to the RDF, which is refuse dried fuel. The main difference between the composition of the MSW and RDF is the organic fraction, moisture content, and the calorific value of these waste. So through the proper management of mechanical biological treatment, the refuse dried fuel is produced, which is a high combustible fraction and having good calorific value, and that can be used for other energy application, and for especially we are looking here for the pyrolysis process of RDF. So if you go for the TJ graph of RDF, we can find like there are two weight loss regions. The first weight loss region we can observe near 280 to 360. This is mainly because of the biomass content in the in the RDF. And the second weight loss region we can find there around 380 to 550. That is mainly because of the plastic components. Basically, the polypropylene, LDP are the main components of the plastics which are available in the RDF. So almost, and from the graph we can also observe that there is around 20% of char, which is mainly comprised of the inorganic components or some non-degradable components, which contributes to the 10 to 20% of RDF char. So these are the different systems. We have just oh, sorry for the interruption. Is it visible? Sorry for the inconvenience. Hello.
Go on. Yes, we can see it. Yeah.
So as we can see, there are different components of the RDF. So there are four systems: single components, binary component, ternary, and quaternary system. So in the single component, we have taken the biomass component, the mustard husk. In the binary system, we have taken polypropylene with the mustard husk as a role of plastics and biomass. In case of ternary mixture, we have kept the polypropylene along with the mustard husk and the waste papers. In quaternary mixture, we have taken LDP, polypropylene, MH, and paper. MH is a representative of biomass component here. So as we can see from the graph, there is temperature shift even from the single components. As we can see from the mustard husk graph, there is a temperature shift. There is a delay in the degradation of the volatile matters, and that has shifted in case of binary components, as we can see from there. And the main thing from here we can observe is from the quaternary mixture, the overall profile looks like the real RDF feed which we are getting from the waste treatment plant. So it resembles the basic characteristic or thermal characteristics of the RDF. So for the kinetic model, we have taken Redfern method. So we have plotted the alpha versus the T. These are the final results of the analysis. So we can see there are good resemblance in the model in the experimental values as well. So there are some other kinetic parameters which we have drawn out from the analysis. So these are some kinetic parameters which we have got for the mustard husk. The order of reaction was like 1.92, and that has gone up to 1.32 for the quaternary mixture. And here we can see there is a huge change in the activation energy due to the combination of different mixtures. So these are all the primary data which will be required for the designing of the reactor when we are going for the scale-up systems. So this is the conclusion that thermal behavior of biomass and plastics at high temperature regions were investigated through the TGA, and the main due to the structural difference of the biomass and the plastic, there was a difference in the TGA pattern also. And overall, as we have done some experimental studies on RDF, and we have got some very good results, especially for the production of some value-added chemicals. So from their point of view, the kinetic study becomes so crucial just to go for the higher scale-up processes and to know that what will be the effect of different kinetic parameters as we changes the operating conditions. So I acknowledge my supervisor, Dr. Abhishek Sharma, for helping me and providing all the opportunities, especially PYRO Asia platform. And with these remarks, I will say thank you.
Thank you, Mukesh. Appreciate that. And let's, I invite, if you have any questions to Mukesh, please post questions in the question box. And now invite Shaurav, Dr. Shaurav. Okay, I'm going to ask you to share your screen quickly. Okay, I'm giving, okay, yes, your speaker is on. Yes.
Yeah.
You have 8 minutes, yeah.
So yesterday I was just presenting the whole about this thing. So today again I had a presentation. So that presentation is about upgrading of a lab scale pyrolysis process to a pilot plant scale process, and that has been done using Aspen Plus, and then the techno-economic analysis has been carried out. So after doing that, so I will just show you the basic things. That is, just a second. Today, my presentation is as previously as before. What is the need for the research and why I am doing the pyrolysis, and then followed by the computer-aided stimulator that I have been using, resultant discussion and conclusion, and any suggestions that you can do it. So yesterday I talked about the empty oil pump bunch. So today I will be talking about the Simani Saman thing. So it is basically some kind of a seed that's getting yellowish in color after getting ripened, and it just makes dirty to the pot. So I will use this seed in the thermochemical process, because there are various other processes like thermochemical, physiochemical, and then biochemical processes. Now, why I'm using thermochemical? Because in thermochemical there is a process that is known as pyrolysis, and in this process what we can generate, that is the 3 kinds of products can be generated. That is a solid, liquid, and a gas, which is very high energy content, and then that can be used for various chemical industries. I mean to say various useful products can be generated from it. That means from waste we can just generate the product. So obviously I want to thank Professor Kaustubh Mohanty of IIT Guwahati, because he has helped me with all this modeling and also with the data that he has provided me. So in this slide, you can see the feedstock proximate and ultimate analysis that has been carried by Sir itself. So, and then the char analysis that also has been carried by Sir. So this temperature variation has been shown at 450 degrees centigrade, 500 degrees centigrade, 550, and then 600 degrees centigrade. So with that variation, I just simply carried out the whole process in an Aspen Plus. I mean to say the whole pyrolysis process can be carried out from 300 to 900 degrees centigrade, as far as I know. So now in this process, what is the thing that I carried out? I take the biomass, and the biomass contains moisture. So that biomass along with the nitrogen is mixed, and then it is sent into the dryer, where it is dried at 110 degrees centigrade, keeping the pressure at 1 bar. So after that, the moisture will be just removed from the exhaust, and then the dried biomass is being supplied, or is being you can say, send it to the pyrolyzer. So, and then in the pyrolyzer, we are going to pyrolyze this whole product at 450, then 500, and then 550 and 600 degrees centigrade. So with that, we are going to get our products, that is pyrochar, pyro oil, and pyro gas. Now, yesterday I talked about, that is your R-stoic reactor, that is the reactor stoichiometry, which is there in the Aspen Plus, and also the reactor yield. So as I had the data, as I got the data from Sir, that is, it doesn't have any kind of a stoichiometry balance, so the balancing was very difficult. So I thought of analyzing this model using R-yield reactor. So the R-yield reactor was the easy to go ahead. So I just simply calculated with the help of the R-yield, and we got the result in the lab scale. So this is 5 gram of the sample that has been carried initially by Sir. So this is a 5 gram sample. So with the rise in temperature, you can see that char is decreasing, and then the oil initially is increasing till 550. After that, there is a decrease in the oil formation. And also for the gases, it has been observed that after 550 degrees centigrade, the gas production increases. Now, keeping all these parameters constant, I just simply varied the flow rate, that is the input flow rate. So input flow rate I varied to 1 kg in order to check what is the formation of the product. And I observed that similar kind of a pattern is being observed in case of, that is the formation of the pyro products. So the first one is the formation of the pyro products, and the second one is showing you, that is the formation of the various components that are present in the pyrogas, like hydrogen, carbon monoxide, methane, then C2H4, C2H6, C3H6, C3H8, carbon dioxide, nitrogen. So these are the gases that are coming down. After doing it, what I carried out, that was the model techno-economic assessment. So this techno-economic assessment initially was done with the help of calculating all the equipment costs. So three equipment was there. One was a, you can say, to be a mixture, and the next one is your dryer, and the last one is your pyrolyzer, and some amount of condenser. So the whole total equipment cost came out to be this. And after the equipment cost, I just calculated the total fixed capital investment, which is comprising of total direct plant cost and then total indirect plant cost. So all the variations I just showed in my presentation. What are the parameters that are generally taken while calculating the techno-economic assessment. And then with that, I just calculated the total annual product cost that will be just required. So in order to generate these pyro products. So after calculating the total annual cost, I just simply calculated, that is with the help of 1.5 tons, the that is for the formation of the pyro products that I haven't shown. So for 1.5 tons day of a sample, you will see that if I just go for without any kind of a discount rate, you will see that at 2 years, I'm going to get a payback. If I give a 10% discount, I'm going to get a payback of 2.5 years. And if I give a discount of 20%, I'm going to get a payback in the 3rd year. So initially, you can understand that if I keep on varying the discount rate, my payback period is also changing. Now, I just kept the discount rate 10% and I calculate the net present value. And the net present value, I just simply calculated, that is the internal rate return. So in this year case, I got an internal rate return of 6 years. So with this, I just want to conclude that the pyro product formation, pyro oil increases till 550. After that, it decreases. Then pyro gases starts increasing after 550. And the formation of pyrochar keeps on decreasing with the increase in temperature. So pilot plant is can be just scaled up, and it can be investigated for a large scale production itself. So the techno-economic assessment was carried out for 1.5 tons per day of the sample. And it has been observed that if I give a discount rate of 10%, 0%, 10%, and 20%, So I'm going to get the paybacks for 2.5 and 3 years respectively, and the net present value with a discount rate of 10% if I carried out. So I'm going to get that is this is something around 5,000 something. I'm going to get a internal rate return percentage, that is to be your 6%. So that's all I just want to say. So now if you have any suggestions or any kind of a innovative ideas, you can just present it to me so that I can just move ahead with this project and make it to be a successful one. That's all I want to say for it.
Okay, thank you, Sharu. Guys, okay, let's if you have any question to Sarah, please post a question to the question box. Let me share the screen. Okay. Okay. Now the next speaker, I didn't see him online yet. Okay, so I'm going to skip his presentation. Okay. Now I'm going to ask Munmi to make a presentation. Let's straight to her screen.
Hello, sir.
Okay, let's share the
Is it
screen.
audible?
Yes, is audible. Can you share the screen, please?
Okay, sir.
Okay, you're on. It's on.
Right?
Yeah, yes. Okay, go ahead.
Okay, sir.
Put it in the presentation mode. Yeah.
Yes, sir. Yes, I have already given. Good evening to one and all present here. The topic of my presentation is kinetic modeling of raw and torrefied duckweed blended feedstocks for co-pyrolysis by Broido method. At the very outset, I'd like to say that the climate change and the waste management policies has resulted in mitigation of the global emissions and the carbon credit to the environment. In that case, biomass acts as a viable resource for thermochemical processes such as pyrolysis, and many such biomasses have been used, such as pine sawdust, etc. But they require land usage for their cultivation. So in that case, aquatic biomass can be used as a viable resource. In that case, algae can be used, where it acts as a viable resource for biofuel production, and also it does not require any land usage, but it requires higher mechanical harvesting for its separation and its extraction from its aqueous phase. In that case, the duckweed can be used as a viable resource because it has a high photosynthetic efficiency. It is the world's smallest angiosperms. It has got the potential for also CCS technology, and also it has it enhances it recovers from pH and the nutrient recovery rate, and also from extreme temperature conditions. So in this paper, Muradov et al. 2010, it has been reported that fast pyrolysis of duckweed in a fixed bed reactor produces various biooil products and pyrolysis gas products and biochar. But the co-pyrolysis of duckweed with low-grade Indian coal or any other fossil fuel resources has not been reported yet. And so low-grade Indian coal, it is used because it has the potential to last for another 200 to 300 years. It acts as a source of heat and power, high net value, calorific value index, and also acts as a nascent tar reforming catalyst in the form of coal char. But this process, it has to be optimized through process intensification process in a TG analyzer for its kinetics and thermodynamic study, and so that it can be used upgraded for reactor design, reactor modeling, and scale up. And also various model fitting and model free techniques are used, such as cold stratification technique, Kissinger-Kahiro-Sunose technique, or OFW technique. But in this technique, I'll be using, in this paper, I'll be using Broido method of kinetics because it gives a thermal degradation profile in different stages of the degradation or conversion process, and also assumes the reaction order as first order reaction. In this slide, it has been said that this is a material section slide where duckweed and Meghalaya coal, it can be pre-treated in a microwave reactor through dielectric heating technique under pressurized conditions and temperature 120 degrees Celsius to 150 degrees Celsius. and also residence time of 10 minutes. So it actually reduces the residence time. It helps in it is selective in process. It is production of the heat is in situ, reduces side reactions, increases the yield, increases reproducibility, minimizes the reagents consumptions, speeds the assembly or the modification of the complex metal centers, and it is automatic control. This is the thermogravimetric analyzer where the pre-treated samples and the individual coal and the ductite samples are given into a TJ DSC analyzer under the conditions of 303 to 1173 Kelvin and heating rate 10 Kelvin per minute by purging argon under 60 ml per minute flow rate at 1 bar pressure. And we get volatile gases char as co-pyrolysis products. In this slide, I directly go to the results and discussion section where 6 samples are being investigated for physicochemical characterization. In the CHNS analyzer, the oxygen weight has been calculated by received basis, and carbon it actually it is maximum in case of Meghalaya coal, but it decreases with increasing biomass blending ratio, and it is maximum in the pre-treated ductite coal and ductite blend, that is 87.4. The Venn equivalent diagram, it shows that with it gives a graphical statistical representation of the various feedstocks and its structure and its reaction profile. So with decreasing in O by atomic oxygen by carbon ratio and also decreasing atomic by H by C ratio, the feedstock shifts was lesser part. In the inference of biomass blending ratio, with figure 2 gives the TG profile of the individual and the blended feedstocks, where with increasing in where we can say that the 3 stages of thermal degradation happens, that is the moisture removal zone till 120 Kelvin, then the active pyrolytic zone, and the passive stage or the char formation stage. With increasing biomass blending ratio, we can see that the percent of the char residue decreases, and the maximum is seen in coal and the least is seen in ductite because of the high volatile matter content in the ductite and also the high volatile matter content in the various blends that we see. The maximum degradation temperature of coal is 950 Kelvin, whereas for ductite it is 570 Kelvin. The influence of torrefaction or the pre-treated sample, it gives the percent char residue in case of torrefied sample is higher than that of coal, that is 89.73%. This may be due to the low atomic O by C and the atomic H by C ratio, and also the high energy density of the sample, and also that there is a partial devolatilization, or the hemicellulose it degrades in this case in the course of torrefied blended sample, so the carbon content it increases. These are the linear regression plots that I have done for the various calculations of kinetic modeling through the Broider method technique, and the activation energy and the pre-exponential factor are calculated by the slope and the intercept of the equation. This is the kinetic modeling. We can see that with increasing fractional conversion, the activation energy for the coal, it is maximum in case of 5% conversion, then it decreases, then it increases as 90% conversion. Similarly, in case of ductite and the blended sample of coal and ductite, we see similar trend in activation energy profile. But torrefied blend, it shows increasing in activation energy profile. We get the apparent activation values for coal as 50 kilojoule per mole, ductite 28.29 kilojoule per mole. For the blended sample, it is 34.57 kilojoule per mole, and for the torrefied blended sample, it is 76.89 kilojoule per mole. Whereas for the pre-exponential factor or the collision frequency, it states what is the number of collisions happening among the molecules in per second of the reaction, or per minute of the reaction. Here I have shown in figure 6 the pre-exponential factor with respect to conversion profile, where with increase in the with increase in the conversion, we can see that the coal has got the maximum pressure factor at the 5% conversion, and it decreases slightly. That is the collision frequency between the molecules decreases. Similarly, for the duckweed and the blended sample, it is almost constant, but the torrefied sample, it increases with increase in conversion. So the conclusions here, we can say that coal duckweed blend proves to be a viable feedstock for co-pyrolysis in comparison to pyrolysis of coal and duckweed. Decrease in carbon content with increase in blending ratio, along with decrease in the char yield and increase in the gas yield. Coal has a higher activation energy of 50 kilojoule per mole, whereas duckweed has an activation energy of 28.29 kilojoule per mole. This might be due to that the duckweed has got high volatile matter content, and also the hydrogen donors, which helps in the devolatilization process. Then coal duckweed blend with 50% blend ratio has an activation energy of 34.57 kilojoule per mole when evaluated by Broido method. The torrefied blended sample due to its high carbon content has got a high activation energy of 76.89 kilojoule per mole amongst the individual and blended sample. These are the references that I have included. Thank you. Thank you, sir.
Thank you, Munmi Bhattacharya. If you have any questions to Munmi, please post questions in the question box. We'll answer. She'll address it later. Okay, let me take over my screen.
Okay.
Okay, now the next presentation is on the studies on pyrolysis of empty food bunch via conventional and microwave assisted pyrolysis techniques by Francis Prashant. Let me invite him to share his screen. Do you want to share your webcam?
No, sir. I'm actually on a limited connection, so I think
okay,
it will cause some issues.
Sure.
Yeah. Yeah. Thank you. Yeah. Good afternoon to one and all present here. My name is Francis Prashant. I'm a project scientist in the Complex Reaction Kinetics group at IIT Madras Chemical Engineering Department, which is headed by Dr. Vino. So today I'll be presenting my results on the studies of pyrolysis of palm oil palm empty fruit punch by conventional and microwave assisted pyrolysis techniques. So the outline of my presentation would be just 1 second. Yeah, so I'll be giving an introduction, going on to the experimental section, the results, and the conclusions. So yeah, so as we all know, palm oil is a very important component in the production of a lot of processed food products. It is also very cheaply and very easily available, and is produced in large quantities in mostly Southeast Asian countries like Indonesia and Malaysia. And so yeah, so as you can see, like the production of palm oil was around 75.7 million tons only in 2018 to 19. And the problem with DFP arises when like after like during the harvest. So what happens here is only 10% of the actual weight of the entire harvest is actually used to contribute to the generation of palm oil, whereas the remaining 90% is either just thrown away and or is just burnt in huge bonfires. So this agricultural residue in EFP fibers and mesocarp fibers and seeds and fronds, as in the leaves from the trees, are all just like it's a very good source of lignocellulosic biomass, and can be used to generate a good amount of value-added products and biofuels with the application of the right processes. So what we have proposed is to just initially understand the composition of the biomass, and by doing a complete characterization of the feedstock, and the use of thermochemical conversion techniques, in this case pyrolysis, to find suitable applications for the feedstock. So yeah. So these are the basic experimental processes that we have used. So we have used the a reactor known as the pyroprobe, which generates fast heating rates at 150 degrees C per second, and with set temperatures. And so we usually take around 4 milligrams of this biomass and we pyrolyze it in the reactor while giving an inert gas flow rate. And we map the kinetics by using various reaction times and measuring the mass loss at these reaction times and at these temperatures. So so that was a study on the kinetics. Coming to the analytical pyrolysis part, so samples of the EFB were taken in this eco cups, which is around here, and we used a Frontier Lab micropyrolyzer in our experiments, and we try to mimic the same conditions in all our experiments at 700 degrees Celsius. So here the heating rates go up to 500 degrees C per second with a good amount of inert gas flow, and we took 0.3 milligrams of sample and we subjected it to pyrolysis. And so the results were and then our microwave experiments, we use a higher amount of sample and like at the same conditions, and we had mixed these samples with a 9:1 ratio of the EFP fibers along with activated carbon, so that we can make sure that pyrolysis happens in a decent amount of time. So so coming to the feedstock characterization, you can see that the EFB itself contains like a very low amount of ash, but it has a good amount of oxygen. So our main aim was to reduce the amount of oxygen in our biocrude and biochar products. So as you can see, the low heating rates are generally like it renders the feedstock unsuitable for direct combustion. We also did a comparison of the treated and untreated samples of EFB, which are the ones generally used for which are generally where EFB is usually washed before it is used in your processing in plants. So these are the results where we have compared those two samples. So as you can see, so the ash content is actually pretty different over here. We have a higher amount of iron in the treated samples, so that is why you have like this red tinge. So so the results from isothermal mass loss kinetics, as we can see here, the mass loss profiles, as in like with respect to temperatures and residence times, you can see like a decelerating profile of like observed during the pyrolysis of these EFB samples. And after some time, like you can see like a constant mass loss that is happening here. And so like comparing the treated and untreated EFB samples, we saw that the treated samples generated a lower amount of char, and that was generally attributed to the lower amount of ash in the samples. From this, we had calculated the conversions, and so we had taken like around 6 different models to try and estimate the kinetic parameters like activation energy and Arrhenius factor. So the models were basically the first order models, 1D, 2D, 3D diffusion models, and geometric models like contracting cylinder and contracting sphere model, and along with the decelerating and accelerating models like your aerophile model. So, and we saw that the 3D model actually offered the best fits for to describe the fast pyrolysis kinetics of this EFB biomass, from which we had drawn the Arrhenius graph for that specific condition and calculated the respective kinetic parameters. So coming to the pyrolysis part. So we had done the analytical pyrolysis in GCMS and in FTIR of both the EFB feedstocks. So as you can see here, the comparison shows that a high amount of carboxylic acids are produced from the untreated EFP as opposed to treated EFP, which produced a higher amount of phenols. So this is basically due to the effect of the washing process, wherein your extractables like any kind of residual carboxylic acids on the surface of the biomass, which might have come out due to like compression or something, would have been washed away. And yeah, so the main component of these carboxylic acids were stearic acid and palmitic acid, which are which contribute to around 40% of palm oil. So it's only natural that we see it reflected in the EFP pyrolysis too. So yeah, yeah. Coming to the real-time FTIR analysis, yeah, we see that it validates the GCMS data by so it's basically like a reflection of the major components in the actual GCMS spectrum, wherein you have the carboxylic acid stretches and the methylene CH stretches due to the presence of long chain carboxylic acids, and also the phenol OH stretches and aromatic in plane bends due to the presence of phenols. So yeah, right. So now coming to the microwave assisted pyrolysis part. So as you can see, the yields of the treated and untreated samples did not show significant difference. So yeah, and yeah, so basically so microwave assisted pyrolysis generated a lot of gas from the samples with the low amount of biocrude or tar. Though we had dried the samples before processing, a high amount of moisture was also generated. So we had attributed this to the deoxygenation of the feedstock, which contributed to a high amount of water through dehydration reactions. Yeah. So coming to the temperature profiles, you can see that it consisted of 3 stages of the experiment. So initially it was a drying phase, wherein it slowly reached to 100, after which you have an acceleration in the temperature profiles. So during when the devolatilization of the feedstock had occurred, after which the carbonization of char, which included the high production of methane and the production of polyaromatics took place in the char component. So yeah, as you can see, there's a huge difference between the results from your analytical pyrolysis and the results from microwave assisted pyrolysis. The presence of carboxylic acids is drastically reduced, and this was mainly attributed due to the fact that due to the effects of the activated carbon, which generated hotspots within the sample, through which when the pyrolysis vapors would rise, they would undergo secondary decomposition reactions, resulting in the formation of a high amount of gas, which was seen in the char in the yields. So yeah, so due to this, phenols were the dominating compounds that were present in the bio. Yeah. So yeah, so comparing the char and the biocrude from your microwave and the fast pyrolysis experiments, you can see that the microwave char, even though it like it has a lesser amount of oxygen, it has like a lower heating value compared to that which was obtained from the analytical fast pyrolysis experiments. This is basically due to the fact that your oxygen dense molecules, as in phenols, were more in the crude that was generated from the microwave pyrolysis than the analytical fast pyrolysis, which also consisted of a lot of long chain carboxylic acids. So yeah, coming to the crude portion, you can see that a low amount of oxygen is present in the crude. This is due to the severity of the conditions that are present in the microwave assisted pyrolysis, and also the nitrogen and sulfur contents have also reduced, and this is again due to the impact of hotspots onto the to the feedstock.
Prashant, can you quickly conclude, please?
Yeah, I'm done, sir. Yeah. So yeah, in conclusion, we can say that biomass show that it was a very good feedstock, and it could be used for basically well, if the proper techniques were used in the extraction of value-added chemicals and biomass-based fuels. Yeah, and so the isothermal mass loss experiments showed that the decomposition of EFB followed a 3D diffusion model from which the activation energy and frequency factors were calculated. Yeah, so and the microwave heating was a good way to generate a high amount of phenol content in the biocrude. Yeah, that's it. Thank you.
Okay, thank you, Prashant. Okay, now we'll ask the Dr. Karthik to take over this summary about the presentations.
Okay, thank you, Parag. And yeah, I'd like to thank all short oral presenters. So first of all, I have to say that the committee could not give you a longer time. So some of you have to really skip a lot of information with this very short time, but still you have done a good job. So I'm not sure whether we have received any questions from the audience. Ram, can you confirm that part?
We don't have any questions yet. So
okay, so I just want to ask a couple of questions. So one question to Mr. Saurav. So can you please tell what kind of feedstock that you have used for this scaling studies? I'm not sure whether I missed that information during your presentation. Mr. Saurav?
Is gone. Sorry.
Okay, no problem. Okay, then I want to ask actually Francis, right? Francis, can you tell in terms of the yield? I think you mentioned that the conventional fast pyrolysis is giving the better yield, but in terms of the phenolic compounds or the formation of these aromatics was high in microwave. Was it the case? And my question is,
so generally we were not actually able to measure the yield from the conventional fast pyrolysis due to the instrumentation problems, but generally we expect a higher amount of yield in our fast pyrolysis conditions because we won't have the possibility of the secondary decomposition reactions which actually happened in microwave pyrolysis, which led to a higher yield of gas.
Okay. So yeah, so related to my actual question is, do you see any kind of synergy effect because of the heat as well as the microwave radiation? Do you see anything as a kind of synergy effect?
Okay, so synergistic effect. So synergistic effects were only due to the presence of hotspots, but otherwise the products that were evolved were basically the same as in your conventional fast pyrolysis. It was just that the secondary decomposition reactions led to the formation of other products.
Okay.
Of lighter compounds.
I see. Okay, all right. Thank you. So once again, I would like to thank all short oral presenters for being part of this symposium. And
there is one question.
Done,
sorry to interrupt, Karthik.
Yeah.
There is one question for Munmi. I think which should be asked.
Yes, sir.
Hi, Munmi. Can you
Am I audible?
Yes, you are.
Yes,
Go
sir.
ahead.
Yes, sir.
Yes, you are. Yeah.
Yes,
Please,
sir.
please read and answer. Yeah. Thank you.
So what would be the reason for high increase in activation energy at 90% conversion for torrefied sample? This might be due to that TGA has got different degradation stages. That is the moisture content removal stage, the active pyrolytic stage, and the secondary char formation stage or the passive stage. So at the final stage of the conversion, the char formation has already taken place in the sample. So it requires a high heat supply or a high energy input so that the degradation could be occurring. But so a high activation energy is required for this process.
Okay, thank you, Dr. Karthik. May I summarize this whole session? Yep. Dr. Karthik. Okay, you guys hear me all? Can you hear me, Dr. Karthik? Okay, now we go to the panel discussion session. Okay, I'd like to invite Professor Yong Sik Ok to chair this session on the panel discussion. Is on applied pyrolysis, biochar, advanced materials. So I also invite the other panelists, Dr. Masek Ondrej, and also Professor Su Xing Lam and Professor Xun Hu. Please, Professor Yok, it's all yours now.
Okay. So hello everyone. Thank you very much for attending this session during your busy schedule. I'm very happy to see still more than 50 participants survived until end of the day. And yeah, so this is for the panel discussion. So if you have any question to our plenary and keynote speakers, just feel free to let us know. And also, I would ask our distinguished speakers to give a short perspective for the overall conference. So I would ask Professor Lam to go ahead at first, and then Professor Masek Ondrej and Professor Hu Jun can give a comment. Thank you.
Okay. Thank you, Professor O. Good to see you, Professor O. Yeah. I think, I mean, our panel discussion today is about, if I'm not mistaken, is about biochar, right? So personally, I mean, I can share, what I can share is in Malaysia, we are really very active in producing biochar from oil palm waste. So, I mean, you can see now, I mean, we have a lot of palm oil mill in Malaysia. So, I mean, we produce a lot of palm oil waste from that. And one of our main groups to convert all this palm oil waste into biochar. And following the productions of this biochar, at the moment, we are using, in Malaysia, we are using the biochar just as a typical solid fuel. I mean, we just put the biochar into boiler and then use it as an energy. And other than that, now there are also, I mean, increasing efforts to convert the biochar into applications like soil remediations and also biofertilizer. I think that's something that I can, I mean, add along. So perhaps we can give a chance to other speakers to comment as well. Thank you, Professor O.
Yep, thank you very much. So yeah, now I'd like to turn over the speak to Professor Masek Ondrej. Sorry,
we can't hear you.
Your speaker. Yeah.
Professor,
can
you can hear me.
Yes. Can you hear me now?
Yeah, lovely.
Oh, okay, yes, yeah, sorry about that. Thank you very much. It's nice to see everyone. I tried to follow as many of the presentations as possible, but because of the time difference, I couldn't necessarily see everything I wanted to see. But from my observation, there has been quite a lot of interesting discussions, a lot of comparison between technologies, and especially what was of interest to me is the microwave pyrolysis and comparing to conventional pyrolysis. So it's good to see that there is a lot of work on both of those technologies. I think they both have their benefits and merits, and I think what will be interesting to see in the future is perhaps looking at some synergies between those two. And that's also just building on the work we have done some time ago. I think there is still a lot of interesting research in that area. Regarding applications of biochar, so of course, given the focus of this conference, that wasn't the primary focus of most of the presentations, but it was interesting to see a lot of mention of palm oil industry residues, including some presentations earlier today, and these being used in pyrolysis for production of fuels, chemicals, and biochar as well. And that is actually, I think, an area that really should be explored further. And I'll be happy to discuss it with the participants at the conference here, because it's again something we are working on actively as well with colleagues in Malaysia, Indonesia, and also in Colombia. Actually, as we speak, I'm preparing a proposal for a small project exactly in this area. So more than happy to discuss it with anyone who is interested. Yeah, so that will be my sort of a view of what has been presented here. Very interesting conference, and thank you for the opportunity to participate.
Thank you very much. So I'd like to turn over microphone to Professor Hu Jun.
Yes. Thanks, Professor Uga. Okay. The topic of the afternoon session is mainly about the biochar, and from my viewpoint, for the biochar, no matter you produced from pyrolysis or gasification, I think there's one product you cannot ignore, and that's bio oil. Especially in the pyrolysis, the bio oil is a major product. So in my past, in my past research, I did a lot of work about the upgrading of the bio oil, mainly to biofuel. The problem of that process is the bio oil is very easy to polymerize or to form coke. So the upgrading process about the bio oil is very difficult. So I just shifted to another research direction or another angle. Just we polymerize the bio oil to produce the bio coke. Yes, yesterday I presented the topic, our work on this research area. The main principle is we polymerize the bio oil together with the biochar. So we also get the actually we cannot call it a biochar because it contains the polymerized product of the bio oil. It's I call it bio coke. Means the property is different from the biochar because it has a higher content of oxygen, and also the pore structure is different. Actually, it does not have much pore structure. It's very dense material. So I'm still exploring its application. For the application of the biochar, we conducted the work about the use the biochar as the catalyst, for pyrolysis for gasification. Also use the biochar as a support for preparation of the catalyst for hydrogenation of the organics, and also we use it as a solvent to absorb the organics, the antibiotics. I think the main thing is we need to correlate the structure of the biochar with its performance as a solvent or as a catalyst. Also its functionalities, because the biochar, it has a lot of functional groups. We currently try to quantify the different functional groups and try to establish the relationship of functional groups with its performance. In the different applications. I would very happy to collaborate with all of you. Okay, thanks.
Okay, so thank you, Professor Hu Jun, for your comment. I just wonder, are there any comment from the audience? I just got one.
Yes, I have a question. I'm going to post on the PowerPoint. Just seconds, please.
Okay.
Here we go. Yes.
The question is specifically to Professor Lam. So, feel free to give your answer for the question.
Thank you, Professor Oak. Yes, let me just look at the questions. So what are the research direction or research questions in this area? Oh, there are a lot of questions and also a lot of things to be researched in this area. I can share a little bit. Let's say in terms of the biochar productions, of course, you can use many technologies, and definitely pyrolysis is one of the technologies to produce biochar. And I can say that pyrolysis does have its advantages in producing biochar. At the moment, we are looking at a yield of up to about 30% productions of biochar from pyrolysis process. But of course, given the opportunity, we would also like to further increase the yield and also the properties of the biochar. So that's definitely one of the questions. And with regard to the applications of the biochar, of course, I think biochar has many advantages because of its beneficial features. So, there are many applications that are yet to be explored for, that we can use the biochar. In my research team, we have been exploring the use of biochar in applications like, I think some of the experts have mentioned just now, Professor Hu have mentioned, you can use it as a catalyst of support material to make catalysts. You can use in soil remediations. Like recently, we have a team working on applying biochar in tobacco productions. Growing tobacco. So, when you add the biochar into the soil, it can, in a way, improve the soil conditions, and that will lead to a better yield and a property of the tobacco that you are getting. Those who are smoking, will know about this. And we also use biochar in nowadays. That was one potential. It can be a question as well. We are applying biochar in aquaculture applications. In growing fish and in growing shrimps. So in aquaculture applications. And also we are trying to convert the biochar into biofertilizer as well. So there are a lot of questions, a lot of potential in these areas. So I can't say the focus is only on applications, but it's also on the production technique itself. Thank you. Thank you, Professor O.
Thank you very much, Professor Lam, for your kind discussion. Just wondered, actually, the second question looked like also related with your expertise, because the panelist, the question is for how we can engineer the biochar. He's specifically asking microwave, whether microwave could help in a way to improve surface characteristics of biochar. I guess you are inventor of the vacuum microwave pyrolysis, so probably you can give a good answer for that.
Thank you. I'll just try to share some of my experience. Yes, our team. We collaborate with Professor O as well. On developing a pyrolysis process called microwave vacuum pyrolysis. And with respect to the role or the use of microwave, the influence of microwave heating in influencing the biochar, I would say yes, there are some positive effects. So when you use microwave, of course, in terms of the process itself, the pyrolysis process itself, it's faster, because if you use microwave heating, it always, it normally, not saying it always, it normally provides a fast heating. And also, there could be some interesting chemistries from the use of microwave in the productions, in the reactions process to produce the biochar. So the surface characteristics, I would say yes. Our studies have found that some of the biochar that we produce has beneficial properties, such as, for example, we can achieve a high surface area of up to 1,200 meters square per gram. So that's one of the good surface characteristics. And using microwave, we can also, try to, adjust or control the size of the pores in the biochar that we want. Like you can have more mesopores, or you can have more micropores, or you can have a mixture of meso or micropores. So definitely it can improve the surface characteristics of the biochar. Thank you, Professor O.
Thank you very much. So just wonder whether Ondreze or Professor Junho, you have any other comment on that? Or we move forward to the next question. It's up to you.
So I have a short comment if there's time for that. For both questions really, so I would just say for the first one, I would probably rephrase the statement a little bit. When it says that production of biochar is a mature technology, I would say that the technology that can produce biochar is mature. That doesn't necessarily mean that production of biochar as such is mature, because and especially when it comes to engineered biochar production. To the second point, I mean, there are so many different ways how biochar can be engineered. It can be pre-treatment of the biomass that goes in. It can be blending of biomass with additives, is the conversion process itself, and then of course there is the post-treatment as well. So that can be chemical, physical activation, and so on. So there are many different ways how engineered biochar can be produced.
Thank you. So we will move on to the next questions. Yeah, so next question actually, let me read it and we could probably share our perspective together. So quality of biochar varies depending on feedstock. Some biochar contain heavy metals or harmful component. How can the biochar be used for high-end product like it must be the supercompensator, right? Supercompensator or medical device. If the quality of biochar cannot be guaranteed, is there any way to purify the biochar at industry level? I think probably, I'm pretty sure Professor Macek Ondreje, you may have pretty good comment on that, but just I will start at first. Yes, of course, the quality of biochar varies depending on the feedstock. As you mentioned, if we're gonna collect cellulosic biomass specifically near the mining area, then potentially the feedstock containing relatively large amount of trace element like copper and zinc. In that case, even though you do the pyrolysis, the product, the biochar itself may contain relatively higher amount of metals there. Because of the impurity, we may not use it for the medical purpose, for instance. But in terms of supercompensator, I think porosity is one of the most important aspects upon my understanding. I have a publication that using oak wood into the supercompensator. In that particular study, we found that the pore structure of the wood might be the most relevant that can be used for the supercompensator. But in my opinion, in general, forest ecosystem, if it's not near the mining area, generally those oak wood in a natural forest ecosystem do not contain high amount of toxic metals if the soil is not contaminated. So I don't think there's any issue that we use wood from a natural ecosystem, right? So that's fine. But if we are looking for the other contaminant like a PAH, polycyclic aromatic hydrocarbon, probably PAH can be a problem during the production process. But I'm not sure for the many other cases, but at least in our case, we had a big pyrolyzer, but the produced biochar contained relatively high amount of PAH. So by purging with carbon dioxide rather than nitrogen, for instance, in that case, we found that the PAH is completely degraded during the pyrolysis or gasification process. So changing a purging gas could be one of the solutions to remove the PAH. But of course, that's the feedstock specific, or could be different depending on the scale of your plant. So that's my brief answer for the question. Just wonder whether Professor Hu-Jun or Professor Macek Ondreje, you can add any comment on that? Or Professor Lam? Yeah, anyone?
Yeah, so I will just add a few things. So, I mean, there is no reason why the quality of biochar couldn't be guaranteed. It all comes down to the selection of the feedstock and, as you said, also the processing, because heavy metals will be coming mainly from the feedstock. It's possible to introduce them during the production process as well, as we have shown in one of our previous published papers, but that's a minor issue. And so it really comes to selecting, depending on the application. If it's something for a medical application or for food applications, we need to be very careful about what feedstock is used in the pyrolysis process or in the conversion process. And it's also possible to do post-treatment to remove metals, but it's much better to avoid their presence in the feedstock. Regarding other contaminants, so pHs or dioxins, furans, and so on, this really comes down to the process itself. And again, we've shown in our past research that actually in the same unit, just by changing the operating conditions a little bit, you can produce a very contaminated biochar or a perfectly clean biochar. So it really comes down to how the process is designed and run. And as Professor Ock mentioned, the use of different carrier gases can also help a lot for specific cases. So yeah, there is no reason why biochar quality can't be guaranteed, but it needs to be sort of let's say designed in already into the process when it's when you're deciding on what you are using the biochar for and how you are going to be producing it.
Okay, so hope that was pretty helpful to address the question. Any additional comment from Professor Lam or Professor Hu?
Okay.
Perhaps we'll let Professor Hu to share some of his opinion. Thank you.
Okay. Thanks a lot. I think in the past, when I was working in Curtin, we tried to use the biochar for the soil improvement. We at that time we worried about some phenolics may still remain in that biochar, so we did the leaching experiments. I remember that we did the experiment for a very long time. I mean, in the unit of days to weeks. The result is that the phenolics, I mean, it's very difficult to be leached completely or quickly. It's just I forgot the data. I didn't publish that paper. Just I think after weeks, still some trace amount of the phenolics was leached. So the phenolics is not good. I think not good to the living creature in the soil. So yeah, we did that experiment. I mean, yeah, the phenolics can be an issue in the biochar. For the heavy metals, it depends on the use of that biochar. If it's for adsorption, possibly some metals can be leached in the reaction medium in the solution. And if we use it for adsorption of the gas, I think it shouldn't be an issue. But it depends on how do you dispose the biochar, the use the biochar. Yeah, it's the heavy metals. It also depends on what's the type of the heavy metals, and if you use it as the catalyst and the support of the catalyst, it really depends on the specific reaction. Some heavy metals even can be beneficial additives for the catalyst. I mean, some are not. I mean, this really depends on the specific purpose of the use of the biochar. Yeah, that's something I want to add. Okay, thanks.
Thank you so much. Okay, so now we will move to the next question. It looked like quite new. How do we use artificial intelligence in the area of biochar or pyrolysis? Do you have any comment on that? How we use artificial intelligence in our field?
Yes, let me, I can share some idea, if I may.
Okay.
Professor.
Sure.
We recently also have a team to work on, this, but just a very preliminary research. We try to incorporate, we don't call it artificial intelligence, but we are trying to develop a novel hybrid intelligent approach to, to promote the applications of pyrolysis in biorefinery. So what we did is we used this hybrid intelligent approach to determine the chemical exergy of the pyrolysis process. So, I mean, once we determine and we can estimate the chemical exergy of this process, we can use it to optimize the pyrolysis process, like reducing the amount of the energy that unnecessarily spent in some aspects, and also to estimate and improve the yield and the properties of the desired products that we are targeting. So yeah, we have started some research on that. Yeah, if I may just add on that. Thank you, Professor Oak.
Yeah, that sounds very interesting. Please let me join.
You are more than welcome.
Yeah. I'm not so sure particularly for using artificial intelligence, but as just Professor Lam mentioned, I can talk about machine learning. As you may know, the machine learning could be prepared to resolve the problem through modeling and running the specifically for the absorption behavior of contaminant onto biochar. So the first step could be the build and train high quality model to accurately predict the absorption efficiency. As you know, during the past several decades, a lot of empirical models such as Rangmia and Freundlich model employed to describe the absorption equilibrium for many decades, but they could hardly draw any prediction conclusion, and the relationship between absorption result and operation condition was also unavailable. To overcome that, we've been developing surface complexation model, as you know, but the surface complexation modeling need highly advanced equipment. So it's not that easy for us to conduct experiment. So based on that theory, the emerging machine learning model, specifically random forest or artificial neural network, or there are many other models, they have been very successfully demonstrated to have the ability to model and predict complex and non-linear mathematical relationship between independent and dependent variable of contaminant in the biochar. So I have collaboration with Professor Shannon Wang, who is an expert in artificial intelligence at National University of Singapore. And we've been continuously publishing a few papers on application of machine learning in the field of biochar. Up to now, very new paper have been published in 2 journals very recently, and a few paper is currently under review or will be submitted soon. So probably some of the participants could check that paper that provide a bit more specific example, not for the whole AI application to the biochar, but specifically for interpreting contaminant absorption to the biochar. And that's for my whole comment. And we can see the next one to Professor Macek Ondreze. You have your specific question from the audience. What are the level of production in biochar in Europe compared to the rest of the world, like Asia and China?
Okay, that's a very good question. Difficult answer to that. So in Europe, I would say certainly compared to countries like China or elsewhere in Asia, I would say the production is on a smaller scale, both in terms of the sort of overall capacity, but also in terms of the individual units. So these tend to be smaller to medium scale at best. There are, to my knowledge, no large-scale pyrolysis plants. It's been quite interesting to see the development over the past years, that a number of other sort of technology providers have started to offer units on the market. So there is a more diversity in terms of options for technology. So I think we will see more and more development very soon. There is also now, for example, specifically in the UK, there is a lot of support, or well, a lot of interest and also support for greenhouse gas removal technologies in terms of financial support. So I think we are likely to see in a very near future a more wider deployment of biochar production technologies. Again, most likely on the smaller to medium scale, because of the geography and the availability of feedstocks, where logistics does not necessarily yield itself to very large scale plants, but certainly the much wider scale of deployment of those smaller to medium sized units. And I see there is a second part of the question as well related to nutrients. Do you want me to answer that as well, or? So,
yes.
Yeah,
so
okay.
Thank you for the comment. There are one more question. What is the best optimized method to produce biochar? Is there any method which can convert any plastic waste into biochar? So I guess you have experience converting plastic waste into biochar, right? As far as I know,
yes,
you worked on that. Yeah.
Yes. Well, as I see the question, so well, this is to be asking about pure plastic rather than mixture of biomass and plastic, both of which are an option. So regarding conversion of plastic to biochar, it will very much depend on the type of plastic, if it's a single type or mixed. Some plastic does not yield any biochar at all, so you can't say that it's possible to convert plastic into biochar. It very much depends on what it is. You might be getting wax and gases rather than any solid char residue. For certain types. When it comes to conversion of mixtures of different plastics or biomass and plastics, then there are all sort of additional synergistic or antagonistic effects that can happen during the process that affect both the yield and also the properties of the biochar. So there isn't a single answer to that. Yes, it's possible to convert feedstock that is purely plastic or contains plastic into biochar. Under some conditions, under others it's not. So it very much depends on the nature of the plastic.
Thank you. So I got a few emails that actually the Pyro Asia is supposed to be finished at 8 p.m. but there was a significant delay. And as you know, right after our session, there will be the announcement for Young Research Award. And then next Pyro Asia conference, they're going to be held in next year. So as I know, the time is quite late, but hope all the attendants will remain for the next 30 minutes. We can celebrate each other by opening the video. We can meet all together. So before closing, I'd like to just ask just 1 minute for each panelist that sharing their future work or current research focus, so that we can be engaged in, and if anyone interested in, you could potentially contact our panelists, start collaboration. So could we start from Professor Hu? Yeah. Jun Hu? Yeah.
Yes.
Yeah, could you just share what is your current focus of your research in this area, and any perspective or any your future plan?
Oh yes, yes. Thanks, Professor. Actually, I want to introduce from my PhD study. From my PhD study, my research topic is catalysis. Specifically, it is slim reforming of the small organic molecules like methanol and ethanol to produce hydrogen. My main work to develop the catalyst, the transition metal-based catalyst for the production of hydrogen. Then I went to Australia, Curtin University in Australia from 2010. And there, from that time, I started to do the conversion of the biomass via the pyrolysis. Also, with my focus on the conversion, the utilization of the bio oil. We did the acidification of the bio oil, try to upgrade its properties, and we also do the hydrotreatment of the bio oil, try to reduce the oxygen content in the bio oil. I mean, to increase its heating value and to increase its thermostability, to be used as the biofuel with the desirable properties. And then also I did some research about the conversion of the major component in the bio oil. For example, the conversion of the sugars, the glucose, the xylose to some platform chemicals such as fluorolevulinic acid, try to just make something valuable from the bio oil. And when I come back in 2016, and I started to do the pyrolysis. The focus of my research is actually is in addition to the bio oil, analysis the bio oil is the biochar. So I want to just mix the biochar, just make something from biochar. So focus on the application of the biochar. I think one special thing I have done for the pyrolysis is we use the in situ FTR. We call it the drifts. The drifts to characterize the pyrolysis process. We want to see the change of the functionalities of the biochar and the different conditions, different temperatures, different atmospheres. So we try to understand the evaluation of the functionalities, and so you can tailor the functionality of the biochar, and just try to correlate the functionalities with its performance in some specific applications. For me, I think the major thing for the application of biochar is the cost, because in China I know that to obtain the biomass, I mean from the farmland to the factory, typically, for example, it's the sawdust is 400 RMB per ton. So when you produce the biochar, so you do the pyrolysis, you got around 30% of the yield. So, and you can sell the biochar. There is a market in China. The market value of the biochar is around 1,500 per ton of the biochar. So the cost, actually the cost of the feedstock account I think a big portion of the overall cost of the biochar you produced. So the yield of biochar is too low actually. It's just 30% from the fast pyrolysis. So kind of my research is I want to just enhance the yield of the biochar. I've tried to achieve 50 to 60% to reduce the cost. So the technology can be applicable in the industrial level. For the biochar, I also do a lot of characterizations to to see the possibility of use of different biochar as the solid fuel for the barbecue, and also for the absorption for the use as a catalyst. So had a lot of collaboration with Professor Oak. We try to advance our research in this area. So the focus is biochar. And just one thing I want to add is we also do the use of biochar as the catalyst for the electrochemistry, for the use as the capacitors, for the OR reactions, that's something like this. Okay, thanks.
Thank you. And then now we could ask Professor Lam. Specifically, I saw. You have invented the vacuum microwave pyrolysis for quite some time ago, and I see very recently you've been publishing a lot of very high quality papers. I just wonder what will be your future research direction for at least for the next 5 years? I'm quite curious, so just share with your idea with us.
Thank you, Professor Oak. I'll just try to make it short because I think most of the interesting future areas has been covered by Professor Hu. Okay, so to me, I'm very much interested in the pyrolysis technique, and then the applications of the pyrolysis products. So with respect to the pyrolysis technique itself, I'm very much into microwave. I like microwave, so I like to promote the use of microwave. So anything on microwave pyrolysis, I'm very much interested. And currently, we are still continue to develop the microwave vacuum pyrolysis. Other than that, we are also exploring CO2 pyrolysis, and we are also exploring cold pyrolysis, and also self-purging pyrolysis. So we are trying to use different techniques to improve the technology of the pyrolysis itself. So that's one. And secondly, with respect to the applications of the pyrolysis products, you have bio oil, you have biogas, and also the biochar. So with respect to these three products, we are trying to maximize the applications of these products into just basically in different applications. So I'm more than welcome to collaborate with those of you who really like to go into this area. Thank you.
Okay, so thank you very much. And Professor Masegondreze.
Yes, so plans for next 5 years. I don't think we have enough time for cover all that. So I'll restrict it just to add a few things that have not yet been mentioned. There are a lot of very good areas that have been mentioned both by Professor Xunhu and Professor Lam. And so one thing that we are also intensively investigating and will be into the future is a combination or synergies between thermochemical and biochemical conversion processes. As an example, combination of anaerobic digestion and pyrolysis. There are a number of different ways how these two processes can work together in a synergy to obtain or to maximize the value from the biomass feedstock that's being used. Another thing is, a lot of different areas related to engineered biochar, so really sort of tuning or designing biochar for specific applications, and also what I presented at this conference, the sequential uses of biochar, so really identifying synergistic sequences where we can use biochar in a series of steps. And related to that really is so things like maximizing the yield that was mentioned by Professor Hu. And that can be achieved by tuning the technology, but also we've been heavily investigating use of various additives that can increase the yield of biochar, but also they can improve other properties. So we are actually solving two problems at the same time. We get more biochar, meaning more carbon sequestration, but we also get a better biochar, so it performs better in the application we select. And a lot of our applications focus on environmental management. So that can be treatment of drinking water or wastewater. It can be related to contaminated soils. A lot of current work is also related to improve the retention of water in soils. And these are things that will continue into the future because these are all very important for not only environmental quality, but also for climate change related issues of climate change adaptation. So of course we are trying to mitigate it by sequestering carbon, but we are also trying to find solutions that will help us adapting to inevitable changes that will happen. So yes, there are a lot of different areas in the environmental section, and then also use of biochar in material engineering and construction. So things like sensors, but also additives or as the components in construction materials, whether it's concrete or interior so components of buildings. So many different applications that we don't have the time to go into, but more than happy to discuss it with anyone on the panel or in the audience.
Right. Thank you. So lastly, also, I'd like to shortly talk about my future research direction. The next year will be exactly 10th year anniversary of my center. It's Korea Biochar Research Center, officially launched in 2011, and we've been organizing international conference since 2011. And next year is the 10th anniversary. So I'm very happy to announce that next year, right after the Nature Conference, I'm going to host PYRO Asia 2021 in Seoul. And at the moment, I hope all of you can join, and we meet together and talk about many issues. Right. So my opinion, last year, myself and all my group, we've been visiting Brisbane in Australia. Reason is that we'd like to visit the first Nature Conference organized by Nature that was held in Brisbane at the QUT. I went there at time to talk with editor of Nature Protocol and Nature Method. As you know, I aim to publish a paper in a Nature Protocol or Nature Method for standard biochar or engineered biochar, because so many people produce engineered biochar for many different purposes. But you know, synthetic method is totally different depending on scientist it's quite difficult to have a standard recipe. This year, together with my collaborator in Australia, I was able to publish one paper in Nature Protocol, and that's for the specific method for produce certain material. Any scientist can follow that protocol, and we can produce and synthesize the same material. Data are comparable. So I'm interested in AI, artificial intelligence based computation plus guided experimental synthesis. Guided experimental synthesis is the new age science and will be very hot trend in material science or any scientific area for next 5 years. This terminology, as for such work, is called digital library or synthesis 4.0. So I think we should make the maximum out of it to produce quality controlled, guided experimental synthesis of designer or engineered biochar for next few years. So that's what I'm aiming to do. And thank you very much. So now this is the end of our panel discussion. So hope our discussion was fruitful to all of you, and thank you very much for giving so many questions to us. We couldn't answer for all the questions, but I see a few more questions related with construction material and so on. Sorry, the Kartik now came, which means he needs to start concluding of this conference. So we will close the session. Thank you very much. Thank you, Master Gondreje. Thank you, Professor Junho, and thank you, Professor Lam. Thank you very much.
Thank you.
You can stay, and later we meet again through the Zoom, all together with the participants. Thank you.
Yeah, so thank you, Professor Oak, and also the panel members. We really appreciate your the kind of the active, the dynamic discussion that we had. And as we understand that we still have a lot of questions, so these questions we try to send it across by email, and so we can still continue our interaction through the email. So also on behalf of the technical committee, I would like to thank you all for taking your time to be part of this PYRO Asia 2020 e-Symposium, and really added value to the technical content of the program. So now we will move on to the last part of the conference, okay? That is basically a validatory function. So I would like to request a couple of other panelists like Professor Yoshiaka and also Professor Thalada Bhaskar. Okay, so if you're online, please turn on your camera so that we can see you. So just want to briefly talk about the forum and the forum mission. Okay, so the last year only we had a kind of thought about establishing this PYRO Asia forum. The reason being is basically to promote the pyrolysis related activities or research in the region, because I was following the Pyro International Conference, and the participation from Asia is very much limited. Particularly, I see some researchers from Korea, Japan, and China. Other parts of the country, they are not really participating. It could be because of the financial constraints or not much activity happening. So this forum at least kind of creates some kind of awareness and create interest for some of the new researchers, when they may be thinking, what is the area that I can work for my future? Then at least if she see some potential on this topic, they can really grab on it and continue. This forum definitely work towards that. That is one thing. And we also want to really provide forum, a kind of platform for people to showcase their research so that the young researchers can learn from them. Also, it provides opportunity for any kind of collaboration. And the third part is, when you want to really promote, we also have to give some kind of recognition, right? So that's why we thought about this Young Research Awards. So that's something that later Prof. Oak will talk about. So before going to the Young Research Award part, I would like to request Professor Yoshiaka and maybe since Thalada Bhaskar, I'm not sure whether he is online, maybe as a guest speaker, Professor Masak Andrej also can give some kind of reflection. So I request Professor Yoshiaka to say a few words about your experience on these last 3 days. Professor Yoshiaka, over to you.
Yeah, thank you very much for introducing to me. And dear all of the participants, it was a 3-day holiday conference, and thank you for your participation in this conference. And we would also like to express our deeply gratitude to Frontier Laboratories Japan, and CDS Analytical, and the USA, and the JO Ltd Japan, and the SD Labo Forum as a sponsor of this conference. And then the Param and the other Technobiz for their logistical support. It was the first online conference in the COVID-19, but I think we were able to exchange opinions and share the information in the in a very meaningful way. Since it was targeted at Asia, the time difference is not a bigger barrier, but it may have been slightly irregular, right? By all means, I'd like to look forward to the next meeting being held face-to-face. However, since each researcher has a problem with fund, it will be necessary to continuously and flexibility to manage the way the meeting should be, including the idea that one online is effective logistic. Also, the presentation from many students were a welcome action for the future development of this field. We hope that even the student who did not win the award this time will be prepared for the next opportunity. Now the field of the pyrolysis has become a very active area these days. The topic also covered a great many topics, such as the recent trend and the advancement in the analytical field, biomass plastics, biofuels, biochar, and biocarbon, etc. in applied field. At the same time, the increasing the number of the submission of the related paper indicated that activity in this area is increasing. Because Asia is becoming more important and hot worldwide, I hope that PYRO Asia will continue to be held on. And finally, we would like to give a big appreciation to Dr. Katik, Frontier Laboratories, for his great contribution to leadership that made this conference so powerful. Thank you very much.
Okay, thank you, Professor Yoshiyaka, for your nice words. Since I don't see Professor Bhaskar online, may I request Professor Wok to say a few words about the conference, then you can further talk about the Young Research Award part. Thank you.
Yeah, sure. Thank you very much for attending this conference during the past 3 days. I've been observing there are a lot of high quality presentation, not just coming from our plenary and keynote, but from young scientists. And at this particular event, though it was online conference, I'd like to deeply appreciate to Katik and Technobiz. The overall organization was pretty good in my opinion. Though the time was almost 6 hours per day, but everyone attended continuously, at least 60 to 80 participants per day. That was quite good by considering this pandemic situation. And yeah, so let me talk about the award, then I will skip for the others because time is quite late. So I do not like the continue for my talk. Later, I will directly talk about the award. So could you give authority so that I can share the monitor?
Just a second, sir. Just a second. Let me I
Yes,
have added
yes,
lots
yes.
of lots of people as a part of the panelist. Okay, so
Sure.
yeah,
Yep. Can you see?
yes.
Good. So as you see here, Pyro Asia Forum during the Pyro Asia 2020, we had the review committee. So the Professor Shogo Kumagai in Japan and myself in Korea, Professor Jipeng Jang, Korea, and Professor Ashad Salema in Malaysia. We served as reviewing committee for this Pyro Asia, and we got a quite number of applicants. And yeah, so I just want to announce the Young Scientist Award. Actually, I've been hosting Micro 2020 just a few months ago. And in the conference, when we provide award, everyone actually connected through the Zoom. That was more than 200 people joined and drinking and celebrating after this conference, continuously chatting. That was unforgettable moment. Among almost 200 people, I was the only Asian. So, yeah. Anyway, let me introduce the first is the Dr. Xiaoyang.
Professor, no, definitely.
Can you see it? Yeah. So it's Dr. Xiaoyang.
Yes, we can see it.
Yeah, Dr. Xiaoyang, congratulations. So Dr. Xiaoyang is currently an assistant professor at Institute of Geographic Science and Natural Resources Research, Chinese Academy of Science in China. Deep congratulations. And one more, next. Congratulations, Dr. Chong Tung Chong, Associate Professor at Shanghai Jiao Tong University in China. Congratulations. And Dr. Chong Ma is JSPS Fellow at Tohoku University in Japan. I remember he made a very good presentation yesterday. Yeah, congratulations. And we just have two more. Is Dr. Ali El Nagar, who is a postdoc fellow at Zhejiang ANF University in China. Congratulations. And then last is Dr. Babia Krishna. So congratulations for your award. So yeah, so that's the end of 5 awardee for this Pyro Asia Young Research Award. As far as I know, our conference organizer soon provide official certificate for the award together with some honorarium. So that's gonna be announced by Kartik through the email after this event. Thank you again for your application. I'm deeply congratulations for your award. Congratulations. So let me.
Also, I would like to thank all the reviewing committee members. Yeah.
Right.
Yeah. Sorry.
So,
please. Continue. Sorry to interrupt. Yeah. Please continue.
Oh yeah, I'm just done. So can I announce for the next event later, right? Or just now, or?
Yeah. Yeah. That's all. No. Maybe we can announce later. I just want to add a few more comments. Then we can. Yeah.
Sure.
Yeah, so I would like to thank the reviewing committee who has spent a lot of time reviewing all these applications. And as you know, all applicants are very young and energetic, and they have done a lot of work. And the committee felt, because we do not want to differentiate one is better than other by a marginal difference. So what they thought, because this is a recognition that will motivate the young researchers to progress further in or advance in their research, also something it's important in their professional career. So keeping those facts in mind, the committee unanimously come up with the idea to give the award to top 5 people. Okay, so that way everybody agreed to this idea, and that's how we are sharing. And definitely, I'm sure most of the winners are not really looking at the money part, but it's more of the recognition for the work that you have done. So once again, on behalf of the committee, I would like to congratulate all winners, and we wish you to continue your research to progress or advance in your research as well as the professional career. Okay, you all may remember about the best oral paper award also. So something that we are not able to announce today because we have to get some feedback from the panel members. So this is something we will announce through email. Okay, so through the all participants, so you all know. So we wish to give 2 best poster awards. Okay, that's mostly we will consider the PhD students. That's one way. But again, so we have to get some kind of consensus from the committee so that we are all in same page. So this will be announced later. And another thing is, okay, like Prof. Oak was saying in his previous event, this Micro 2018, they were celebrating. Okay, so we also want to do some kind of celebration for this award. So we would like to organize as a award ceremony, basically where we will invite these winners to give a short presentation, and we'll think of what else we can do to really bring the celebration mood. Okay, this will be announced through the email to the all forum members, including the winners. So that is on the Young Research Award part. And for the best oral paper, we will announce through email. At least we will choose 2 winners for this. And so, like Professor Yoshiaka mentioned, whoever is not got it this time, definitely you are waiting for the next one or better one. So we have to continue our activity, and the recognition will come now or later. Okay, so congratulations to the winners again. Now I would like to request Prof. Oak to really announce that the next year conference, we hope the pandemic will really, the dust will get settled soon, and we look forward to a physical conference, which is something important, I feel. Okay, so let's hope that we are able to see face to face during next conference. And I'm happy to announce that Dr. Prof. Oak has really expressed interest to do that. So I will let Prof. Oak to talk about that. Yeah. Okay.
Right. Thank you very much. So
yeah,
let me share my. Thank you. So just wonder, can you see my screen?
We do, yeah, we do see, yeah.
Yeah, so this is for a short announcement for the PYRO Asia 2021. So basically the PYRO Asia, together with all the reading group in Japan and China and Korea, Malaysia, and a lot of most of the Asian countries and India and so on. So we all want to meet somehow face to face. But as just mentioned, this pandemic is a bit quite unclear. So I was talking with my colleagues and tried to put the best date. Then up to now, as you know, the London, the Nature, the London, they said end of October, face-to-face conference might be possible. Of course, they can be delayed, but as predicted by the leading scientists all over the world, possibly they think end of October might be good for traveling. So I was deciding the date, continuing together with the Nature conference right after. This topic is for the waste management, so PYRO Asia participant could attend both if interested in. So they're gonna be end of October to early November 2021. And this photo shows our conference venue. And all the logistic we'll discuss again with our committees and Katik, so that all the participants who is observing this online conference now could potentially join. Of course, this year I've been organizing many hybrid conference or online conference. If things not cleared, we can definitely consider hybrid type conference. Hybrid, either face-to-face, might be the best choice for the next year. And as far as I know, 2022 will be held in China. So thank you very much. I'll provide more information later through the email. Thank you.
Okay, thank you, Prof. Oak. So yeah, we are really looking forward to this 2021 conference, and I'm sure, like me, everybody can try to maximize or justify our travel to Seoul by attending both the nature conference and this. So definitely we will plan in that way. Okay, now I just have to do the last part of the event, which is basically the vote of thanks. So firstly and foremost, I would like to first thank our friend, okay, Mr. Pram Prasad Rao, who has been really instrumental in doing this virtual symposium seamless. Okay, so we have actually considered him as a partner, and he justified that role, and he was really into the conference, and he was enjoying himself, and he has really taken the ownership, okay, just to show that it's not I'm providing service or anything. So it's really a conference that we have organized jointly. So on behalf of the committee, I would like to thank Mr. Param, and we definitely like wish to work together with you in our future kind of programs also, whether it is virtual or physical. So we will keep in touch. And so on behalf of the committee, I would like to again express our sincere thanks to you and also the background staff who may be helping you at the back. Okay, so that's the first thing. And secondly, yes, because we have not put very big conference participation money. So some of the money we had to get from the industrial vendors. And in this regard, I would like to thank our sponsor, Frontier Lab, CDS Analytical, Geol, also the Singapore Forum, okay, for giving us this sponsorship, okay, to keep the financial part manageable for this conference. Then I would like to thank, on behalf of the committee, all speakers, okay, who have actually contributed, like a plenary lecture, invited talk, keynote speakers, and also the panel members. Everybody has accepted when we have invited them. So that's something important, because you need to have a very good technical content for any conference. And here, even though we do not have a number in big, but like Prof. Oak said, we have the quality audience, because we have been seeing 50 to 60 participants throughout the 3 days. You know, that's something definitely a good thing, because so I really appreciate that the kind of interest that the audience have shown to keep the conference live. You know, it's important, because when a speaker speaks, even though we are speaking in front of the monitor, at least this attendees number gives some kind of motivation for the speakers. And you all have been very good audience, because it's important to have some interaction. So we were not short of questions for any Q&A sessions. So we only have to omit or ignore some of the questions because of the time. So otherwise, it was a very good interaction and deliberation. Okay, so finally, like Prof. Oak said, we can have a kind of group picture. So, but in this platform, we cannot allow all members to turn on their camera, only the panelists. But Mr. Param has tried his best to maximize the number of panelists. So whoever can turn on your webcam, please do that. Then we will have some screenshot that we will share with everybody. Okay, so all panelists can turn on your camera. Okay.
I have included many of the participants as well. Please turn on your webcams. Yeah.
Yeah. So at least whoever is possible to do that, please do that. Yeah.
Yeah, I tried
it will be a nice memory for this virtual event.
Really good.
If you have webcams, turn on. Yeah, it's good.
Okay, don't be shy. So whoever can start, please do it.
Hello, Ali. Congratulations.
Hi. Okay, so we will wait for a few more minutes. Maybe some of them, they are looking for the icon, the camera icon. Okay, Param, you'll be taking some screenshot. I will also do it from my side.
Okay, just a second. Okay.
Yeah, so let's wait a couple more minutes. Okay. Okay, in terms of the winner, we see only Ali Nagar, so others we are not able to see. Okay, Dr. Siti Chong also is here, so at least you can raise your hands.
Yeah, congratulations.
Yeah, congratulations. Yeah, and okay. So who else is online?
Thank you, Pyro
Okay,
Asia. Thanks for the award. Thanks, Karthik.
Okay. Yeah, so let's have some screenshot so everybody can have it in their own laptop also, but later we will share it also. Okay. And okay. So Param, do you want to share some of your experience? Definitely, we have given a lot of hot time for you. So maybe I will let you speak a couple of minutes.
And can you show your face? Just wonder. I never met you. So
who you are? We have only seen your picture. Okay.
Okay. Guys, if you have any webcams, I'm keep on adding some more. If you have webcams, you can turn on. Some I cannot add because the device you have, but okay.
Yeah, you can do for yours as well.
Sure.
Yeah, please turn on your camera.
Okay, all good. Okay, I think that also I have. I try to move as many as possible.
Hello, Professor Xiao Yang. Congratulations. Well done.
Oh, Xiao Yang is
Hello,
there.
Professor.
Congratulations. Okay, Dr. Bhavya Krishna also online. Dr. Bhavya, congratulations.
Thank you, sir. Thank you.
Yeah.
Okay.
Yeah. So, Param, we are waiting for your camera.
Right.
My camera is difficult right now, so let it go. Yeah. Okay.
Okay. All right. Dr. Ma also is there. Congratulations, Dr. Ma.
Thank you.
Oh, congratulations.
Something around.
Well done.
Okay, so Param, probably you can speak a couple of minutes, then we can end the session. So.
Okay, guys, thank you very much. I'm hoping that you found this event is valuable to you. What's important is any event it's about networking and the knowledge sharing and the knowledge gaining. Okay, so I'm sure with all these experts, keynote experts and young researcher, what I like is always about young people. Old people already they'll know a lot. Okay, it's a time for us young people to move forward with interesting research. I think I'm hoping that you find it this whole event is useful. So and all the again Dr. Karthik, I appreciate letting me in as a part of this program. I enjoyed it as even you don't see me online, but I know how it works system. Thank you very much for being part of this Pyro Asia 2020. Let's this discussion continue and make sure that you guys whatever you learn, share it forward. You have an opportunity to learn from these people, professors from across the world. What's important is sharing to others, your colleagues, your friends, your juniors or seniors. Then only you can keep that, you can retain the knowledge a long time. Otherwise, what you learn today, tomorrow it disappears. We have a short memory. Okay, so please continue sharing it. Okay, thank you all for joining this whole event, and I think that's the end of my talk. Yeah, thank you.
Thank you.
Yeah, so before closing, I would like to say a couple of things. So we will upload all abstracts. Okay, we will compile everything as a kind of conference proceedings. Then we will upload to the website, so everybody who is interested can download. Similarly, we will upload the presentation PPT file as a PDF for all talks. Okay, again, we do not want to fill your inbox. Okay, so we will put into our website. It's up to you. Okay, if you are really interested to like look back some of the talks or the content of any presenter, please feel free to visit the website and you can download that anytime. Okay, so with that, I would like to thank you all and have a nice break, because much needed break. It's just a 3 intensive days, and sitting in front of computer is something not easy, but still we all have done it and we are still alive. Okay, so
Karthik,
good.
One thing.
Thank you.
Karthik.
Yeah, go, Mr. Dr. Ashok. Yeah, go on.
Yeah, actually, some speakers were asking for the certificate, presentation certificate. Is it possible to give certificate for the presenters?
Yes, yes, we will give the participation certificate and the oral presenter certificate for the people, so who need it. So again, they can put a request to the email so that we can send it, because we do not want to send just like as a formality. So if they really need, if they think that will add value to their kind of database, definitely we will be happy to send that. Okay,
perfect. Thank you very much.
So if no further question from anybody, okay, before I close, actually one thing I wanted, but I want a couple of audience, like to speak on this symposium, because we as the organizer and also the plenary speakers, people have spoken, but somebody from the audience side, so as a, so can I request a couple of them to maybe you can send a message first, or you can raise your hand so that we know who is speaking. Then I think 1 minute, even we can take 1 or 2 or 3 depending upon how many is showing interest. Okay, so please feel free to say something about your experience. Okay.
Yeah, I guess I'd suggest to say from young researcher awardee, if there's no volunteer. Dr. Chun Ma and Professor C.T. Tong, Xiaoyang, Ali Nagar, I think 4 of, Krishma, I think 5 of all the awardee attended this meeting. So I think they can say something for us.
Can I start?
Sure.
Yeah, I'm Dr. Bhavya. Thank you very much. And I would just like to state that the biggest advantage that I saw in 3 days is to understand the recent developments in this area, because all of us are familiar with the area of pyrolysis, but getting to know at a single place as to what everybody is currently involved in working, and like Professor Oak in his last session on biochar also asked all the panel members like what their research idea for the next 5 years is. So these kind of inputs are like extremely useful for young researchers like us, who will be able to take this forward by trying to see as to how we can try to fit in this kind of an area and use this potential to proceed further. So I think we thank all the senior members of the forum and also my co-participants to have provided us with such a huge information and the recent developments in this area. Thank you.
Thank you, Dr. Bhavya.
Okay, me?
Oh, yes. Come on, please.
Okay, the first thing I want to see, actually my full name is Chuan Ma. They make some mistake about the name, even around the email they send me, and also the young researcher world. The first thing. And the second is, I'm very glad to get this award. I'm very happy actually. And actually, I heard a lot of the presentation these days. They're about the pyrolysis and also the plastic and biomass biochar. And actually, I learned a lot because as we discussed with Professor Shogo Kumagai and Professor Yoshioka Sensei, we have like the proposed, I write about the biochar and also the plastic. I combine them together. Actually, I learned a lot from your all of your presentations. I mean, they give me a lot of information. They can tell me how I should do further if I want to improve my research in this area. Actually, I think this conference is very useful for both of us. Again, I want to say thank you very much.
Okay. Okay, so quickly, who is going next? Okay. Yeah.
Yeah, go ahead.
Yeah, go ahead.
Okay, this is Xiaoyang from CAS. And first of all, I have to say many thanks for the academic community and to give recognition to the young researchers, because for young researchers, actually the first of all, we don't have the most difficult things is to focus on some specific topic, because we only try to follow by some hot topic, but it's very difficult to how to say, to get the confidence. Actually, during the conference, I really learn a lot of things from the panel discussions, because most of the professors, they just share their 30 years or 40 years research experience to all the young researchers, young generations, and it really make a big impact to the young researchers, because as we know, we all know the pyrolysis is a very common, conventional and method to produce products. But actually, we can see the pyrolysis has many different ways, and those ways will give many different very high impacts to their properties of the pyrolysis products. So the first of things, the professors and the leading professors give us very clear directions that can provide such wonderful opportunities to let the young generation to follow up. And this is the first thing. And another thing, secondly, I would like to say thanks, because for the young generation, we do a lot of paperwork every day, but actually we need some confidence, and we need some how to say, encourage, because we published a lot of work, but we didn't make any, we didn't make not that more many changes. But once we get some award, then we got the new motivations, and we know we're working hard. When we will receive award, and we will continue and keep fighting. So this the two things I really want to share with all the young generations, and we also want to say thanks to all the mentors, because they really provide a clear way to keep moving forward. Thank you. That's all.
Just have a few words to say.
Sure.
Yeah, first of all, thank you, Pyro Asia. Thank you, the organizer. Thank you, the reviewing committee, for giving me this award. It is really an honor. So I'm very grateful, and thanks for your recognitions. I mean, Pyro Asia really rocks. I really like this conference. It gives us the opportunity to share our research, and also bring together all these big names in the area of pyrolysis. I mean, I've seen a lot of your papers, but I've never met you guys in person. So this is the first time I joined this conference dedicated to pyrolysis. So I feel very included in this community, and I really hope to work with you guys someday. And for next year's Pyro Asia 2021, Professor Ock, definitely I will try to make it to Korea. So thank you again, and Pyro Asia rocks.
Thank you.
Okay, thank you.
Thank you.
Thank you. Okay,
Yes, thank
yeah,
you.
just coming.
Maybe can I start?
Yeah,
sure. Yeah.
Sure.
Okay. Yeah, thank you very much. I would like to thank the organizing committee, the reviewer committee, and thank you very much for this nice award. It will be a good memory for us from PYRO Asia 2020. Actually, we have been growing with the guidance of our appreciated seniors and our supervisors, as well as the support of our families, our friends. So when we get this kind of recognition, we feel like that we would like to thank all of them. So thank you for all of them who supported us as a young researchers. Maybe some of them are here, like my PhD supervisor, Professor Beyonce Cook. And finally, I like also tell you guys that we believe all that biochar is a promising solution for a number of environmental issues. So we would like to promote biochar application within our societies and to spread out this culture of biochar application in our societies. Thank you very much.
Okay, can I ask any of the PhD student, Ms. Munmi, or I see one like Mukesh or Munmi, can you say something as a PhD student? How was your experience?
Sir. Yes, sir. So it was a very good conference, and I really enjoyed 3 days of the conference. And I actually have got the opportunity to interact with many of the researchers and the speakers. So it was a very big opportunity for me. And I feel that in the future, after my PhD, if I get any chance to do some research on pyrolysis, like catalytic pyrolysis or biochar, then it will be, I am highly interested to work in such areas. So let's see. Otherwise, I really like the conference.
Yeah, sure. Yes. Okay, great. Yeah, so you please continue your interaction with the big names. So wherever you see the interest, you have to keep your contact intact.
Yes, sir.
Okay, so I would like to request the young researchers, like the awardee, like you have to be a future leaders for this forum also. That means slowly you have to take up some responsibility to run the show in this forum. Okay, you will assign that slowly. At least I want to mentally prepare you people, so that we can give you some assignments for future conferences. Okay, with that, I would like to thank everybody in this call. And let's enjoy our Sunday, at least the Sunday evening. And then tomorrow we are back to our routine. Okay, so have a good rest. Okay, also, yeah, so we will keep you informed about the awarding webinar plan in January or February. Okay. All right. Okay, so if no further comments, let's just end this call. And thank you all, and have a nice evening. Bye bye.
Yep. Thank you. Bye bye. Bye, Shah.
Bye bye. Congratulations. Congratulations. Congratulations.
Goodbye.
Okay, bye. I'm going to close it. Thank you. Enjoy your evening. Enjoy your work life. Bye bye. Cheers.
Thank you.
Bye bye. Bye bye. Cheers.
Thank you.